Okay, we are going live now.
By the way, are we live?
Wait,
Are we?
Yes.
no, not. Are we? No.
Didn't you say?
We are going now, like the progress bar is going.
Yeah, but probably it's buffering and then.
Okay, now we are
Hello,
on.
what?
Yes.
Okay. You can mute if you want to say something.
Are we?
Yeah. So, good morning, everyone. Welcome to another edition of SaLWo. Today, we're going to discuss several exciting works in the line of storage-centric computing. The first talk, Andreas is going to discuss about this work, RISE, our recent publication in ISCA 2025. Andreas is a first-year PhD student in the Safari Research Group at ETH Zurich, advised by Professor Mutlu. His research interests lie in computer architecture, focusing on DRAM, hardware-software co-design, and virtual memory. Before joining Safari, Andreas received his master's degree from the National Technical University of Athens, working on system-level optimizations for DNN inference and energy-efficient LLM serving. So, stage yours.
Yeah, thanks for the introduction.
Thank you so much, Andreas.
So, hi everybody, I'm Andreas, and today I'm going to be presenting our work RISE, a high-performance and energy-efficient retrieval system within storage processing, which was presented this year in ISCA. So let's start with an executive summary. The problem is that retrieval augmented generation, or RAG pipelines, incur data movement overheads between the host and the storage system. And at the same time, existing in-storage processing, or ISP solutions, only accelerate the nearest neighbor search stage of RAG and introduce significant area and power overheads. Our goal in this work is to alleviate the I/O data movement overheads of RAG by accelerating both nearest neighbor search and document retrieval without modifications to the storage system. To this end, RISE introduces a lightweight scheme that links embeddings to documents, an ISP-tailored data placement algorithm, and an approximate nearest neighbor search, or ANNS engine, that uses the existing computational resources within the storage system. Our key results are that RISE improves throughput and energy efficiency by 15 times and 55 times over the CPU, respectively, and it reduces the I/O data movement overheads of RAG to under 0.2% of the total runtime of the RAG pipeline. In addition, it outperforms an existing state-of-the-art ISP-based ANNS accelerator by up to 2.5 times. So this is an outline of my talk, and I'm going to start with a bit of background. This is what a typical LLM inference pipeline looks like. A query is received by the inference system, and then it is fed through a large language model, which usually runs on a GPU, to create a response. However, large language models can only generate responses from data that they have seen in their training sets, and they require expensive retraining to memorize new data. This is a problem because it limits their effectiveness in real-time and domain-specific applications. So to solve this issue, researchers have proposed retrieval augmented generation, or RAG. RAG combines the text generation capabilities of large language models with information retrieval techniques from document databases. RAG identifies the most relevant documents to a user query to generate a high-quality response by combining the information from the relevant document chunks. To achieve this, RAG first uses an embedding model to generate embeddings for both the query and the document database. Embeddings are multidimensional vectors representing the information contained in the query and in the documents. Unfortunately, they can be quite large, reaching up to 8,000 dimensions. As a result, the document database has to be stored in the storage subsystem and usually in flash memory. The next step is to then identify relevant documents using a process called nearest neighbor search. Nearest neighbor search involves calculating the distances between the query and the database embeddings and identifying those with the smallest distance to the query embedding. To generate the response, RAG then combines the documents that correspond to these embeddings with the query, feeding them to the LLM to generate a response. The problem, however, here is that nearest neighbor search creates significant data movement between the CPU that actually does the calculations and the storage system that holds the embedding vectors, and also that the large embeddings, which have thousands of dimensions, lead to expensive distance calculations. So to try to alleviate these overheads, researchers have proposed multiple approaches. And one family of such approaches is quantization, for example, integer quantization, binary quantization, or product quantization that reduce both the bit width of data as well as the total dimensions of the vectors. And another big family of approaches is in-storage processing, which employs the computational resources within the storage system and takes advantage of the large internal bandwidth of the SSDs. In our motivation section, we analyze both of these approaches. First, we perform a latency breakdown of all the stages in the RAG pipeline when using binary quantization. So as you can see from this figure, dataset loading comprises almost 70% of the total latency of RAG and dominates the total runtime for large datasets. We thus deduce that quantization on its own is not enough to alleviate the data movement overheads of the RAG pipeline. Second, we explain why existing in-storage nearest neighbor search accelerators are not suitable for accelerating RAG pipelines. Specifically, existing designs mainly accelerate the search process, which only comprises a small part of the total latency, but they do not provide support for accelerating the retrieval of documents from the storage system. In addition, they introduce significant modifications to the design of the SSD, and they incur prohibitive power and area overheads, which further hinders their adoption. So our goal in this work is to fundamentally alleviate the I/O data movement bottlenecks of RAG through an ISP design that does not require modifications in order to perform computations inside the storage system. To this end, we propose RISE, which stands for Retrieval System with In-Storage Processing. The key idea of RISE is to leverage both in-storage and in-flash processing to exploit the computational parallelism of flash storage and conserve precious flash channel bandwidth. When RISE is deployed, the host system offloads RAG retrieval to the storage by sending the query embeddings and then receiving relevant document chunks from the storage system. To achieve this, RISE employs three key mechanisms. The first is an efficient ISP-tailored implementation of the inverted file algorithm. The second is a low-cost embedding to document linkage mechanism. And the third is an ANNS engine that uses existing computational resources within the SSDs. However, this is not straightforward, as the design of the storage system creates unique limitations. For example, the embedded cores of the storage system have limited performance and functionality. For example, they lack floating point arithmetic support. Second, the computation inside the flash chips is limited to simple bitwise and bit counting operations. And third, error correction limits ISP performance due to data movement overheads between the flash chips and the embedded processor. Despite these challenges, we base RISE's design on the existing design of the SSD, which is comprised of multiple processors, a small amount of DRAM, and then multiple flash channels with multiple flash chips each that are then composed of multiple flash dies. Each flash die contains multiple planes and pages, a page buffer for each plane, and peripheral circuitry, which all contain logic that can be used for computation. In modern system, the flash pages store data, and they also contain a small amount of reserved space, which is called the out-of-band region, and which is used for error correction purposes. So let's now move to the database layout of our proposed design. Rice's database layout creates separate regions for storing embeddings and documents, and it stores embeddings using enhanced SLC programming to provide robust ISP operations. It also stores documents in TLC in order to provide high storage density. Both embeddings and documents are stored contiguously to avoid address translation overheads, which usually occurs in the embedded processor of the SSD. And finally, it links embeddings to documents via the out-of-band region found inside flash pages. And this again reduces the overheads of address translation because once an embedding is selected in the search process, the relevant document chunk can be directly retrieved without the need to perform address translation. So while this database layout can be used to facilitate exact nearest neighbor search, Rice goes a step further and also provides support for approximate nearest neighbor search, which provides higher performance. Specifically, Rice employs the inverted file algorithm, or IVF, with binary quantization to accelerate nearest neighbor search. IVF first organizes embeddings into clusters, and then the search process occurs in two steps. First, we perform a coarse-grained search to identify the nearest clusters to our query embedding. And in a second step, we perform a fine-grained search within the identified clusters to find the nearest embeddings. The inverted file algorithm provides high performance and accuracy, even with binary quantization. And it also features characteristics, which are actually streaming access patterns, that make it suitable to the storage system. As a result, we choose to design an in-storage ANNS engine that provides support and accelerates the inverted file algorithm. So both for the coarse and the fine-grained stages of IVF, the ANNS engine first copies the query embeddings to the page buffer inside the flash dies, and then moves the document embeddings to the page buffer. At this point, it calculates the distances using logic in the page buffer and the peripheral circuitry, and it then transfers the distances back to the SSD's read DRAM. At this point, the embedded processor of the SSD performs quick select to identify the nearest clusters or the nearest embeddings, and then performs re-ranking and quick sort to further refine the search results. After the search process is completed, the ANNS engine moves the identified document chunks to the SSD's DRAM, and finally transfers them to the host to complete the RAG retrieval stage and continue the LLM generation process. To further improve our design, we propose 3 additional optimizations, which are distance filtering that quickly filters out embeddings with large distances without transferring them to the embedded processor. So in this case, when the distance of an embedding to the query embedding exceeds a predefined threshold, it is immediately dropped, and we don't do any further computations using this vector. The second optimization is multiplane input broadcasting, or MPIBC for not so short, which parallelly transfers the query embedding to multiple planes at the same time. And the last optimization is pipelining, which overlaps flash page reads with distance computations for another page. I will now move on to the evaluation section of RICE. So for our evaluation, we use multiple baselines. We have CPU real, which is a CPU-based RAG retrieval system running IVF. And then we have no IO, which is the same CPU-based system, but this time without taking the IO overheads into account. We also compare RISE to ND search, which is a state-of-the-art ISP-based approximate nearest neighbor search accelerator. We evaluate our performance on both exact nearest neighbor search, which is a brute force approach, and thus we call BF, and also using the inverted file algorithm, or IVF. And we evaluate throughput, which we measure in queries per second, or QPS, energy efficiency, which we measure in queries per second per watt, and we also perform an evaluation of the end-to-end retrieval performance when using both of these approaches. We evaluate RISE on many different datasets and on two SSD configurations, SSD-C, which is a cost-oriented SSD design, and SSD-P, which is a performance-oriented SSD design. So let's start with the performance evaluation. For the performance evaluation, we compare the throughput of NoIO and RISE on SSD-C and SSD-P. In the y-axis, we plot throughput, which is normalized to that of CPU real, and we evaluate performance on both brute force and IVF across different ranges of recall values. We can see that RISE outperforms NoIO due to the massive parallelism of the SSD, and also that our performance improvements over the NoIO baseline actually increase at higher recall values. So it goes from 2.3 at 0.9 recall at 10 to 3.3 times at 0.98 for recall at 10. We perform a similar experiment for energy efficiency, and this time the y-axis represents queries per second per watt, which we normalize again to the same metric for the CPU system. And we again draw a similar conclusion, which is that improvements in energy efficiency increase at higher recall values, from 28.6 times to 46 times almost. In the paper, we evaluate this on multiple different data sets, and we observe that the patterns are largely the same, and also that the performance benefits increase with larger data sets, again, due to the massive parallelism of the SSD. So let's now move on to the evaluating end-to-end performance. We repeat the latency breakdown experiment from the motivation section, this time also performing document retrieval with RISE. As can be seen from the plot, the once almost 70% of latency stemming from dataset loading and search is now combined into a single in-storage retrieval step that comprises just 0.15% of the total latency. And we thus conclude that RISE eliminates the data movement overheads from the RAG pipeline. In the paper, we also perform a sensitivity study which quantifies the speedups provided by our optimizations on top of our basic design, which we call NOPT in this study. In the x-axis, we sweep different target recall values for recall at 10. In the y-axis, we measure queries per second, again normalized to the throughput of the real CPU system baseline. And the different lines correspond to different configurations, each adding a different layer of optimization on top of the previous ones. We perform this experiment both for the cost-oriented and the performance-oriented SSDs, and we see that on average, distance filtering provides a 5 times throughput increase across all configurations on average. Pipelining provides an additional 1.4 times speedup on top of that. And multi-plane input broadcasting improves performance on SSD-P by 26% on average on top of pipelining. So if we combine all of these optimizations together, they offer a combined performance improvement of almost 13 times over the basic NOPT baseline. For my final evaluation slide for today, we have a comparison to ND search, which is a state-of-the-art approximate nearest neighbor search accelerator design. For this comparison, we normalize the throughput of RISE to that of ND search, running HNSW and disk ANN, which are two graph-based approximate nearest neighbor search algorithms. And we evaluate both RISE and ND search on the SIFT 1B and DEEP 1B datasets. Rise improves performance by 2.5 times and 1.8 times over ND search when running when ND search runs with HNSW, and 1.05 times and 1.36 times over ND search when ND search is running with this KNN. We attribute like the performance benefits and the performance improvements of Rise to the fact that IVF features streaming access patterns that exploit the internal bandwidth of the storage system much better than the more irregular graph access patterns of these algorithms. Our paper is available on arXiv, and there you can find more details about our implementation. So let me recap my talk again. The problem we attempted to solve is that RAG retrieval is currently bottlenecked by I/O data transfer overheads between the host and the storage system. And to solve this issue, we proposed RISE, which is the first system for RAG retrieval that leverages in-storage processing using the existing computational resources within the storage system. Our key results are that RISE outperforms CPU search by 15 times on average. It improves energy efficiency by 55 times on average, and it reduces document retrieval latency to a negligible under 0.2% of the total RAG pipeline. Finally, it outperforms an existing state-of-the-art accelerator and the search by up to 2.5 times. So this was my talk, and thank you for your attention. If you have any questions, please.
Thanks, Andreas, for the great talk. So I have two questions, and the first one is a high-level question. So this work, the background of this work, talking about like large language model, right?
Well, the applications of AI and NS are like the hottest topic right now is about RAG, because that's where the big workloads exist. Yeah. But it's more general, like it can be extended. This was a traditional workload even in the past.
Yeah, so it can be, I mean, deployed to any search algorithm, or focusing on the type of the searching algorithm.
But, you mean RISE specifically?
Yes.
Yeah. So because we wanted to exploit the high sequential bandwidth of the SSDs, we settled on IVF, which again demonstrates these patterns. However, there are other works that do the more graph-based algorithms. But even in this case, we show that RISE with binary quantization and IVF can achieve reasonable accuracy, very good actually, if we combine it with a lightweight rescoring step. So we fetch actually more embeddings than we need to in the first step of the process. And then we refine our search by performing a more detailed comparison of a few elements. This wasn't in the presentation, by the way, using a higher precision, so int8 embeddings in that case, not binary quantization.
Okay. Yeah. And the second question is, what type of data movement is eliminated by this work? Because I still saw some data movement between the flash and SSD.
Yeah, you mean between the storage and the host, right? Yeah. So usually, if you wanted to perform search on the CPU, for each embedding, you would have to fetch it from storage and move it to the CPU. And then after the search is completed, you would fetch the documents that correspond to these embeddings. So in this case, we perform the entire search step inside the storage system. And finally, once the search is resolved inside the storage, only then we transfer just the document chunks, which would have to be transferred. There's no other way, because you need to get them to the GPU to perform inference.
Yeah, I mean, when I see the slide, maybe.
Yeah.
How was that?
Okay. Like in the beginning, probably.
Yeah. Maybe just the next slide. To the.
Yeah.
maybe the architecture part.
That's interesting. Here. Yeah.
So for here, the document chunks means the final result.
Yeah, it's just the pure documents containing the relevant text to the user's query.
Okay.
Yeah.
So I have one issue, one question about this figure. So part of RISE has been implemented in the flash chip as well, right?
Yes,
we do some computation with that.
So it's actually like very limited. The modification RISE is essentially a firmware design.
Yeah. Okay.
So there is actually like we don't need to perform a lot of modifications to support it.
Yeah.
I don't think it's plug and play like to a modern SSD, but if we really wanted to do this, it would be very, very straightforward because all the hardware needed to perform these operations is already in the storage system. We just need to orchestrate the operations a bit differently in a different order. But it should be very, very easy.
So what's the exact operation we are doing the flash chips?
Okay, that's a good question. So let me go to this slide here. So here we have both the query embedding and the document embeddings in the page buffer. And there is XOR logic, which will compute a bitwise, basically a bitwise XOR between the two, these two vectors.
Mm-hmm.
And then the peripheral logic contains the fail bit counter. Now, the fail bit counter is usually used to see if there was an error reading the page to then do read retry. But in our case, we can actually use it to compute the Euclidean distance or the Manhattan distance for one bit elements. It's the same distance actually, which produces our distance score. So the logic that happens inside the flash chips is the distance calculation and also the optimization that does the distance filtering that compares the distance that is produced to a threshold and then drops the vector altogether if it exceeds a predefined threshold.
So yeah, exactly.
Yeah.
So that part was my question. How do we do the comparison? Because one of the main reasons that we are getting improvement is that we are reducing a lot of data in the flash chip.
Yes.
And that's why actually when you were
in the sensitivity study, right?
Sorry?
In the sensitivity study.
Yeah, exactly.
Yeah.
When you were reducing the recall.
Yes.
Basically, we are reducing more data. Right?
Low recall enables us to more aggressively filter out embeddings.
Yeah.
So there is less traffic going to the SSD controller, which is weak in terms of computing performance, and we generate less load essentially to the embedded processors.
So how do we do the comparison inside the flash chip? For that, don't we need to change anything?
The logic is already there to calculate basically how many errors are in the during the read.
Yeah.
So instead of computing a number of bits, we just add the distance threshold there. We replace that value.
Oh, I see.
Yeah.
I see.
In the peripheral logic of the.
So basically, we repurpose.
We repurpose all the existing components that are there for ECC essentially.
Okay. Yeah, sounds good.
And this also because we do the enhanced SLC programming mode. That's what allows us to remove these elements and repurpose them for our code.
So my next question is that, so we are using this IVF, which is cluster-based approach, to make sure that we can parallelize our search across all flash drives, I guess, right?
Yeah.
I assume you are also using the multi-plane operations in a DOT, right?
Yes.
So how can we make sure? So in the beginning, everything looks good, but maybe after some time that you might need to change the position of the pages because of internal SSD operations. So how can we make sure that we can keep using this cluster-based approach, as we go to the future?
That's a tricky question. Like updates are a bit difficult because we have this contiguity. And if we try to do wear leveling, for example, it might get a bit hairy in that case.
Yeah.
But I think we can just move like one cluster somewhere else and just change the mapping in the out-of-band area to somewhere else.
And how big is those clusters? Each cluster, how big is it?
In the IBF algorithm,
Yeah.
I mean, it's configurable, and also it depends on our target recall probably. Yeah. So more clusters is probably better.
Okay, and so I understand that you're searching. You try to be regular as much as possible to to get good parallelism. But when you want to basically retrieve the documents that you want, that search can be actually a bit random, right? Not that it's not a search, but when you access flashes to retrieve documents, those can be random accesses, right?
Yes.
Do we have any support or any idea in this paper to how we can, provide better parallelism also for document retrieval?
So because we have this rescoring step, I think that's another idea actually here, which will take some time to compute. We could potentially overlap this because we will fetch 10 times the amount of data vectors that we're eventually going to select, prefetch a large amount of the document chunks that correspond to these embeddings, and then by the time the rescoring step is completed, maybe we will actually have prefetched everything, and we are ready to transfer these out to the host system. So while the refining step
but basically, when you want to overlap, you need to make sure that your channels are free. So when you're doing this searching inside the flash chips, that you are saying that that's going to take some time. So channels are free in the meantime, and I can use that.
After we have done all the transferring out to the SSD, then we're going to do quick select and some sorting to perform the rescoring. So while this is happening in the SSD controller, the flash channels are underutilized.
Okay, and
so
we can use that.
We can use that to prefetch.
And my next question is that how large is that? Because when you want to prefetch, you need to have a large enough DRAM,
So it shouldn't be too hard because the embeddings, like the document chunks, are kilobyte sized.
Okay.
And in our evaluation, we fetch like the 10, 100 embeddings.
Okay.
So
it's in the line of 100 megabytes.
Maybe megabytes, yes. It shouldn't be a problem.
Yeah, sounds great.
In RAG applications, the databases are huge, right?
Yeah.
So in your evaluation, you're only using one SSD, right?
Yes.
Okay. What would happen if you would need multiple SSDs or multiple devices to store your database?
Yeah, I think that there is a way to distribute this. So you can still distribute the clusters to different SSDs. And the only difference here is that you need to exit the SSD to basically identify the nearest cluster in the first step. So this would mean going to the CPU to find the nearest cluster, and then again in the end to perform the quick select or quick sort. But actually, a lot of the benefit, which comes from the distance filtering optimization, still happens in the SSDs because we are dropping a lot of unnecessary vectors very quickly inside the storage systems on multiple SSDs at the same time without incurring any penalties from transferring data out. So I would argue that it's probably very good. It will probably scale very well.
In this book, you describe just the IBF way of doing DNS computation. Are there other ways? And if there are, why specifically do we choose IBS?
IBF, yeah. So there are other ways, like there are many other works. There are also works that were presented in the same conference as this paper. And they take a different approach, which is to use graph-based algorithms, usually HNSW, highly navigable small world. Yes, I got it right. And these essentially, they construct layers of a graph, and then at each step, it's a hierarchy of graphs. So they cluster nodes of the graph together, and then they traverse the graph from the top layer to the bottom layer and refining the results at the same time. That's another way to do it. And there is also locality sensitive hashing as a different approach. But we have evaluated LSH as well, and this didn't give us the accuracy that we were looking for, so we dropped it. It doesn't perform well when you have vectors with very large dimensions. And also we selected the IVF over the other approaches because it really enabled us to exploit the high sequential bandwidth of the SSDs.
Makes sense.
Yeah.
Because the graph traverse.
Yeah, so here you could get like every let's say every flash page inside, you could just stream through them one by one. And this would be the entire thing would be a cluster that you can very quickly stream through.
Yeah, makes sense.
Andreas, so you can hear me, right?
Yeah.
So how aggressive of a dimensionality reduction did you do to apply LSH?
I'll have to look into that. I don't remember it off the top of my head. Yeah.
Okay.
Yeah.
And also about distance filtering. So let's say I'm aiming for 0.94 recall across data sets, all of them. So how do my thresholds differ, like across data sets? Does it wildly differ?
It's actually no. From what I remember in the paper, it doesn't differ a lot, and we actually have pretty much fixed thresholds across multiple data sets, going a bit conservatively, because even going conservatively, it still provides a very big performance improvement.
I see. So you don't have a fine-tuning overhead or something?
No.
I see.
Yeah.
Also, lastly, maybe you mentioned it, but do you deal with optimizing the initial vector database layout, like optimizing it in the sense that putting some similar embeddings close by in the storage?
I mean, IVF does this for us because it organizes them into clusters, and the clusters contain embeddings that are roughly similar to each other.
Okay.
Yeah.
Okay. Thanks.
I can barely see you because you're right behind the light.
Is it fine?
Yeah.
Okay. So I just want to can you just explain how exactly you store the embedding region and the document region at the same time in Flash? Like how is the data layout based?
So these are completely separated from each other. They're not stored in the same area. And the way to link these two together is that inside the out-of-band area of the embeddings, which are stored in SLC and thus enhanced SLC programming, and thus are reliable, we store the physical address of the document area. So this embedding corresponds to that document chunk.
So on this embedding region, you need to perform those modification in ECC and those steps, right?
Yes,
on this
yes,
embedding
yes,
region,
yes.
which is an enhanced SLC.
Yes.
And that's how you get into
Yes,
it.
yes. But so there are other works that kind of show that you can have both of these things at the same time. You can have a part in SLC and a part in TLC.
Okay. Yeah. And the second brief question is, how large of a space do you need in your DRAM to actually reserve some of the intermediate data for your processing?
So let's think about this a bit. Like the embeddings can be up to 8,000 dimensions. we reduce it down to a single bit because we do binary quantization. So 8 kilobits, 1 kilobyte. And we usually fetch, like I would say, probably a few thousands of embeddings. So that would be in the megabytes.
So is it actually same as how many number of pages you can access in parallel? Because that's what you're going to read once at a time, right? And store it in the.
Yeah, but a lot of these are going to be dropped and
Yeah,
not
exactly.
go
So
to
you will
the.
pipeline it in such a way that you don't use more DRAM space, right?
Yeah. No, what I mean is that you will not transfer all the embeddings out to the SSD's DRAM.
Yep.
You will drop most of them.
Yeah, that's it. Okay.
Yeah, Nika?
Would this design require any changes in the file system, or because the higher layers have changes you make to the SSD?
Can you repeat
So,
the question, because this might not.
sorry?
Just repeat the question.
Yeah. So the question is if doing this will require any changes to the file system. So I think we designed RISE in order to just upload the retrieval process to the SSD, but we still wanted the SSD to be able to operate in a normal mode, like as a regular storage system. But we cannot do both of these things at the same time. So in this case, what happens is that we flash out, when we turn over to RISE mode, we flash the FTL metadata from the SSD's DRAM, and we go into full RISE, bringing in the relevant metadata about the clusters, about IDF. But the problem is that if somebody wants to use a regular storage system, they cannot do it at the same time because they have been flashed. So it's either one or the other at any given moment. Yeah.
Okay. Any other questions? That's quite interactive talk. Thanks a lot,
Yeah.
Andreas.
Thanks for the questions.
Who's next?
Mine is a very short one. It's just intro to
My turn to ask
Konstantina.
questions.
Huh?
My turn to ask questions.
We'll just get started.
Let me introduce you,
Oh,
or maybe you can introduce
that's okay. You can.
I'm trying to find the video, but maybe I will say something. Okay, so for the next talk, Nika, she's going to discuss about, I think, several works, right?
Yes,
That
a
she's-
summary of our works and research.
Yeah. So Nika is a sixth year PhD student. I have known Nika since 2017, and she was brilliant back then. She's even more brilliant.
It was not written in my bio.
That's how I creative I can be, right? So yeah, and I think she's gonna be also on job markets later.
Too early to announce that.
Too early to announce that. So okay, then yeah, feel
Not
free.
this second.
Yeah, stage yours, Nika, and feel free to discuss.
Sure. Thank you so much, ma'am.
Yeah.
Okay, so this is a very brief talk, and it's just an overview of several works in this direction, and I hope that it sets the stage for Konstantina's talk, who will talk about one of the recent works in more detail. So storage-centric systems for genomics and metagenomics. So genomics and metagenomics are very critical for applications such as uncovering and treating diseases, developing personalized medicine, detecting pathogens in an environment, and also rapid surveillance of disease outbreaks. All of these applications and many more rely on understanding and analyzing the genomic information that is encoded in the DNA. So by comparing the genetic information of a sample's DNA to other samples or to reference genomes, and based on the similarities and differences we find, we can make medical or biological conclusions that can guide all these applications. And the information that is encoded in DNA gets translated to digital data that we can analyze using these high throughput sequencers. But the point is that these sequencing technologies cannot read the whole DNA end to end, and instead they extract the smaller fragments of the original DNA known as reads. So therefore, genomic applications require us to map these reads back to the reference genome, and at the locations that these things match, perform operation called alignment that finds the exact similarities or differences between the reads and the references. And that is done via computationally expensive approximate string matching operations. So based on these points that I mentioned, genomic and metagenomic applications typically require performing expensive computation on large amounts of data. Right? So then therefore they suffer from computation and data movement overhead. So what is metagenomic here now? So metagenomics is the study of genome sequences of organisms that are in a shared environment. For example, in human blood or gut, soil, ocean, etc. And it overcomes limitation of traditional genomics for cases where we cannot separate these organisms to analyze them individually. And therefore, metagenomics on its own also has led to a lot of new advances in medicine and various biological domains. But then since we don't know what are the species that are in the sample, metagenomics typically requires performing, some tasks to figure out what is actually in the sample to begin with. So let me show you here these organisms' DNA. So we have here preparation of input queries typically at the first stage, which we extract some shorter subsequences, which are called k-mers, sequences of length k. And the second step is to find what are the species that are present in the sample by looking up these k-mers in a database that contains information on many species. And these databases that actually can be very large, exceeding more than 100 terabytes in emerging cases, and even growing at a fast pace. So after figuring out what are the species that are in the sample, there is also optional step of finding their relative abundance. So the problem we have with genomics and metagenomics today is that we have these specialized, very high throughput devices to generate this data, but then relying on general purpose systems to analyze it would be extremely slow because of computation and data movement challenges that we talked about. So because of the importance and the impact that these fields can have on many areas, there's been a lot of effort also in industry to devise or to accelerate these things with the specialized hardware. And also in general, in both academia and industry, there are a lot of efforts for making this faster via efficient heuristics, accelerators, or some filters. While these things help actually a lot with computation overhead, they still do not address data movement overhead from storage system, whose impact actually on end-to-end performance becomes even more pronounced when other bottlenecks get alleviated. So today I want to very briefly just make a case for storage-centric systems for genomics and metagenomics by summarizing our past and ongoing efforts in this direction. So first I will talk about very briefly about GenStore, which is storage-centric design for genomics, then about Medis, which is a storage-centric design for metagenomics. Then I will just mention our efforts on some more emerging areas in genomics and metagenomics by talking about grains and also mentioning Mars, which Konstantina will talk about more. And finally, before I conclude, I will also talk about efficient analysis and compressed genomic data, which is a very important one. So let me start by just very briefly mentioning GenStore. So the key idea of it is to filter reads that do not require all that expensive computation just directly inside the SSD. and send the reads that do not require expensive computation outside. And then examples of such types of reads that do not require expensive computation are reads that exactly match. So if you remember, we talked about approximate string matching. So these would not require that expensive computation. And reads that do not have any matching locations, meaning there is no location in the reference to go and perform expensive approximate string matching on that. So of course, there are also challenges to do this because read mapping workloads can have very different behavior based on the features of input set, meaning with which sequencing technology they're generated or from which species they're coming from. And add to all of that, the fact that we have limited hardware resources in the storage system to perform computation. So by addressing these challenges, our WorkGenStore is the first storage processing system designed for genomics that alleviates computation and data movement overhead. And we show that compared to state-of-the-art software and hardware approaches, it provides significant speed up and energy benefits at low cost. Of course, there are a lot more results and implementation details or like design details in the paper, so you can check it there.
Nika, before you move on,
Yes.
We should share your slides to the Zoom.
Oh my, that's
It's okay.
a nightmare.
No, it was actually good, but we wanted to.
Oh, you could see something at least. Okay.
Yeah.
Where is it?
Yeah, it's okay now.
Perfect. Okay, now we go to. I thought the screen is shared and not the slides, so I did not know screen sharing would stop. Okay. I will go to my gift. This time we can even see it. If we can. Okay, so that is the insert processing system for metagenomics. Okay, so these are the steps, the traditional high-level pipeline of metagenomic analysis tools. And as discussed, it requires accessing very large databases. So we perform a case study of performance of metagenomic analysis tools with various state-of-the-art storage systems. And we try to compare to an ideal configuration with no overhead. This system is performance optimized and cost optimized. We incur large data movement that leads to very high network performance overheads. And in fact, we observe that this overhead becomes even larger, has even larger impact in turn performance and other bottlenecks, such as memory computation, is using large amounts of data is very difficult and very hard to avoid this. One might think that it is possible to perform some sampling techniques to shrink the data to the size, but that leads to accuracy loss, which is not tolerable for many accuracy critical applications. And another potential solution might seem to be keeping all data required by metagenomic analysis completely and always in main memory. But such a solution is inefficient, costly, unscalable, and also unsustainable. And that is also two reasons. One is that these databases, which are already large, grow in size very rapidly. For example, they double every few months. And the second point is that different analyses require accessing different databases. So it is not sustainable to keep all databases all data that will be required by all possible analysis in main memory at all times. So motivated by all these points, our goal in this work has been to improve metagenomic analysis performance by reducing data movement overhead from the storage system in a cost-effective manner and with high accuracy. So, like in storage processing, which basically processes data directly inside the SSD, can be a promising solution. We have this challenge that no metagenomic analysis tool can actually run inside the SSD due to SSD's limitations. such as long latency of NAND flash chips, limited DRAM capacity inside the SSD, and limited bandwidth of that internal DRAM. So our work, MIGIS, is the first in-storage system for end-to-end metagenomic analysis with the idea of cooperative in-storage processing for metagenomic analysis, which is enabled by an efficient hardware-software co-design between the storage system and the host system. So to effectively leverage and orchestrate the capabilities of both systems, we perform hardware-software co-design in 5 different directions. The first one is to partition the tasks and map them in the hardware that they take most advantage of. And the second step is to perform some data and computational flow orchestration so that we don't incur large data movement overhead between the steps of the application, and also we don't incur large amounts of writes to the SSD. The third point is storage-aware algorithmic optimizations. Fourth is lightweight in storage accelerators. And finally is data mapping scheme and flash translation layer that are specialized to the features of metagenomic analysis. So we have a lot of results in the paper, but I want to just focus on one result to show that what this storage-centric paradigm can provide for this class of really data-intensive applications. And that is MIGIS's impact on system cost efficiency. So consider 2 systems. One is a cost-optimized system with low bandwidth SSD and 64 GB of DRAM. And the other one is a performance-optimized SSD with a high bandwidth SSD and 1 TB of DRAM. So in this figure, we are now showing impact of baselines. Here, performance-optimized and accuracy-optimized metagenomic analysis tool. And note that MIGIS reaches the same level of accuracy as the accuracy-optimized baseline. So these baselines are running on the cost-optimized system and performance-optimized system. And we compare them to MIGIS running on the cost-optimized system. And we observe that MIGIS outperforms the baselines even when running on a much less costly system. So that shows that what we can actually gain in enabling larger scale adoption of these critical applications. There are, as I said, a lot more results in the paper, and of course, a lot more details about our design. So please check the paper if you're interested. And now I just briefly mention our efforts in some emerging areas that are playing critical roles in genomics and metagenomics. So first one is about large scale genome graphs. Instead of encoding large genomic sequences in linear ways, genome graphs represent them in forms of graph box. And these graph representations are more powerful and efficient representations of genomic data because first, they have greater expressive power because of their topology and encoded metadata. And second, they're more compact representations of massive and population scale databases. Because in a lot of cases, actually, it will be very beneficial to analyze genomic information of the whole population to see how a specific disease is evolving and many other use cases. So therefore, these graph representations are becoming more and more critical. So our GRAINS is the first storage processing system for large scale genome graphs. And the point is that it first makes these complex genome graph analysis workflows more storage friendly through our specialized execution flow and scheduling. And second, we further improve performance, energy efficiency, and cost effectiveness by our in-storage and in-flash processing designs. And we show that MIGIS provides large performance and energy reduction compared to hardware and software solutions at very low cost. The second emerging direction is this raw signal genome analysis. So typically, many sequencers generate these raw signals that through a process called base calling, they turn into these DNA characters that we analyze. But in some use cases, it will be very beneficial to directly analyze these raw signals. So what are the benefits of raw signal analysis and what are the details of the design? I don't go through it because Konstantina will be explaining a recent paper in a lot more detail just after me. So, and finally, I wanted to talk about efficient analysis on compressed genomic data. So after the development of high throughput and low cost sequencing, the volume of genomic data that we've been generating has been increasing at a very fast pace. And as we discussed, there's been a lot of efforts up and coming also on accelerating genome sequence analysis. But another key effort that has been done is actually to store this genome sequence data in highly compressed formats. So the problem that we're looking into in this work is the data preparation bottleneck, where genomic sequence data is stored in compressed form, which is a typical scenario, in fact, and needs to be decompressed and formatted first before an accelerator can even start operating on it. So let me show you the impact of this bottleneck with a simple timeline. This timeline is not drawn to scale because then otherwise we would not be able to see all parts of it in detail, but this simple pipeline will show the point. So first is that it's a baseline case that we have data preparation and analysis happening in a pipeline in different batches of data. In the second case, we see accelerated analysis because, as I said, many thanks to all this effort, analysis can be accelerated significantly. And the third case is an idealized case where data preparation can happen with the same or even higher throughput than analysis. So we see here, by comparing the first and the third case, that accelerating analysis can actually potentially provide very large benefits, but a large part of that benefit gets amortized due to data preparation bottleneck. So our work stage is an algorithm architecture co-design for highly compressed storage and high performance access of large-scale genomic data. It is enabled by carefully exploiting features and properties of genomic data in a synergistic way to design both the hardware and the algorithms such that we have high compression ratios, which is comparable to state-of-the-art genomic specific compressors, which is larger than general compression techniques. And second is that it enables fast decompression using only lightweight hardware and efficient streaming accesses. And that is important because it enables us to integrate Sage with genomic systems, even in resource-constrained environments. What are they? Examples could be portable systems, which are rising in importance in genomics. And the second one is near data processing systems, such as storage systems that I've been talking about, or in memory processing systems. And we show that by integrating with the genome analysis systems, Sage can improve the average end-to-end performance and energy efficiency of genome sequence analysis accelerators significantly. So basically, it enables us to unleash the benefit that actually these accelerators can provide. Okay, so there are a lot more again in the paper, so I invite you to check. So in summary, storage-centric systems for genomics and metagenomics can lead to a lot of benefits in improving performance, energy efficiency, cost effectiveness, and while I didn't talk about it, they also help us improve robustness, such as security and privacy. And we hope that all these efforts would lead to making accurate metagenomic analysis more accessible for its wider adoption. Yeah, so these are also some of the other ones. And yeah, that's it.
Thanks a lot, Nika.
Sure.
Questions for Nika?
I have one.
Yes.
Thanks, Nika, for the presentation. So I was wondering, do you see genome graph construction also handled in storage anytime soon?
Right, so right now it is not, but it's a really time-consuming step, and it's I think is a very important problem to look into. It is relatively done less frequently compared to analysis state because you would construct some things and then perform analysis with it for a while, but still with the rate that these databases are getting updated, it's becoming a more and more important problem. So I think while as far as I'm aware, there is no work currently, I think it's a very important problem to look into.
Do you see any future for it in storage though?
Yes, definitely, because with my personal experience, just generating large enough databases to perform our analysis for grains, we had a lot of problems, meaning it would run for several days in a system with 1.5 terabytes and then crash after 1 week. So it's already, I think, is a very important thing. Is that what your question is about, the importance of it, or whether the mechanism would be enabled in storage?
No, I agree that it's a very important problem, but I was wondering if you see any potential benefits of in storage processing for that problem. Like
Right.
you mentioned the size, but from the computation side as well.
So computation, yeah, so it requires performing alignments and everything. But I think that at least a storage-centric system would be beneficial for it. Maybe not all the steps of it would be executed inside the storage, but a system in which closely collaborates with the storage system to do it. Because I agree that probably not all parts of it end-to-end can be done just within the storage device.
I see. Yeah. Thank you.
So, Nika, you didn't talk about improving privacy and robustness, but if you can provide some quick insight, how these techniques can provide better privacy and also robustness.
Yeah. So it moves the data simply into into fewer places. So by keeping the data inside the storage system, we expose it into fewer areas to hurt its privacy and robustness. But another point is that specifically within context of genomics, some might rely on cloud environments to do some computation, which exposes again another set of issues, because then you have this shared environment. Whereas if you are able to perform computation, as we saw, for example, in Megis, as opposed to relying on terabyte scale main memory, or like in the future, probably needing to scale it even more and more, you could rely on a system like your laptop, then a medical center can keep its data local and not share it.
Yeah, I think that makes sense for privacy. But for robustness, I think one part of being robust is also being reliable. And by doing a computation inside the storage, it's not easy to do a lot of system level support that we usually have in order to solve errors, because when we read data from storage, there are some reliability techniques inside the storage, but there are also some techniques, at the OS level to fix errors. So basically now I'm seeing kind of a trade-off here, because we cannot do all these complex techniques to improve reliability. So how do you think about it?
Yeah, I think actually, yeah, so as you said, there are two sides to it. One side of it leads to some improvements because of exposing it less to other places, but the other side is that it also has less opportunity to get fixed in other places. There is, and to see the exact trade-off of it, I think is a more, let's say, nuanced manner. And so one is that some of these designs can be able to integrate with other techniques that help with improving reliability, let's say some RAID type of structures. So that is one, because these data are, as we show in each of these works, they can be partitioned efficiently to leverage multiple SSDs, either for higher parallelism or better reliability. But I believe that designing these storage systems such that it enables them to integrate with other reliability enhancing techniques throughout the system would be interesting. Meaning, or to see that how we can integrate some parts of those techniques inside the SSD.
Yeah.
Right. Or so the third dimension also would be, how would they be needed if the data doesn't also move outside?
Yeah, exactly.
Right?
Yeah.
So 3 things.
I think these are very exciting future directions.
Yes,
right?
yes, definitely. Yeah, thanks for bringing it up.
So another related question, like, could we use Sage if we wanted the data not only to be compressed, but also encrypted for privacy purposes?
Not directly. I think that it can be combined with other techniques, but it cannot immediately be used on the data. And I think that looking at combining them would also be important. Let me see, actually. Yeah, I think that combining them would be definitely possible. Yeah. Yes.
So I have a general, okay. So I have a general question. Basically, like as we see that you need some modifications in your SSD. So what do you think, like, is the current SSDs are actually, the host side is actually, if you just modify SSD, host side can handle it, the existing stuff, or you need to modify those protocols also, so that to make it like much more efficient?
Right, right. So in the designs I presented here, the only change we needed was to introduce some extra commands. For example, let me give you the most extreme case, which would be for the case of Megis, which was a lot of back and forth between these systems. So we added some commands, first of all, to mention that we are starting the in-storage processing mode because of loading the metadata, related metadata, etc. But also at the end of each step, we would send a notification between them. So that was what was needed for our designs. But having said that, I believe that it would also be interesting to look more deeply into how the interfaces should change more broadly to enable a smoother integration of these storage-centric systems for broader applications. There are some works going on, but yeah, I think there is definitely an important area.
Okay.
Yeah, so you mentioned that the data size increases exponentially, maybe over like 100 terabytes. So if one SSD storage system cannot hold all this data, you may need multiple or clusters to handle this process. So there's a communication between, some single node system becomes the new bottleneck.
Yeah, good question. So in that design, the data is really nicely, meaning disjointly partitionable, because we rely on pre-sorted databases, so that you know that for this range of data, you would just rely on this SSD. So if you're preparing your data in the, let me go to actually a specific slide. Yeah. So in step one, where you perform some preparation on your data, you would exactly know in advance which partition you need to go to perform your analysis. So yeah, this problem would not arise. And in some baselines tools, that would be the problem actually. But because we changed the algorithm significantly to fit within this computation paradigm, that problem goes away.
Yeah.
Sure.
Any other questions? Okay, so we'd like to, thanks a lot, Nico, first for your great talk. We'd like to improve the sound quality. So we suggest that we can have early break for 30 minutes. And in the meantime, we will improve the sound quality. So let's be back at 10:20.
There is a break.
Sorry?
There is a break.
No.
Okay.
I agree with you.
Okay.
Perfect, thank you.
So, how long did you say for the practice?
10:20, we should be back.
20 minutes? 10:20?
10:20, yeah.
I see.
You should use the mic. Like the sound is a bit choppy.
What are you?
Broken down.
I need to remember what to do.
I also never wrote this exact command.
And you were in the middle of
No, I actually I filed that.
Oh, like-
But when you
Wait.
Okay. Can you hear me?
I'm not sure if it's connected.
Yes, let's see. Oops. What is not connected? The microphone. Can you hear me now? Good. So let's check the other one as well. Do you hear me now?
Yes, but maybe from there. I can even hear myself actually slightly.
I'm not sure. I can go outside.
I didn't hear you. So that one is working and it can capture my voice as well. It's all of us.
Giray, can you mute us?
Okay, and then okay.
No, it's not sure.
So
It's
I don't
not?
see the slides going up now. I don't see them before.
So they share the entire screen?
Now
No, I see it partially.
Yes,
It's
yes, it's too big for some reason.
I think I know. Change the display. Change the display format.
Change the what?
can
Yeah.
Display. Is it because we changed the? Good. This is not. Maybe this is not the one we want. Maybe that was the issue. Yeah. Yeah, I don't know why it's like it's not. Okay.
Is it good for you?
Yeah. Okay, thanks a lot,
This view
Mayank.
is good?
Don't care. No, it's fine.
Can I have the mic?
Yes.
Thank you. Okay, welcome back. Now we're gonna continue with. You cannot hear me.
It's actually some weird noise.
Is someone?
Snoring.
Someone is snoring.
But it worked before. We didn't change anything.
Everyone should be mute, I guess. On
Yeah, it's only the Safari. I can't hear anything.
maybe this one is. Can you check?
Correcting the audio settings, like
Yes.
is this the correct one?
This is fine.
Can we pay it again?
Can you hear us now?
No. It's completely off now. Nobody's snoring.
No, but when we talk, this is changing, like the mic here.
Yes.
Maybe I can. Speak now.
Yes, can you hear me now? You can hear.
Yes, I can hear now.
Okay.
Sorry.
Perfect. Okay, welcome back, everyone. Now we're going to continue with the SaLWo workshop today. For the next talk, Konstantina is going to discuss her work named Mars. Konstantina received her PhD degree in electrical and computer engineering in 2023 at National Technical University of Athens. She is currently a postdoc at Safari Research Lab at ETH Zurich. Her research interests lie in the field of computer systems and architecture, heterogeneous computing, and hardware acceleration. Her research has focused on hardware-software co-design, efficient high-level synthesis optimization, and design space exploration, targeting mainly genome analysis applications. Thank you so much, Konstantina, and stage yours.
Thanks a lot, Mohammad, for the introduction. I hope everyone can hear me. So I'm going to continue down the line that Nika started before and present to you one of our latest works that couples genomics with storage processing. I'm going to present Mars, which is the first processing in storage system that performs acceleration of raw signal genome analysis using processing in memory techniques. Okay, I guess the introduction has been made. So this is a brief outline of my talk today. First, I'm going to go through some background information in genomics. Then I'm going to talk you through the motivation and goal of this work. Then I'm going to present the key mechanism and architecture of Mars. And finally, we will move on to evaluating the system and then doing some conclusions. But first, let's start with an executive summary of this work. So we're going to talk about the raw signal genome analysis, which is a fast evolving field in genomics. Raw signal genome analysis is currently struggling to keep up with increasing real-time requirements of genomic application, as well as the high throughput generation of data from sequencing technologies. Therefore, there is a huge need for accelerating raw signal genome analysis. When we do that, however, we notice that I/O data movement becomes now the most prominent and dominant overhead. The goal, therefore, is to design a high-performance energy-efficient system for raw signal genome analysis that addresses both the I/O data movement as well as the computational bottleneck. So the key idea in this work is to design an in-storage processing system for raw signal genome analysis that addresses the data movement, but also exploits the parallelization capabilities within the SSD to accelerate the computational bottlenecks. So we achieve that through Mars, which is the first in-storage processing system for raw signal genome analysis. It is the result of a co-design between targeted software modifications and some dedicated hardware components that accelerate the steps of raw signal genome analysis by leveraging processing in memory within the storage. We have very much encouraging results. Mars manages to improve performance and reduce energy consumption over state-of-the-art works that are implemented either in software or hardware. So now let's start with some brief, maybe refreshment on some genome sequence analysis facts. So genome sequence analysis focuses on the study of genome in order to understand the genetic variation of species and evolution. And studying the genome has led to some groundbreaking advances and the arisal of some very interesting applications, such as doing evolutionary biology, outbreak tracing, as well as personalized medicine. So these applications, genome analysis application, usually starts with two steps. I think part of it was also covered by Nika. So we have the sequencing and the mapping steps. During sequencing, we have some dedicated devices, which are called sequencers, and they receive as input some DNA sample. And through some processing, they manage to generate from it some small DNA fragments. These are usually initially raw signals. Then we have the mapping step. In this mapping step, we want to align those small signals generated by the sequencing machines to a reference genome of an organism. During this mapping, what we get is potential positions on the reference genome where these small fragments of DNA belong to. The goal is usually to reconstruct the genome. Now, typically after the sequencing is done, we have a step that's called base calling. Base calling transforms the raw signals that are generated by the sequencers into DNA bases, these ACGTs that you all must have heard of. This, however, is done through deep neural networks, which makes it a very much computationally costly as well as energy-hungry procedure. The advantage, of course, is that it creates, it reduces the noise and it generates very accurate input data to continue with the downstream analysis. Due to the computational, however, overheads that these have, there is a novel approach that has been targeted lately, and this is using and mapping raw signals immediately to the reference genome without using the base calling at all. This way, we manage to have some efficient analysis with better scalability and even portability. And we have the added advantage of working with raw signals that contain richer information than bases and can potentially even open the road to have some more meaningful analysis. So this work focuses on raw signal genome analysis, which is this novel approach that directly works on raw electrical signals. It manages to exploit the high throughput generation of data from modern sequencing technologies and can even enable and keep up with the real-time requirements of genome applications. Now let's take a high-level overview of raw signal genome analysis in order to understand further down the presentation exactly what we accelerate and how we implement it in storage. So we have two main steps for raw signal genome analysis read mapping. First of all, we have the indexing part. This happens offline. For the reference genome, usually it's stored as bases. We have to convert it to the domain of raw signals, and we segment it into small events, which are small segments of the original DNA, and store it through a hashing function, a hash table that allows us to do some very fast lookups of mapping positions later on. The second part that is happening online is the mapping. So during mapping, we have the raw signals that are coming for a sequencer, and we need to look them up into the genome to find the mapping positions and be able to reconstruct it. So let's take a deeper look into the mapping step to understand exactly what is happening. Initially, we have a raw signal. This is a query sequence. The first step within the mapping is the event detection. During the event detection, we segment the original signal into events, which is like discrete signals and discrete parts of the original sequence. Next, we move on to the seeding step. For the seeding step, we compress multiple of these events into hash values through the hashing function that we have chosen. And then we do some queries to the hash table that has been generated in the previous indexing step offline. So this query returns potential matches and potential locations and positions in the reference genome where these events might map. The output of this querying mechanism, which are these matches, are their input into the chaining step, which is based on some sorting and dynamic programming-based operations that have the goal of group together the matches that can form contiguous and collinear parts of the genome and then form a good estimation of the final alignment. So now we are ready to move on with our motivation. So we have mentioned so far that sequencing throughput of modern sequencers is growing rapidly and is expected to grow even further. And it is to the point that it can generate like 100,000 signal samples per second. Therefore, raw signal genome analysis struggles to keep up with this pace of generating data. Furthermore, it's even harder to keep up with real-time requirements of execution. Therefore, we need to look into accelerating raw signal genome analysis. In order to do that, we should identify and study our application to find the key bottlenecks. So here we are presenting a breakdown of the raw signal genome analysis pipeline for read mapping by using 5 different data sets from D1 to D5. These are different species. It goes from smallest to the largest one. And what we can see through this breakdown is that the chaining and the seeding part are consistently always dominating the runtime. But also we can see that depending on the data set, event detection and input-output overheads might also have an important impact on the overall runtime. So then we're going to do a further model analysis to identify what is the role of the data movement overheads when we actually accelerate the computational bottlenecks. So for that purpose, here we perform a model where we have accelerated these most computationally intensive parts of seeding and chaining by leveraging state-of-the-art accelerators that exist right now. And we can see that the more aggressive our acceleration is and the more effective the accelerator is, it looks like the I/O data movement becomes actually the dominant contributor to the overall execution time. So therefore, I/O data movement from the SSD becomes the dominant overhead. Therefore, this makes us realize that in order to have an efficient overall acceleration of this pipeline, we're going to have to address both aspects, and therefore design a high-performance and energy-efficient system for raw signal genome analysis that addresses both I/O data movement as well as the computational overheads. We therefore propose Mars, and we go on to present exactly our key mechanism and architecture. So Mars is the first in-storage processing system for raw signal genome analysis. The key idea is to create an in-storage processing system that addresses these I/O data movement overheads, but also exploit and leverage the acceleration capabilities within the SSD to be able to minimize the execution time of the bottlenecks, of the computational bottlenecks of the workflow. Mars is implemented and designed through a co-design approach between targeted software modifications as well as a dedicated hardware components within the storage system. The scope of the targeted software modifications is to optimize raw signal genome analysis for efficient acceleration, for efficient execution within the storage. And it basically tailors the steps of RSGA to the SSD parallelization capabilities and architecture. For the dedicated hardware components, we're leveraging processing in memory techniques within the SSD to accelerate these computational overheads. And we're going to leverage both processing using memory as well as processing near memory by using the SSD internal DRAM. Now let's take a deeper look into the software modifications that we propose. The scope of these modifications is to reduce the computational workload as well as try to diminish the intermediate storage requirements when executing the end-to-end workflow. So we propose two different types of software modifications. The first one is adding filtering techniques in order to discard any candidates and seed hits that are unlikely to result in valid mappings later on. So we have two different types of filters integrated within the pipeline. The first one is frequency filters, and then the second one is vote-based filtering. Next, we also introduce some arithmetic conversion techniques. The goal of this is to convert the floating point values and operations to fixed point representations. Through this optimization, we achieve to reduce the memory footprint, but also the computational cost of performing computations with floating point numbers. Now, a major contribution of our work is that it's the first time that we actually apply these techniques to raw signal genome analysis, and therefore we have to tackle the challenge of preserving the accuracy in the presence of raw signal noise. In order to do that, we make sure to carefully place all the filtering techniques within the pipeline, so we have to identify the correct positions within the workflow that best serve the purpose of retaining the accuracy. And of course, fine-tune any filter parameters to maximize the accuracy. In order to make sure that this is a valid assumption, we establish that we actually do not hurt our accuracy by conducting an analysis. Our ground truth in this case is a typical pipeline that first performs base calling on the reads. The base calling is done using Dorado base caller. And then using these base called reads, we perform the read mapping through the Minimap2 aligner. Again, we use the 5 datasets that we also used before, from smaller to largest one. And as a comparison point, we're going to compare variants of the Mars workflow with state-of-the-art raw signal genome analysis pipeline, which is ROHAS-2. For our variants, we're going to first apply our filtering techniques to our SGA typical workflow, and then we're going to apply both our filtering and arithmetic conversion techniques. So this is a table that shows the result of the accuracy. We have the following observations. First of all, we can see that Mars variants improve the recall and F1 score over ROHS2. This shows that our filtering techniques are indeed effective in eliminating all ambiguous and redundant acquainted matches, and allows the pipeline to focus and work on more informative regions that are more likely to end up with a correct alignment. We can also see by comparing our two variants that when applying the fixed point arithmetic, we only have some minimal accuracy loss. And we achieve that by making sure that we perform the conversion at an earlier point in the workflow and ensure fixed point arithmetic has not significant impact on our results. So now that we have established that our new workflow with the software modifications is accurate, now let's move on to have an overview of the architecture and the system. So we have now an in-storage processing system for RSGA. We have two modes of operation. First, we have the conventional mode. In this case, the SSD performs standard SSD storage operations. During the accelerator mode, the SSD executes the full RSGA pipeline without having any host intervention. You can see here an overview of our architecture. Now we're going to see one by one the components. So first, we're going to focus on the components of Mars that are implemented within SSD controller. First, we have the Mars control unit. This is implemented as a finite state machine that orchestrates all pipeline execution, the control, and data flow. Next, we have the sorter and merger unit. The sorter unit performs parallel sorting of sequences using some dedicated logic, while the merger unit combines sorted subsequences into logger sorted ones. These two units are implemented using the processing near DRAM paradigm by operating on data that come from the internal SSD DRAM, and we implement one pair per flash controller. Now let's move on to the components that are implemented within the SSD internal DRAM. First, we have the arithmetic unit. This is dedicated to performing all arithmetic and logical operations that happen across all steps for RSGA. It also implements processing near DRAM paradigm, and it is based on a design of state-of-the-art fulcrum architecture that leverages the DRAM subarray proximity to achieve low latency parallel arithmetic operations. Here we implement one arithmetic unit per two subarrays. Next, let's go to the querying unit. This is implemented again within the internal DRAM of the SSD. This is a dedicated unit that performs efficient in-memory hash table lookups for the seeding part of our workflow. This is done processing using DRAM. It is based on the Pluto architecture that leverages DRAM row activation for massively parallel hash table lookup operations. In this case, we have one querying unit per subarray. So once we've seen all our individual computing units, let's take a look of how we implement the entire workflow. First, we need to break down our workflow into fine-grained tasks that actually are compatible with all the functional units we have so far established. So basically, we have to break them down into arithmetic, querying, and sorting operations. Once we do that, we then implement Mars as a pipeline of these tasks. So this is a predefined and fixed pipeline where each task must be mapped to the dedicated compute unit. For example, whenever we encounter multiplications, we have to map them to arithmetic unit. When we have some sorting, we have to do it with the sorting unit. Now, the Mars control unit manages to encode this pipeline into a finite state machine. It defines a fixed execution sequence. However, it doesn't always have the exactly same execution sequence in the sense that some steps might not be required depending on our input data. So the data dynamically trigger the tasks that are going to be executed. Now that we've shown a high-level overview of our architecture, let's go to see a step-by-step explanation of how the data and control flows within our architecture. So first, our raw input signals, which have been stored in flash memory, are transferred to the SSD internal DRAM to perform the event detection step on the arithmetic unit. Next, we go on to the seeding part of the workflow. Seeding has multiple steps within it. So first, we're going to leverage the arithmetic unit in order to create the hash values and also perform the filtering. Now, the next part within the seeding is the hash table querying. Again, this happens in the internal DRAM, but now we have to leverage our querying unit by using the person using DRAM technique. Then we have to move on to the chaining part. The chaining initially needs to be done with the sorter and merger unit, but first we're going to create some batches of sequences to send them in batches to the SSD controller. Therefore, this happens initially in the arithmetic unit. Once the batches have been created, we then send these unsorted sequences to the sorter and merger units. Once the sorter and merger unit operate on the sequences, we return back to the DRAM the sorted sequences for the remaining part of the chaining, which is based on dynamic programming techniques and is done on the arithmetic unit. So more details on this mechanism of the individual components as well as the system integration can be found in our paper. So you're welcome to check it out online and come back to us with questions if you have. So now we can move on to the evaluation section. So to evaluate our design, we compare it against 4 systems and perform both performance and energy analysis. The first system is a conventional pipeline that performs base calling and read mapping. The base calling is happening with a GPU-based base caller that's called Dorado. And the read mapping is done with Minimap2 aligner on a CPU. Next, we have a hardware-based and an NVM-based hardware-accelerated pipeline for base calling and read mapping, which is GenPip. And next, we move on to comparing our design with a state-of-the-art CPU-based RSGA pipeline, which is RoHS2. And then, of course, we also want to evaluate only the software modifications to the RSGA workflow that we perform. So we also have a variant of Mars that's called Mars CPU. It's executed on the CPU and only has the filtering and the quantization. Now, let's see the experimental setup. So for all the CPU-based pipelines, we execute them on a state-of-the-art server that has 2 AMD CPUs with 64 physical cores, 1 terabyte of DDR4 DRAM. And whenever we have to execute something on the GPU, we use an NVIDIA RTX A6000 GPU. Regarding our SSD configurations, we have an SSD with 8 channels, with each one having 8 flash chips and PCIe 4 interface. And it's equipped with 4 gigabytes of DDR4 DRAM. For the accelerators that we create and all the simulators we use the Synopsys design compiler for the accelerators, and we use MQCM simulator to simulate and emulate all SSD internal operations. And lastly, CACT7 for simulating and creating the all functionality within the DRAM, the internal SSD DRAM. Now let's take a look at our results. We can see here that Mars manages to outperform all other baselines across all other data sets. It is very interesting to notice that it manages to outperform GenPip, which adopts processing memory acceleration outside the storage. So we conclude that the fundamental reason that this happens is that Mars manages to actually solve the data movement overhead that GenPip does not manage to tackle. And also we can see that even our version and variant that only includes software modifications manages to provide the speed up of 1.7 times over the state-of-the-art CPU-based pipeline for raw signal genome analysis, showing that even our software modifications are effective in reducing the computational workload. We have a similar encouraging results for our energy evaluation. We can see that Mars manages to reduce energy consumption over all other baselines across all data sets. And we can identify that the reason for this energy reduction is that we reduce both the execution time as well as diminish the IO data movement overheads. So let's now conclude this description of Mars. So Mars is the first storage processing system for end-to-end raw signal genome analysis that's enabled through software improvements as well as a hardware system that's implemented inside the storage system. Mars manages to preserve high accuracy that is on par with base calling based pipelines, and even manages to improve the F1 score over state-of-the-art RSGA pipeline. It manages to improve performance over state-of-the-art software-based base calling with mapping pipelines, hardware-accelerated base calling with mapping pipelines, as well as software-based state-of-the-art RSGA pipelines. Similarly, it achieves impressive results in reducing the energy consumption of respective pipelines. So this concludes the presentation. Thank you very much for listening and paying attention. So I'm happy to take any questions.
Or Konstantina can repeat the question.
Accurate base calling to detect this, the nucleotides fully accurately. Would there still be benefits from the signal analysis?
Sure. So the question is that if base calling achieves perfect accuracy, if raw signal genome analysis would still be meaningful. So the answer is yes, because what RSGA does is mainly address right now the computational overhead of base calling. So we don't want to replace base calling because it doesn't perform good in terms of accuracy. I think the accuracy achievement, let's say, of base calling is good, but we're trying to look at a lot of ways to diminish the computational workload, and because it really relies on the deep learning techniques, which is very energy consuming and time consuming. At the same time, we can see that raw signal genome analysis allows us to work with raw signals that might indeed include some more rich information that we can then harp on and create new pipelines that can extract more results. But I don't think that it can necessarily replace it completely. Thank you, Nick.
Questions?
Sure.
Maybe you can.
Or I can. We're really close. You can just speak here.
I see that like it is heavily using the SSD internal DRAMs for processing using DRAM and both processing near DRAM instead of like just typical like logic accelerators. And I wonder, you designed this because basically using DRAMs are free, or was there another like reason why you chose to use processing using a near DRAM technologies?
So thank you for your question. So we have not included this in the presentation, but you can find it in the paper that we actually did an ablation study where we have created different ways of performing these computations in different parts within the SSD, or potentially even we have explored architectures like Smart SSD to implement these logic units. And we saw that this configuration actually gives us the best trade-off between energy and performance.
Thank you.
Thank you for your question.
Can I ask more?
Of course.
I know I'm in Zoom. Yes. So if we in the future. It's okay.
I can hear you.
Okay. So if in the future we develop new heuristics to handle raw signal analysis, given that it's an emerging field, can you elaborate what parts of Mars can be still reused? Meaning if you have, let's say, so we have several tools right now, right? For example, one of them being rawhash and rawhash2. So if you have rawhash3 in the future, or any other tool, any other pipeline which have new heuristics, what parts of Mars do you envision still would be useful as to perform like key primitives? meaning how much of the design is based on a specific pipeline versus like overall general raw signal analysis?
Okay, thanks, Nika. So I think that most of the operations that Mars right now accelerates and implements will potentially remain, especially the parts that perform, for example, the seeding or the chaining. I don't think these are expected to change. But as the pipeline evolves, we could be able to add more steps or explore different filtering techniques. So I think that parts of Mars pipeline can definitely be repurposed and integrated in similar pipelines for sure, and then potentially expanded. Yeah. Thank you, Nika.
Can you hear me? Okay.
Yes.
So I have a general question, like in the application itself, how frequent?
Is this so? But this doesn't, is muted. Okay, I muted it.
Hello. Okay. To come close now. So basically in this applications, when you do the sorting step, and so do you need to basically store that data back again so that you can perform the next steps? Where do you basically store that data? And maybe a broader question is how like frequently there are updates, so you have to change your data basically.
Mm-hmm. So I don't remember the exact number of how frequent this is, but I know I cannot be heard.
No, maybe you're.
I can hear you.
No, I'm unmuted. Yeah, I can check it. So in most cases, at least in this scenario, the sequences are not long enough that they don't fit. So basically, we transfer them once and we manage to sort them and then transfer them back to the SSD internal DRAM once. However, there are some minority of cases, which I think would even be less than 5%, that it's not the buffers are not enough. So in that case, we indeed have to store some intermediate data in the internal DRAM and then do some back and forth until we manage to sort the entire thing. But this has been accounted for, and we still overall have better execution times.
So the communication is between your DRAM and the unit?
Yes.
And then once we're done, it's fine.
Exactly. Only once we write to the flash the results, yes. Thank you. Sure.
Yeah, so my question is,
Yeah.
Okay, thank you. So we do we still need to read the data from the storage system?
You need to speak in this.
Speak. Yeah. So can you hear me now? Okay. Yeah. So do we still need to access the data within the storage system? And so my question is, the power of accessing the data within the storage may be dominating the overall system. Do you understand?
Not entirely. So we do access our raw signals, and the hash table it's stored in the flash, and we read it from there. And then we only once write back to it.
Yeah. So I mean, so we need to access, and we have some near storage processing, right?
Mm-hmm.
So, but we still need to access the data and read the data, read the data to the near memory processing unit. Is that true?
But right now we're doing the processing in memory, targeting the SSD internal DRAM. So we don't have to take them outside the storage and move them to an external memory. This is what you're asking?
Yeah, so
It's all
so
inside the storage. So everything is close by right now.
okay, so we do not have the access to the storage. We just,
Just everything
allocate.
happens within the storage. We don't have to transfer outside at all.
Okay.
Except for like the initial writing of data, which happens either way, right?
Yeah, okay. Thank you.
Okay, then. Thank you very much for your questions. And I guess we can move on. So the schedule has been changed. So do we move on with the next presentation now? Okay, good. Let me then start my presentation. So it's Flash Cosmos.
We can even give like a 5-minute break if needed.
Do you need a break?
Okay.
Okay, so then I download the slides. Oh no. Yeah, I thought I did though. So Mohammad, do you need this to introduce? Thanks. Thank you.
I see the slides, but yeah, there are a lot of things over there. Could you get rid of them? And there's also this not hearing anything there. Turn up volume, yeah. Okay.
So everything is okay now?
Perfect.
Okay, so we move on to the next talk. Rakesh Nadig. He's a fourth-year PhD student in the Software Research Group at ETH Zurich, advised by Professor Mutlu. His main research areas are heterogeneous memory and storage systems, near data processing, and machine learning in computer architecture. Before joining Safari, Rakesh worked as a senior staff engineer at Samsung Semiconductor Research Labs in Bangalore, India. Rakesh has obtained a master's degree in electrical and computer engineering from the University of California at Irvine. Thanks a lot, Rakesh, for giving this talk. Stage yours.
Thanks, Mohammad. Okay, so yeah, thanks for the opportunity to present this work. So I'll be presenting our one of the first works in the direction of in-flash processing, and this work is called Flash Cosmos, in-flash bulk bitwise operations via inherent computation capability and of NAND flash memory. And this work was published at Micro 2022. So I'll jump to the executive summary. So bulk bitwise operations like bitwise and or are widely used in many important data intensive applications like databases, cryptography, image processing. The problem that we tried to solve in this work is that we looked at the performance and energy efficiency of how these operations are being performed in traditional systems. And the data movement bottleneck between the storage and the compute units remains the key bottleneck to perform these computations. We also looked at in-storage processing techniques, where we perform computations within the storage device, and we still see the same problem. If we look at in-flash processing works, like there are prior works which propose bitwise operations, bulk bitwise operations, and these works have a problem of are limited by the serial data sensing, which means that they have to read each and every operand to perform these computations. The second or even more critical problem is that these techniques, these prior IFP techniques, are limited by low reliability because they cannot leverage these error mitigation techniques in SSDs or in NAND flash memory, like ECC and data randomization. So these are some of the problems that we try to solve in this work. And our goal is to improve performance, energy efficiency, and reliability of bulk bitwise operations. So we propose Flash Cosmos, which is flash computation with one-shot multi-operand sensing. And this in this work, we propose two key contributions. So the first one is called multi-word line sensing, which enables multi-operand bulk bitwise operations with a single sensing operation. So unlike the prior work, we don't have to read the operands in a serial manner. Now, we also, in order to improve the reliability, we also propose enhanced SLC mode programming, which increases the voltage margin between the states in the SLC cell, and this also provides higher reliability for in-flash computation. Now, some key results from this work. So we evaluate Flash Cosmos on 160 real 3D NAND flash chips. And we also perform a system level evaluation using state-of-the-art SSD simulator MQSIM. So Flash Cosmos improves the performance and energy efficiency by 3.5 times and 3.3 times over the state-of-the-art IFP technique, and it also provides high reliability during computation. So this is the outline of my talk. I'll start with some motivation, and this work can also provide some background for NAND flash memory and going forward in flash processing works. So I'll start with motivation. So bulk bitwise operations are seen widely in many critical applications like databases, cryptography, set operations, genome analysis, and so on. As I mentioned, data movement remains a key bottleneck between the compute units and the storage, where typically all these large data sets are stored, and this significantly affects the performance and energy efficiency of these operations. Now, let's look at how these traditional systems or some of the upcoming systems are performing these computations. So we first look at conventional systems where all the computation is performed in the host instead of where the data resides. So here we look at a very high level overview of the memory hierarchy. We have the host processor, the main memory, and the storage, and large amounts of data are read from the storage to the host to perform the computation and then return back to the storage. So now the main bottleneck here is that the external I/O bandwidth of the storage device or SSDs, which are typically around 8 gigabytes per second if you consider PCIe Gen 4. This is quite limited, and you can't move large amounts of data in parallel. So this is the main bottleneck with traditional systems if all the data sets are stored in the SSDs. Now, there are near data processing techniques for bulk bitwise operations at different levels of the memory hierarchy. We have at cache level, we have compute cache, ambit for the DRAM, base main memory, NVM, we have peanut tubo, and we have biscuit and parabit for in-flash. Now, our focus is mainly on these two areas because these data sets are quite large and they don't fit into the main memory. So we looked at in-storage processing, and in-storage processing is typically a computation paradigm where you perform computations inside the SSD using the embedded cores or you can add an FPGA within the SSD to perform these computations. This certainly reduces data movement compared to outside storage processing because it only transfers the result out of the SSD. But there is still a bottleneck that we'll see now. So again, looking at the traditional view of the memory hierarchy, we also show what is inside the SSD in this figure. So again, large amounts of data are being read from the NAND flash chips to the in-storage computation unit, which is the SSD controller or FPGA or embedded cores. And the computation is performed in these units. Now then you transfer the result, which is much smaller in let's say much reduced, outside the SSD. The bottleneck in this paradigm is the flash channels, which are which have low bandwidth, and in a work that we present later in the workshop, we also show that there are things like path conflicts which affect the flash channel. So we are limited by the bandwidth of the flash channels in this case. So so then we move the computation more closer to the data, which is basically where we want to perform computations in the flash chips. So this is in flash processing. What we do is, or in the prior works, what they do is basically they read the data in a serial manner. So here the computation is already being performed in the flash chips, and you move the data across the memory hierarchy, and the data sensing is the key bottleneck. So we look at what data sensing bottleneck is in the next slides. So in the state-of-the-art IFP technique, which is parabit, they perform bulk bitwise operations by controlling the latching circuit of the page buffer. So the latching circuit typically has multiple transistors and latches, and you control the transistors to at different points to get the bulk bitwise operations performed. So if we look at a slightly magnified view of the flash chip, you have the page buffer, and you have multiple word lines where the operands are stored. So you have the operands, and to perform these computations, you need to basically read the data serially to the page buffer, and the computations are and you end up getting the result of a bitwise AND in this case. So you have, if you have to perform let's say a bitwise AND operation on 100 word lines, then you need to do everything serially. So that is a very costly operation, because each data sensing operation or each read operation is very expensive, and it's in the order of microseconds. So serial data sensing is a bottleneck in the in-flash processing techniques. Now, the second problem that we looked at is the reliability issues in IFP, because we cannot leverage the traditional mitigation techniques to handle errors in SSDs, which is the data randomization and the ECC that is being used. So these components are in the flash controller, and we need to move a large amount of data through the flash channels to the flash controller and the basically the scrambler and the ECC engine to perform randomization. And we cannot afford this, because then the whole purpose of performing reducing data movement is not achieved. So basically what we do is in these prior techniques, they basically depend on the applications to be error tolerant. And so if there are errors in the flash pages or in the operands, when you are performing data sensing, they tend to get accumulated in the result, and basically can also get compounded. So the whole idea of doing computations near the data means that in this prior work, the applications have to be highly error tolerant. So our goal is to address the bottleneck of state-of-the-art IFP techniques, which is serial sensing of operands, and make IFP more reliable by providing accurate computation results. So our proposal is Flash Cosmos, which enables computation on multiple operands using a single sensing operation, which means that we perform one-shot sensing of all the operands, and we get the result in the page buffer. And it also provides high reliability during in-flash computation. So we'll see how this is done. But before that, I'll provide some background, and please stop me if you have any questions at any point. So some basics on NAND flash memory. And so a flash cell stores data by adjusting the amount of charge in the cell So if you have a very charge with very low or a cell with very low charge, then it basically is an array state, is in the array state, and it stores the value 1. If it is in if it has high charge level, then it is a programmed cell and it stores the value 0. Now, if you activate the cell, the array cell operates as a resistor, and the programmed cell operates as an open switch. Now, if you take multiple such cells and then serially connect them, then it forms a NAND string, and you can see a typical NAND string here. The size of this NAND string depends on the number of cells that you connect serially, and this basically forms the number of pages in a block, which you will see later. So when you are reading a particular cell, the other cells are considered non-target cells, and they all operate as resistors regardless of the stored data. Now, the cell which we want to read either operates as a resistor or an open switch, depending on the charge level in the cell. So during the read operation, the bitline current flows through the NAND string, and if the cell operates as a resistor, then it flows through the NAND string, and the sense amplifier detects the bitline current, and it considers the read as or the operation as a value 1. And if the cell is let's say in the 0 stores a 0 and it operates as an open switch, then the bitline current is blocked, and it reads as 0 if the bitline current cannot flow. Now, so if you take multiple such bit lines and lay them out next to each other, we basically form a block, and the cells in the same level across different bit lines are connected to each other to form a word line. So basically this provides high bit level parallelism. If you access a single word line, you can control a large number of flash cells. And if you look at multiple such blocks which share the bit line, so what you can see is there is some analogy that you can kind of make out. So what you can see is, if you see the cells connected within a block, it is similar to how cells are connected or transistors are connected in a AND logic, where all the transistors are in series. And if you look at cells connected in different blocks, then you see then you can kind of make parallels with digital OR logic, where the transistors are in parallel. Now, using this insight, what we did with Flash Kosmos is we basically proposed something called multi-word line sensing, which enables bulk bitwise operations with a single sensing operation. We also we'll first look at intra-block MWS, which is the AND logic that I just showed. So with intra-block MWS, what we do is we simultaneously activate multiple word lines in the same block. And this results in a bitwise AND of the stored data in the word lines. So here you see a simple block with 4 word lines. And let's say you want to read or perform computations on the data in 2 operands. The other two word lines are basically considered as non-target cells, and they operate as resistors. So depending on the data stored in these cells, in the target cells, when you perform the read by activating multiple word lines, you basically depending on the state of the cell, if both cells are 0 in the NAND string, then the current won't flow and the result is 0. If you have both cells which store 1 or operate as resistors, then the current flows through the NAND string and the value is detected as 1, which means that this is similar to the AND operation that you of 2 operands. So this is about intra-block MWS. So this can be extended to multiple word lines within a block. We show that in the paper that we can do up to 48 word lines in the block. So again, if If none of one of the cells in the NAND string is an open switch, then we basically detect the value as 0. So intra-block enables bitwise AND of multiple pages in the same block via a single sensing operation. Now we look at inter-block MWS. So here again, we simultaneously activate multiple word lines in different blocks. So here you can see 2 blocks and 1 word line that is shown in each block. So if you perform the read operation and the bitline current flows through these NAND strings, because they are connected in parallel, even if you have one cell that is, let's say, in the resistor state, the current will still flow through the bitline through the NAND string, and it's detected by the sense amplifier. So if there is a 0 and a 1, it still detects as a 1. So this is similar to the OR logic. So only if there are 2 cells which basically have a 0 value, the sense amplifier detects the value as 0. So this is equivalent to the bitwise OR logic, and you can also in the paper we show that this can be extended to 4 blocks in parallel, or 4 different blocks, so we can read multiple word lines across 4 different blocks. So bitwise interblock MWS shows that we can perform bitwise OR of multiple pages in different blocks with a single sensing operation. We also support other bitwise operations in this work. So for bitwise NOT, we have the traditional NAND flash memory already supports something called the inverse read operation, where you can read the inverse form of the data, and this is already supported for copy back operations. We also support bitwise NAND and OR, and you can combine inverse read with bitwise AND and OR to achieve this. And bitwise XOR, which Andreas also mentioned, we have XOR gates in between latches, and we can leverage that to support these operations. So we have seen how we perform bitwise operations using a single sensing operation. Now we look at how we improve the reliability of these operations. So in traditional SLC mode programming, we have a sufficiently large gap between the voltage states. So we have the array state. If you take the voltage distribution of a word line, you have some cells in the array state, some in the programmed state. So the voltage margin is quite big. But in our work, we also show that without using randomization, we anyway can't use ECC because that's far away from the flash chips. Without using randomization, we still see a lot of errors if we have higher retention times and if the cell has aged. So basically what we do is, it's still highly error prone. So what we do is we increase the voltage margin between the erased and the programmed states. And with a wider voltage margin, we see that it improves the reliability and also gives 0 error bits in our operations. So we further increase the voltage margin by modifying the ISPP programming technique to add further steps in that programming sequence. And we also make the voltage, the programmed state, much thinner compared to the traditional SLC mode programming. So with a wider margin, even if some of the cells start leaking and then it moves towards the left, the voltage shifts. You basically still have a large headroom to kind of play with in terms of error-free reads. Now, so this is basically our technique to perform to improve the reliability. But as you can see, this is only in the SLC mode, and we need to come up with good techniques for making MLC and TLC mode more reliable also. So this technique can actually improve the reliability of prior in-flash processing techniques as well if they are using SLC mode for performing these computations. So we support new flash commands to enable flash Cosmos. So there are 3 commands that we support. One is the MWS command, Then we also support the ESP command for performing the programming. And then there is an XOR command. So the MWS command can be used for intra and interblock MWS. It also, we provide some flags to also set the inverse read operation. And we can also accumulate the results across multiple MWS operations. The ISCM flag that you can see here, it provides different flags to turn off, turn or on or off 4 features, which is inverse read, sensing latch initialization, cache latch initialization, and you can also move data across these latches. If you look at the MWS operation, what we do is we provide the address, and so this address basically has different blocks and the page bitmap. So the page bitmap is to specify which word lines in the page or in the block have to be sensed or activated. And we also provide 4 such address slots for interblock MWS commands. So you can perform OR operations across 4 blocks. Now the ESP command works like a regular program command that is used in traditional or commodity NAND flash SSDs. And we also provide the XOR command, which is used for the bitwise XOR operation between the sensing and the cache latches. Now, let's look at a very simple example of how we can perform bitwise operations in using Flash Cosmos. So here you can see this logic equation, which has multiple OR operations and AND operations. So what we do is we store these operands in different blocks. So A is stored in block 1, B is in block 2, and C and D are stored in block 3 and block 4. Now, if we look at the first part of the this equation, where we take this C1 plus C3 and D1 plus D2 plus D4, what we do is we first store the inverse of these operands in these blocks, because we want to perform more bitwise AND operations instead of bitwise OR operations. So what we do is we first enable the inverse read operation. We also initialize both these latches, the sensing and the cache latch, and we basically perform an MWS operation by providing the block and the page bitmap. So then for performing the first part of the logic equation, what we do is, after we perform this C and D, we don't want to, so this result is already there. So we don't want to reinitialize these latches where the data is already present. So we basically set the inverse read as 0, because we operate directly on the actual data. And then we also disable the initialization of these latches. So by disabling these latches, the result of these 2 MWS commands are accumulated in sensing and cache latches. So that's a simple operational example of how we can perform this, or how we can realize any equation in our bitwise set of bitwise operations using Flash Cosmos. So if I can move on to the evaluation, but if you have any questions, I'll be happy to take that. Okay, I'll move to the evaluation then. So in terms of evaluation, we first have a 2-step evaluation process where we first look at how Flash Cosmos fares in a real scenario. So we look at 160 real 3D NAND flash chips, and so we validate the feasibility, performance, and reliability of Flash Cosmos. We use real 3D NAND flash chips. We tested around more than 3.5 million word lines, and under worst case operating conditions, where we looked at 1 year retention time at 10,000 P cycles. We looked at worst case data patterns, and basically the result looks like this. So we can perform intra and interblock MWS operations without any changes to the commodity NAND flash chips. And both these operations can activate multiple word lines. In case of intra-block MWS, we can do 48 word lines. And in case of inter-block, we can do up to 4 word lines, because beyond 4, we see that the power budget of the SSD is, or it goes beyond the power budget. And the MWS operations can be done with a small increase in sensing latency, which is less than 10% of the read latency. And ESP significantly improves the reliability of these results. And we see that see 0-bit errors in our tested flash cells. Now we look at system wide evaluation, and we use some real world applications to perform these operations. So we use MQSIM for to model the performance of Flash Cosmos and the baselines. And we use 3 workloads. Bitmap indices is basically kind of a data structure that you use in databases. It performs bitwise AND of up to 1,000 operands. Image segmentation is a image processing kernel which performs bitwise AND of 3 operands, but these operands are quite large in size. K-clique star listing is basically looking at subgraphs within a graph data structure, and it performs bitwise OR of up to 32 operands. Now, the baselines that we look at are outside storage processing, which is how it host performs these computations, in storage processing, and parabit, which is the state of the art in flash processing mechanism. Now, in terms of performance and energy efficiency, we show the speed up over OSP in for performance, and we see that compared to parabit, we achieve around 3.5 times improvement in performance on average. In terms of energy efficiency, we see again normalized to OSP, we see the improvement of up to 3.3 times over parabit. And these improvements can only increase if we perform simultaneous sensing of more operands. So this is the link to the paper. I encourage everyone to read this and let us know if you have any comments or feedback. So in summary, Flash Cosmos is the first work to enable multi-operand bulk bitwise operations with a single sensing operation and with high reliability. It improves performance by 3.5 times over parabit and 3.3 energy efficiency by 3.3 times over parabit. And it comes with low cost and requires no changes to the flash cell arrays. So that's my talk of Flash Cosmos. Now I'll be happy to take questions. Thank you for your patience.
So I have a question, which is a bit naive. So as you know, these threshold voltages can shift in Flash in regular usage, right? And if we also consider the technology of scaling, this can really get like problematic to always like read the data in a reliable way. And once we also throw in some computation into this analog process, how does it affect the reliability overall? And do you think that we should take extra countermeasures going forward to enable this in a reliable way?
I'll show some characterization, and probably we can discuss more on this. So what we have shown here is SLC mode programming. So your question is perfectly valid that with technology node growing smaller and then more disturbances happening, if you take denser flash technologies like MLC or TLC, this technique is kind of not going to scale up so much. It works well for SLC mode because we already have a large gap, and we further increase the gap between the voltage states. If you take just the SLC mode, we still see that even with let's say more disturbances, and if you take technology node considerations also, we still see that the bit error rate is quite low with our technique because the gap is so large. But if you kind of use the same technique for MLC or TLC, it doesn't really scale up so much.
So if I remember the terminology, I guess if I remember, it was for MLC cells that you had something like read retry in normal usage, right? To make it more reliable. So can we resort to those methods to make Flash Cosmos work reliable in MLC as well?
So read retry is a common technique even for SLC. So if there are errors in the flash cells, then we perform read retry with different voltages to correct the data with the assistance of ECC engine. But in our case, we cannot do that because the thing is, we just by changing the voltage levels, if we can let's say reduce the number of error bits. But if we don't use the ECC, then it becomes a problem. So with MLC and TLC, we use read retry always with ECC as the correction engine. But if we can find an ideal voltage level just by read retry with these techniques also, it's going to make it better. But yeah, as I said, if you go to denser technologies, then you need ECC for that. So my simple answer is like it can work to some extent, but beyond that, you need ECC for correcting the data.
So we need to. So when we just read data, we can easily use ECC. But if we, like in Flash Cosmos case, if we do computation and then read the result of the computation, so then how will ECC work?
So
I guess we will need some other technique.
We cannot really use ECC at this point because then when we decode the data, then we don't have the same parity bits that we added for the operands because of the computation. So we really can't use ECC at this point, and that's something that we need to explore how we can kind of leverage in the future. So interestingly, there's a work that is coming up in Micro where they try to perform single error detection and correction within flash chips. But that's again an active research area.
Okay, thanks.
Yeah. Yes.
Without performing any computation, if we just use the enhanced SLC mode, then how good is it in terms of it as compared to these?
Can you please repeat the question?
Yeah. Can you hear me? So when we just want to read, but if we are using enhanced SLC over here, then how good is the performance of enhanced SLC as compared to ECC? Like, can we not use ECC at all because enhanced SLC is very good?
In the workloads that we used, we did not see any errors.
Okay.
Maybe I also have the results from the paper. Yeah. So here you can see the RBR when we kind of use TESP, and basically the errors are at 0 after a point. So this is, I think, in terms of timing. Yeah. So in this figure is quite confusing, but in any case, in our experiments we did not see any errors in using the TESP or the ESP programming technique.
Hi, yes. Yeah, I have one follow-up questions on regarding ESP. So yeah, basically for enhanced SSC programming, we need to spend longer time for doing that programming. And probably we are also consuming more write energy, right? And so that can affect some, I guess, energy consumption, but more importantly, I assume it can also affect the reliability of flash chip, because now you're, for that program arrays, you're spending more energy, and that affect the endurance of the flash, no?
So, I mean, we are not, I think for the arrays operation, we are still not, in our work, at least, we have not shown that we use a longer arrays operation or something like that. So as you say, the power consumption is definitely higher with ESP. In terms of reliability, again, it's something that we have not explored in our work, whether increasing the threshold voltage to a higher level can actually cause lower reliability is something that we have not looked at.
Okay, yeah, I agree. Also, when we do programming, or also when we do read, we need to apply VPass to other cells. And so now that we are doing programming for a longer time, so I assume that, you know, that weak programming effect can be actually more important here, right? Because we are spending more time. We are applying VPass for a longer time to other cells, and that could affect the reliability of other pages, no?
Yes, the read disturbance effect is going to be.
No, not read disturbance. I'm talking about actually write disturbance now. So essentially, when you apply, that's a weak programming, you know, issue that you need to apply VPass to other cells, right? That's the case for read and also for programming, right?
Yeah, you're right. So when we apply VPass to the rest of the word lines, then we see some because the VPass is quite higher compared to the threshold voltage, we see some weak programming effect, as you say. So your question was on endurance again.
Not really. I mean, it can also affect endurance, but it can affect the reliability of those pages. So when you want to read them for computation, you know, basically, you know, so you use ESP to have these, you know, the wider margins, but because of that weak programming effect, that could affect the, you know, that margin as well. So that you might actually see more errors, you know, after some time because of the weak programming effect.
So, so one thing I have to say here is that if you take this the normal SLC mode versus the ESP mode and the weak programming effect caused by the VPass. So with ESP mode, we are even moving closer to the VPass voltage compared to, let's say, an SLC mode. So the difference between the voltages in the ESP and the VPass is much lower compared to ESP, compared to SLC mode. So the effect of weak programming will not be as high as, let's say, compared to the regular SLC mode programming. So the reliability should be much better than, let's say, the traditional SLC mode programming because of the weak programming effect.
So yeah, I agree, but there are two things here. So I agree that the difference between the voltage are higher when you have ESP programming and that VPass, but that's a good thing. But also from the negative point, we are doing programming for a longer time. So we have these two effects, that's a trade-off we should see.
So that's the longer latency of the programming is something that we have not looked at, whether that has any reliability impact or not. Traditionally, as far as I know, longer or slower programming techniques or more number of steps can only increase the reliability because it makes the states or the lobes much narrower compared to the traditional SLC or traditional programming techniques.
No,
So
for that page that you're programming, I agree. I'm talking about neighboring pages, because you're applying VPass, and now you're applying VPass for a longer time.
Yeah.
So basically, I'm saying that here we have kind of trade-off. That from the positive point, the difference between VPass and programming voltage is much higher. So the problem of, as you said, the program interference might be lower, but then from the downside, you are applying VPass for a longer time, so which can affect the reliability of neighboring cells, essentially.
So this, I think, is something that we have not explored at all.
Yeah.
And this effect has to be understood more, because the more the more time you are programming, if it has any effects on the neighboring word lines or even, so we need to explore that more.
Thank you, Rakesh.
So just to answer Priyam's question, I'm kind of realizing that this is a factor of or a function of the traditional programming timing. So if you are actually doing more, if the ESP is, let's say, more slower, or the time taken for ESP is higher than the traditional programming mode, then the RBR is much lower. So if we if the TESP is much smaller, let's say same as TProg, but with higher states, then we see more errors in the cell.
But there is a limit to which you can shift that voltage margin.
Yes.
So because then you have power constraints and
exactly.
Are there any other limiting factors apart from these two?
So as far as I know, the read latency in SLC should not matter, but I guess the power constraints are there, and reliability is something that we have not fully explored in terms of other secondary effects of these programming techniques. Yeah.
Priyam, did you unmute or? Oh,
So I can probably repeat the question. So Priyam asked whether if we have any other, let's say, concerns because of doing high or programming using ESP for longer, and also the threshold voltage is increased. So that was the question, and the answer is that we have to explore the secondary effects of this programming technique, but at this point the power is higher and the time programming latency is higher. Yeah.
Yeah, please. Can you hear me?
Yes.
Okay. So I want to ask some questions on the read side, basically how we are doing the MWS operation. So when you say that we are actually restricted by only 4 blocks that we can actually do, and you say that there is a power constraints, can you elaborate a bit more, like what will happen if you go higher? Like, is it something that SSD does not allow you to do, or you will induce some other effects? What will happen actually?
So I mean, the simple answer is that we have a power budget for the SSD, and if we go beyond, let's say, this is again an empirical analysis that has been done using real flash chips. So if we go beyond, let's say, 4 word lines across different blocks, then it could have considerations in terms of thermal and power considerations, that it increases the overall power consumption of the SSD, and also the heat that is generated because of simultaneously reading more word lines can be higher. And beyond that, I mean, we have not explored much in this work on what could be the effects of like going beyond 4 word lines. Yeah, but again, there are techniques that SSDs use to throttle power increases or power spikes and thermal spikes, as we have discussed. Yeah, I think we need to see how like what is the maximum that we can go with this.
Okay. And second question is basically like if we just want to, let's say, replicate this thing in our commercial SSDs, is it directly available that we can perform an MWS command, and it's like we need to of course have some sort of system, but do we need to do some modifications to the peripheral circuitry to get this, to enable this sort of operations like MWS operation, or is it available in commercial SSDs that we can exploit?
No, you're right. So we need to change the peripheral circuitry to perform simultaneous activation of multiple word lines. So that's something which is not there in the commodity SSDs. So the reads happen in a sequential manner. So the command transmission happens from the flash controller to the flash chip in a sequence. So we need to see how we can send more commands from the flash controller to the flash chips, or like we propose, we can use the MWS command and then indicate how many word lines have to be activated simultaneously.
Yes, but this there is a evaluation methodology which says that it's evaluated on real systems.
So this
right?
is when we say real system, it's on an FPGA board with real flash chips. So the commodity flash chips don't require any changes, but we need to change the peripheral circuitry. In terms of the cell array, we don't have any changes.
So apart from cell array, the outside circuitry we can change to do this. Okay. Okay. And maybe one last question I will ask. So at the application level, when you have this set of operations and you perform bulk operations, you got the result in your latches. Then after that, like, can we do something? So to perform next set of operations, do we need to write back the results to the NAND flash basically?
So that's something that we have been exploring, right? So if we have to, since these latches are limited, like we have 3 latches that are provided for performing PLC programming, or we have 2 latches for MLC. There is no reason why we can't add more latches, but it also increases the area overhead. Now, if we can kind of move around the data intelligently within these latches and then perform as many operations as possible, that's the best approach. But at some point, we need to have some data in these latches to perform the next set of operations. So we have to write the result back to the word line or to the page, which actually increases the power consumption, reduces the lifetime, and so on. So it's again how we manage the data in these latches and try to reduce the writes.
So I have one more question, but it is more from the application point of view. So I know little about NAND flash structure at this point, and if I want to use IFP, then how good do I need to know the data layout in order to make sure that I can use my application? So the 3 examples that you have, workloads that you have tested out, for each of them, the data layout was completely different, or there is some sort of similarity which we can use to build a higher layer of abstraction which someone can use to program it.
So in all the 3 workloads, the data layout is quite similar in terms of how we and that is not driven from the application, but from the structure and from the operation that we support. So we need to have, if we are doing more AND operations, then we need to have data in the same block. if we need to perform OR operations, then we need to lay out across the blocks. So in this work, we actually support some interfaces at the system level, which ideally we should, if you use those interfaces, it should write the data to the flash pages at the start in the format that we have or that we need for the MWS operations. But again, this is only something that we are kind of scratching at surface right now, because we are not fully supporting all kinds of like data updates and so on. So if the application updates the data, then we have to move it to a new location, and we also need to support those the contiguity that we need for MWS operations there. So so this is something which we are actively looking at also, like how to lay out the data, how to provide more system support for the applications to easily manage data. That's a very we have done it in a limited way in this work, but we need to do more.
Okay. Yeah, thank you.
Okay.
Thanks a lot.
Thanks.
Okay, great. So I think now we have a lunch break, and
So it's like 11:58. According to schedule, we were gonna start at 1:15, but we don't have to be alive later, so we start at 1.
of course, yeah, let's be back at 1 p.m. and we will start with Mayank's presentation. It's correct, right? Thank you.
Mohammad, you can lock the door, right?
I can. Only senior people might have keys, but I think.
So usually it's a good idea to go for lunch and lock the door, or should we leave some people here? Or take no, just take all our
Can you
valuables with us as well. I don't know.
So are we? Yep. You on mute? Okay. Okay, welcome back. I hope everyone have had nice lunch. So for the first talk in the afternoon, we have Mayank. He's gonna discuss about his exciting work cipher match. But before that, let me introduce you, Mayank, very briefly. Mayank Kabra is the first year PhD student in Safari Research Group. His research interests are in advancing privacy enhancing technologies. And he is currently focusing on one of these technologies, which means homomorphic encryption. He's interested in developing novel algorithmic techniques and hardware-software co-design approaches to accelerate homomorphic encryption using upcoming paradigms like memory and storage-centric computing, and to make it practical for real-world applications. So thanks a lot, Mayank, and stage yours.
Thank you.
Okay. Hello, everyone. So let's get started with the presentation. So the paper title is Cipher Match, Accelerating Homomorphic Encryption-Based String Matching via Memory-Efficient Data Packing, which is an algorithm design, and in-flash processing, which is a hardware-software co-design. So this is the talk outline, and we'll briefly go into first about the bit more background on why exactly homomorphic encryption, and then we move on with the executive summary. So there are two types of string matching. As we are focusing on string matching, there are two types of string matching which are used in applications. One is exact string matching and one is approximate string matching. In this work, we are currently restricting our scope for exact string matching, and we'll get to know more about it. So exact string matching is used in many security critical applications, such as databases. For example, searching a query in a sensitive database, for example, financial databases, or in bioinformatics, for example, identifying similarities in DNA sequences. Now let's take a look at how exact string matching is actually done. So let's assume you have a user has a query, and there is a server, and in the server we have our database which is stored. Now in this database, we'll send the query, we'll perform the string matching, and we'll get to know the result where exactly we have a match. And then based on that match, we will send back the result. The result can be anything. It can be either a match, like whether you have a yes or no match. You can send back the document itself. There can be many things. However, if these whole computations are performed on plain text, it can lead to data leakage, because any attacker now can see what you are performing on computations, and they can see basically what's going on and what is your actual data is. Now it requires secure exact string matching. Now let's take a deeper look into what types of secure string matching are. So there are three types of secure string matching. One is private information retrieval. Sorry for that typo. And then another is symmetric searchable encryption, and third is homomorphic encryption. Now in these settings, we have a client and a server. Now let's take a look at very briefly what is one by one. In private information retrieval, the client has a query, the server has a database, but the thing is the server has the database in a plain text format. Now the goal of this specific, let's say, paradigm, it's just to make the client query not to be seen by anyone. They don't care about the database, it is publicly known, but the query of the client should not be known, and that's why we send an encrypted query, we get back the result. So there is a upside of this, that this technique is very performance efficient, because you just have only one encrypted component, that is query. The database is still in plain text, whereas you have unencrypted database. That is a downside. If you have an important data set, it's not a good technique to use. Now let's look into other part, symmetric searchable encryption. Now in this, we have the query on the client side, and the database is now encrypted onto the server, which is good. You send the encrypted query, you get back the result. Now the upside is that we have encrypted query and encrypted database, but the downside is that this technique leaks some search pattern. Why? Because this technique uses a deterministic encryption, which I'm not going into detail, but what does that mean is that if you send some query, encrypted query, the next time the server can figure out that, okay, this is the same query that has been received. And that's why this technique is a bit slower than the private information retrieval, but still you can find out because this uses a very simple symmetric key encryption or deterministic encryption. Now we have the third side, which is homomorphic encryption. Again, query an encrypted database. You send the encrypted query, get the result. Now in these scenarios, there are no leakage. No leakage in the sense that you cannot leak any sort of search patterns, because every time you send a query, this is going to be having some extra, let's say, randomization, so that the same query is different every time when you encrypt it. But it has its own overhead. It is very high. It has very high complexity. Now, this is the whole background on secure string matching works. And in this whole work, we are actually focusing on homomorphic encryption. So let's take a look at secure exact string matching now with same example. Now we will have an encrypted query. You will have encrypted query with some parameters. These are homomorphic encryption parameters. And instead of deterministic parameters, which was just S, the secret key, here you have two parameters to play with. Similarly, the server will have the encrypted database, which will again be with two parameters. You will perform homomorphic operations where you allow, so homomorphic operations, it allows users to compute on encrypted data without decrypting it. So you can perform any homomorphic or any operations homomorphically so that you can basically compute your values and then can send back the result. Now, in all our scenarios, we will assume that this left side is the client side, which is our user, and this right side is server. The client is trusted. Basically, whatever the queries it is sending, it is encrypted, and client is not leaking any of the security parameters like say secret key, some other noise parameters or encryption parameters. Whereas the server is semi-honest. What does semi-honest means? That server is curious but honest, which means that server is actually can see what is going on, but it can play around with the plain text, ciphertext values. But it is honest that it needs to follow the protocol, what is actually we have derived, the algorithm that we have written. It cannot deviate from that algorithm. Otherwise, it can return a very garbled result, which doesn't make sense. So algorithmic wise, it needs to follow that, but it is curious and it can get to know what exactly is going on, and can he retrieve something from the ciphertext, he will always try. And the goal of homomorphic encryption is not to leak anything from that ciphertext. So let's look at the approaches to this HE-based string matching. There are two approaches. One is in homomorphic encryption, you can compute it using Boolean operations. Other are using arithmetic operations. Boolean operations, basically what you do is, just like conventional, you have XOR and AND operation to calculate a string matching. Here you have homomorphic XOR and AND operation. Whereas on the arithmetic side, you need to use some arithmetic operations, and you use homomorphic multiplication and addition operations. Now let's see the trade-offs between these two approaches. Boolean approach has very high memory footprint. Why? Because they need to operate on individual bits of the data. So individual bits will be encrypted, and each, like the data set will be so huge because each bit encryption is going to be much larger, and you have a large data set. So it has high memory footprint. Whereas on the other side, arithmetic approaches, they support some sort of data packing techniques that you can take multiple bits and then encrypt it, which is, let's say, in the same size. So you can take larger set of bits and do encrypted, which is lower memory footprint as compared to the Boolean approaches. Now, the next is that Boolean approaches has high computation cost. Why? Because you have large number of HE operations that you need to perform, because you have large number of encrypted data. So you need to perform lot of homomorphic operations, even though if those homomorphic operations are a little less complicated as compared to complex as compared to arithmetic approach, but you need to perform a lot of them. On the other side, you have lower cost because you perform small number of HE operation or less number of HE operation. Now the upside of this Boolean approach is you have flexibility in terms of query sizes. Now there are more details about this in the paper, but I'm just going to briefly tell you that Boolean approaches can perform any length, any database string matching, because you can support flexible query sizes, just because you have unlimited number of computations that you can perform. On the other side, they support limited query sizes because after some point in the computations, after that you have to stop. You cannot perform computations because after that you cannot decrypt back the results. That's a downside of that arithmetic approach part. Now, overall, we see some good sides of arithmetic approach. Can we make it more better so that we can do something with arithmetic approach and can have a better algorithm with it? So that's why we'll focus more on arithmetic approach. And there is a more detailed analysis on these trade-off, and you can check out our paper. So there are prior works in both the approaches, arithmetic approach and Boolean approach. We'll focus on arithmetic approach now. Let's see the arithmetic approach. So assume you have a database. You will take multiple chunks of database. You will make a vector of that database. I'm using very simple terminology. Assume that you chunk down the database and you take multiple vectors of that. That vectors can be encrypted and it will contain some random values that you cannot basically reverse back. What is the plain text if the decryptor unit does not have the correct parameters to decrypt it? Now, let's see the trade-offs here. If you have one bit in the vector, that bit is going to convert into a larger size, for example, a 32-bit number. If you have 1024 elements in the vector, that will go into 2048 element vector. These are some of the things that homomorphic encryptions come with. When you perform homomorphic encryption, you need to pay this cost because the data size will go bigger. Now, if you see, if a conventional database size is 128 bytes, the encrypted database will be 8 kilobytes, which is 64 times increase. And I'm talking about one of the techniques. There are different parameters, different trade-offs. Other techniques use something else. One of the techniques use that. Now, once they encrypt it, they perform homomorphic multiplication and addition to get the result. So assume you have this encrypted database. You have your encrypted query, which client sends. You basically perform some homomorphic operations in them, which constitute some mixture of homomorphic multiplication and addition, and you get back the encrypted result. Now, based on that encrypted result, you will perform further operations to figure out, let's say, your string match, and then you will send back the results. So these are the very basic background on what goes on this homomorphic string matching, what are different techniques, and how can you do this. And in our case, we'll focus on exact string matching and arithmetic approaches for now on. Now, let's go into the executive summary of the paper. Now, with the background defined, secure exact string matching using homomorphic encryption, it lacks scalability due to performance bottlenecks in two key areas. First is that they use complex homomorphic multiplication. And I will come back to this, why it is like a bit complex by analyzing some prior works, because it has very high computation cost as compared to a conventional multiplication or other homomorphic operations. And there is a data movement bottleneck. Why? Because you have encrypted database. It gets bigger with homomorphic encryption. So it needs it, and it is stored in SSDs, the solid state drives in the, let's say, server. So you need to pay this data movement cost. Now, our goal is to develop an algorithm hardware co-design so that we can provide scalable, parallelizable, and efficient HE-based secure exact string matching. So the key idea of this paper is to use only homomorphic addition. So we eliminate homomorphic multiplication so that you don't have to pay that high cost. That is the algorithm contribution. And then we perform in-flash processing, which I guess we all are been discussing since morning, by exploiting the operational principles of NAND flash memory so that we can accelerate the secure exact string matching. With this, we propose CipherMatch, a new algorithm hardware co-design where that significantly improves the performance by using only homomorphic addition, which reduces high computation cost, optimized data packing scheme so that you can reduce the memory footprint, and also designing a new in-flash processing architecture so that you can reduce data movement. Some of the key results that CipherMatch algorithm running on a CPU is 42.9 times faster and 39.4 times energy savings than the best state-of-the-art existing algorithms, basically. This is on CPU. When we further enhance CipherMatch with IFP technique, we further get a speed up of 136.9 times and get an energy savings of 256.4 times over this CipherMatch software. So this is the whole executive summary. Now I will briefly move on into problem statement and our goal. So we were focusing on arithmetic approaches. So we analyzed one of the arithmetic approach, which is faster. There are some other problems, but at computational time, it is faster. The total execution time to perform the secure string matching, we observed that 98% of the total time is spent on homomorphic multiplication. This is because homomorphic multiplication is around 100 times slower than homomorphic addition in a CPU system. People have done studies on GPU system, A6 system. always homomorphic multiplication is worse than homomorphic addition because of the algorithm wise. Homomorphic multiplication is much more complicated to perform. Now, this gives us our key problem 1, that homomorphic multiplication limits the scalability of these HE-based string matching algorithms. Now, second, as databases are large and they are stored in SSDs, homomorphic encryption will further increase the database size. Now, you need to fetch back the data to perform some computations and different processing paradigms. Let's see them. In compute-centric system, you have to fetch the data from your storage to your CPU or a GPU system to perform computations. And you have a lot of constraints here that you are limited by the storage IO bandwidth or the memory bandwidth. There are other techniques like memory-centric systems where they perform computations in main memory, where you utilize the bulk, like the parallelism in the main memory, but you are still limited by the data transfer from this IO. Now, there is this external IO bandwidth of this storage system is the main bottleneck for this memory intensive system. And why memory intensive? Because you have databases and they are now homomorphically encrypted. There is third set where is storage centric system, which we all are talking about now. And you send the data from NAND flash chips to this in storage compute units. But still you have to take out the data and then move it there to this in storage compute units. Now, the limited internal bandwidth of these flash chip is now the new bottleneck. Now, this is something that we have to basically solve. Now, data movement is a major bottleneck for different processing paradigms and for reading large encrypted databases which are stored in SSDs. So there are prior works which reduces the data movement basically in flash processing, because that means that you can perform computations inside the flash chips itself. They show that makes sense because that's where the data resides. You can exploit the parallelism and then you can exploit the operational principles of NAND flash memory to perform computations. Now, this looks like a goal that, okay, we should do our computations there and we need to change our algorithm. So with that, our goal is to develop an in-flash processing based algorithm, hardware co-design system that can perform scalable, parallelizable, and efficient secure exact string matching. And it requires both the contribution from algorithm side and the hardware side. So let's move on to our key observation and our key idea, what we observe and why we can enable this very easily. Assume that you have a database. You can assume in any settings. Let's assume you have a database. This is a conventional way. If you have a query, you have a database. If you negate the query and send it, if you perform additions on that database, what you will see wherever the match has happened, you will see the output as string of all ones, because the query is negated. If it's exact same match, all additions, the addition will make all ones, and you will see a string of ones if the query matches. Now this, in conventional database, we need to perform only addition to get a string match. This is for exact string matching. This observation can be extended to perform secure exact string matching with only using homomorphic addition instead of addition, homomorphic addition. So let's see, we have a encrypted query, encrypted database. You have a query, you negate it, you encrypt it. Now this encrypted query is sent to there and perform homomorphic addition. You will see an encrypted ones. And if you find encrypted ones, that's where the query matches. Now, this is the key idea. This brings us to our key idea 1, that we can use only homomorphic addition to perform secure exact string matching. So exact is the keyword that we are performing exact string matching. The another observation is that when now we are using only homomorphic addition, it is very highly parallelizable. Why? Because homomorphic addition inherently means that you are performing polynomial addition. What does polynomial addition means? That it is element-wise addition. If you have element-wise addition, then it is highly parallelizable. You can parallelize it across SIMD basically. Now that means that we can exploit the inherent parallelism of NAND flash memory. It improves the performance of secure string matching and reduces the data movement. And that's our basically second key idea, that we use in flash processing to reduce the data movement and accelerate this algorithm that we will propose now for secure exact string matching. With this, we propose cipher match, an algorithm hardware co-design that improves the performance of HE-based secure exact string matching by reducing the memory footprint first, that we optimize the data packing scheme. Prior works, we observe that they have 64 times increase in memory footprint. We'll minimize that. We'll eliminate the costly homomorphic multiplication by designing this secure string matching algorithm using only homomorphic addition. And we reduce the data movement also by leveraging the massive bit level and array level parallelism of NAND flash by designing an in-flash processing architecture. Now let's go. So till now we have seen an in-flash processing architecture. Last talk was for bitwise operations. We need to take a step further and now introduce addition operations, and we will see that in the hardware. But before that, let's go into the high-level overview of how the cipher match system actually looks like from both algorithm, hardware, co-designing part. So assume you have a client-server the interface. You have the client. Client will have its database. Client will encrypt, efficiently pack this database so that you reduce the memory footprint after homomorphic encryption. And then you upload it to the server where the encrypted database is stored. Now you have your query. The client will have a query. Client will also efficiently pack the query so that it does not have very high memory footprint of the query itself, and then send this encrypted query. We perform homomorphic addition operation, which performs secure exact string matching. Now this is the whole algorithms part where we can perform basically we can get back the matches, and then to accelerate this, we need to perform string matching inside the storage system, or maybe inside the NAND flash chips itself, and that's where we accelerate the secure exact string matching. So let's see this all the steps can be divided into 3 key steps. First is to design a memory efficient data packing scheme. Second, to have a secure exact string matching algorithm, and third, to use in flash processing. Now let's delve deeper into the cipher match algorithm. Now, as we know, cipher match algorithm consists of the first 2 key steps basically, and let's look at them one by one, where we have to efficiently pack the query and database. So again, in the same scenario, we assume a query and a database. Let's take the database first. What we do is we take multiple chunks of data instead of as I just discussed. Previous works were taking only 1 bit and packing it into the vector. Now we take multiple bits and pack it into the vector. We encrypt it using some encryption parameters A1, E1, and then we encrypt it to make an encrypted database basically. So we encode the database by packing multiple bits into the single vector, which we call plain text vector. Now here we have 16 bits which are packed in 1024 elements. It becomes 32 bits with 2048 elements. These numbers are specific to only one scheme. There are different numbers which I'm not going into detail, but with this we can, at least for one homomorphic encryption set of parameters, the increase in encrypted database size is only 4 times. From 2 kilobytes, for example, the query to 8 kilobytes, whereas prior works were there which were doing 64 times. So we reduce the encrypted database size. Now we have a query. Now we first negate the query. We replicate the query across this multiple slots in the vector. We have same replicated query across the plain text vector. We encrypt it with a different set of parameters, E2 and E2. Now this is important to note. These parameters should be different. Otherwise, so for example, this is the first query that I'm encrypting. The second query should have different parameters. Otherwise, you will actually be able to come in the same searchable encryption thing where you will have the same ciphertext coming out of same query, which is not desirable. You need to have different ciphertext come out of even same query so that no one can even get anything from that ciphertext. So we encode the query by negating and replicating it into this plain text vector. And now we have these 2 things, encrypted database and encrypted negated query. So let's look at now the string matching algorithm. Yes.
So if you pack 16 bits for both the database and the query,
yes,
then what happens if the query is kind of not aligned with the database?
So this is so to answer this with the initial for example, we will have first in the query chunks that will be defined. For example, you can have let's say 16-bit query. If you have a 32-bit query, what you will do is you will break the query and have it into 2 slots of the vector. Now you will match those. Now these 2 slots will be able to match with your encrypted database. If you have an arbitrary number of queries, this is possible to do it, but at the runtime, you cannot dynamically switch between what type of query length you are doing. For example, I will be fixed with the database, how I have encrypted a database, and you can only have, let's say, length 7, length 8 type of queries, only like that. You need to re-encrypt the database so that you can support all other sort of query sizes, like let's say some other sort of query sizes also. Yes. Sorry. Yes.
The query can be of the same size, but what if it's the offset is not aligned?
What do you mean by offset?
The query that you are trying to, I mean, in the database, the string will be, let's say, starting at the 5th offset in the 16-bit chunk that you are using for encryption, right?
Mm-hmm.
And it will kind of overflow to the next chunk. But when you are kind of packing with 16 bits, will you be still able to compare both of them?
So you will be able to compare, right? Because we are having them in the plain text vector in the repeated format. So you will be able to basically compare it with all the possible, let's say the databases that you will have, right?
No, I guess my point is like if the query and the database should start at the same offset or at the same chunk.
So yes, if your database query is starting from here, the database is also starting from here. That's true, yes.
But what if it doesn't align at the same offset?
So, but that's why we have replicating it, right? So that you can match if there is any other match that somewhere else happened, that you will get to know,
but
right?
It's also at 16-bit granularity, right?
That's yes, it has to be 16-bit granularity.
Okay.
If you need to change the length basically of the query, you need to have a different, so you need to re-encrypt the database with a different set of, let's say, granularity.
Okay.
Yes.
Thanks.
Is the same limitation for previous operation?
So prior works actually try to look at, we make a case study here that exact string matching is actually important. Prior works actually look at even a broader picture. They try to look at approximate string matching. An approximate string matching needs to you need to calculate, let's say, some sort of Hamming distance, Euclidean distance. And that's why they require all you having homomorphic addition, homomorphic multiplication operations, basically. Whereas they also propose that you can use this for exact string matching, but that is not optimized for exact string matching. So that's why we propose homomorphic addition only to look at this. As far as knowledge from us, like the exact string matching was not explored by homomorphic addition only. There are broader scope where they need to perform approximate string matching, and that is basically there. Yep. Okay. Any other questions? Or maybe we can go in the end. Okay. So we have this query, and we have this encrypted database and encrypted query. Now we look at secure exact string matching. As we just discussed, the key idea is to perform homomorphic addition. We do addition, which is element-wise addition across all sort. And that's what basically we do. We need to perform element-wise addition. We get the result. Now this result, if we decrypt, now the saying is if we decrypt it, we'll find at some index, we'll find that, okay, there was a match, the decryption make it 1111. But you cannot decrypt it in the server because server is your semi-honest or malicious thing. So what you need to do, we need to find a match on this encrypted result. Now for that, what we do is we generate a match value on the client side, which is encryption of all 1111s. We encrypt it with that specific parameters. Now these parameters are important. They are actually made with database and the query. And then we make the encrypted match value with that parameters. Now, once we do that, we can actually compare these match values that the same value will actually exist. Now with this, now you will say that we will have actually the same value. How is this true? Now if we see that it depends on A1 and A2. Now A1 is actually for database, which we are not changing. A2 is for query. Now, with the next query, we will have A3 there. Next query, we'll have A4 there, and similarly E3 and E4 there. So this value is always going to change. And then we compare it and basically generate the result, which can be yes or no, or let's say the final index that we send back to the client. So to summarize, we have efficiently packed database using the memory efficient data packing scheme, negated and replicated query, and they send with encrypted match value. And then we perform string matching using only homomorphic addition operations. This is the whole algorithm side. Now we know that we can specify the case of exact string matching with only homomorphic addition. And with homomorphic addition, how do we accelerate it? That's what we will see with CipherMatch hardware, where we perform this secure exact string matching inside SSD using IFP. Now let's look a bit more detail into SSDs. I think people know about it, but I will briefly walk you through it. SSDs have NAND flash based SSDs have an SSD controller connected to a flash chips and an internal DRAM. The flash chip hierarchy is like this. You have multiple dies, and inside multiple dies you have multiple planes also, and then you will say multiple bit lines. Basically, you will have multiple word lines, multiple bit lines, and it's like a 2D array for you. Now in this 2D array, I think we discussed this already, that we contain a word lines and bit lines in a block, and you have multiple such blocks basically, and then we have an erase cell state as 1 and program cell state as 0, which is basically we have discussed already. And then there is a latching circuitry. Now this part I think we briefly discussed, but now we need to delve deeper into this. The latching circuitry contains a sensing latch and 3 data latches. For example, we are considering a 3 data latch system. There can be 4 data latches also, or 5 data latches also, as a different SSD can have. But let's take a look at 3 data latches. The prior works use this latching circuitry because this latching circuitry is some sort of analog latches. You can control the transistors in this analog latches so that you can perform bitwise operations. Now, prior work, I think Flash Cosmos compared with only does bitwise operation, and Flash Cosmos also does bitwise operation. But we need to extend it to support addition, element-wise addition. So the goal is homomorphic addition can be parallelized, and we can exploit the array level and bit level parallelism. So let's take a broader picture into the SSD, how the SSD will look like. You will have the NAND flash memory, which will contain the encrypted data. You need to generate the final index or the result basically. Now let's look at them one by one. For this one, we need to perform element-wise addition, we discussed, and that's where we propose our IFP architecture. So with this picture we had in our mind, we use bit serial addition because propagation across bit lines is actually very difficult and there is no circuitry which exists. So that's why we use bit serial addition to exploit the bitwise parallelism basically, and to avoid carry propagation also. So let's look at this now, how we will lay out the data and how we'll perform operations. So first you have this encrypted database. Encrypted database were values like bits. You will lay out the data vertically. So you will take the values and vertically lay out in this vertical fashion. In this 1 bit line, let's see what we perform in 1 bit line. We need to perform some sequence of operations. Now this is the latching circuitry, 1 sensing latch and 3 data latches. Let's a bit broader picture into the bit latching circuitry also. It looks like this. So I'm not going into detail, but what we have is it's connected with the NAND strings, and you have sensing latch and data latch, which is some kind of a latching circuitry and analog circuitry. This is taken from a prior work which already exists, and what we do is we play around with the transistor values so that we can basically control the bitwise operation. Now let's see how can we perform a bitwise and between 2 data A and B. Let's say they are stored in NAND flash. First we load the data. Data A comes into sensing latch. We transfer it to data latch. There is a circuitry which can transfer it to the data latch. Now we load the second data B into the sensing latch. Now both of them has data A, data B basically. So let's see the operations. If assume that data latch has all values 0, and we now need to control M7 and M8 transistor, which you can see here in the red. First, we pre-charge the bit line. Bit line is 1. We enable it. We enable the M8 transistor. If the data latch value is 0, this transistor will turn off because this contains a 0 value. There is no discharging path that will be there. So whatever the values will be there, because it is 1, this is basically going to pull this down everything and make it basically 0. So if you have inputs A as 0, any output B will be pulled down to 0. Similarly, if you have data as A1, what will happen is you will pre-charge the bit line. The bit line will actually get discharged from here and it will go to 0. Now with the 0, it will retain the value, which means that you will get the actual B value. Now that's basically a bitwise AND operation that we got. Similarly, we can do bitwise. Yes.
So I didn't quite get if these latches are your addition, or are they already there?
So this latch is already there in one of the prior works that we have used. They propose these transistors for a specifically different thing, that they try to control the thresholding voltages of the NAND flash. But we try to utilize it for this, let's say, digital operations that we can perform.
But they do not exist in the baseline flash design. Is that correct?
So so this part I cannot answer, because maybe it exists. This is one of the prior patents that we have seen, that they have this design. So this transistor may exist in some of the models.
So that's a very good point. So then I'll ask another question. Does the existence of these latches open up new opportunities for like privacy-oriented attacks? Like, do you also need to secure these latches somehow,
so
other than the encryption that you're doing?
So this can give you some, so this can cause a problem with data integrity, that if these are not reliable, that they will change the output of the results, right? That will not give you bitwise and all. But inherently, the privacy, basically, when you have encrypted query or encrypted database, they will still be in an encrypted form or either in a garbled form. So you cannot still figure out the database or the query from that. So the data confidentiality is still there, data integrity get lost, which is true, which homomorphic encryption from the first go it does not solve. That even if you have any bit flips also in the system, the data is lost basically for you. Yep. Okay, thank you.
I have one
yes
question. Like, you need to do like modular add, not addition.
Yes. So this part is actually, so as we are only doing addition, the modular operation is basically in your control. You can delay the modular operations till the end so that your client does that. Because these are modular add is basically commutative across your operations. So you can basically delay it till your final result.
You need to ensure that it does not overflow.
What do you mean it doesn't overflow?
I mean, if you're using like 32-bit.
Yeah, that's true. That's true. I agree. Yes, you need to be in those limits.
And in highly, it has a high chance that it does overflow. But on operations, when it comes to addition, you can just subtract it because your coefficients are going to be near the modulus.
Yes.
So can you
unmute? No, I think it is
okay. Yeah, so for modular additions, you can always subtract it because your coefficients are near to the modulus. So there is no reason. I mean, you can always delay that approach, but it's like offloading some computation to the client. Whereas if it is possible to subtract over here, you can just do that, and yeah, the client doesn't have to do anything.
I think that's kind of fair enough, but I do think that it should like incur some overhead, like still.
No, yeah, it will definitely incur some overhead, but if you don't want to, there's also the, yeah, I'm unmuted. There's also the possibility of, it depends on the word size that you're using for your coefficient. So if you are using larger word size of 64-bit, because you want to use a larger ciphertext, then offloading that modular computation will be very heavy because you will be accumulating a lot of data.
That's true.
So it's better to make the approach more scalable. I feel that we can just subtract it at every point.
That's true. But this part is a very good point. But this part is actually not there in the paper, and we have not studied after how many operations that we have overflow or different bits. it actually goes out of hand. So this is a good point. I think we should study this part.
Did you look at the different word sizes, or was it fixed for the?
We assumed it for the fixed word size of 32-bit size, and we assumed the parameters to be 27-bit encryption, basically.
Okay.
The 27-bit key value.
These are working on RNS systems, so there is no guarantee that even the raw value is small. You could probably have higher small values inside the 32-bit words. And if you consider that this is an RNS system, every word, I mean, like every limb should have different modular values.
No, but we will have to keep on accumulating every 32-bit limb. So the accumulation can be in thousands of bits, depending on how many limbs you have. Over here, the limb count will be very less because the polynomial degree is very small. Or maybe it's only one, but yeah, the RNS, I think RNS is orthogonal to the accumulation over here.
So I think like Priyam is saying that I guess we should explore this point. I think both of you are saying actually correct part, and I agree that this part is not there in the paper, and we should actually explore that after how much is our budget, that how many additions we can perform. So I agree with you. Okay.
Yeah, there is also one question on YouTube.
Okay.
So let me read it.
Wait, sorry, you will unmute, right?
Yeah, I mean, Rakesh asked them to elaborate more. Let me read the question. So the question is, how does the bitwise only latching limit reshape SSD controller NAND flash system design trade-offs? Like I think the question is about when you want to do this use latching those circuitry for doing bulk bitwise operations. How does that change the trade-offs for designing the storage in general? That for normal operations. But I think the answer is like we don't. So these are already there also.
The latching circuitry and like this whole circuitry is present there.
Yeah.
So this doesn't need to modify. The only modifications on the SSD side is that how do we control these transistors?
Yeah.
And that part is actually modifications to which commands you want to send, how will your SSD controller look like. Those sort of modifications we need to propose to control these things. Okay. You are unmuted.
One more question regarding the accumulation thing. So after each, at the end, when you delay the modular modular part to the client, so at each stage your data is being accumulated. So the computation that you have to perform for each element will also keep on increasing, right?
So the thing is that when in this case you are sending a query and the query has to perform only one homomorphic addition with your database, right?
Yes.
If you just tried across your query or across all ciphertext, you will basically be done and get the results and send them.
Yeah.
The case can become if you have coupled queries, multiple queries that you want to get, say, let's say, evaluate on and then perform matches, multiple matches, then it becomes a tricky which we don't evaluate.
Okay.
Okay, let's move on. So we can perform these similarly bitwise operations, other operations or operations. We saw that bitwise XOR is also available among the data latches. Now we have these primary units like XOR and OR and the data transfer between the data latches. We need to utilize them so that we can perform a bitwise addition. Now I will briefly go over how the bitwise addition is done, not in detail one by one, but maybe it will be easy to visualize. Again, going back to this bit line, how does it look like? It needs to perform a sequence of operations. This was our latching circuit. We send the query from the SSD controller to these latches. The latches basically perform a sequence of steps to calculate the sum and the carry bits. And it takes 6 steps for you, which involves data transfers, XOR, and operations. And then you will generate the sum. And then you will accumulate this bit and send the accumulated bit to the SSD controller. Now you have actually found out so you have done homomorphic addition here. And also basically you have done where exactly your match is found, because you will also send the encrypted 111 values also. And similarly, you will reduce your result, because if you just send all the result back, you don't solve the problem, right? Because you need to send like whatever the result is same as size as the database. So you need to send everything out, but this does not solve. So that's why we reduce the result further, so that you send only the accumulated bit. With that accumulated bit, you can basically get to know whether it's a match or not, and then you can generate that index basically. So basically we have done homomorphic addition and we can generate the final index. And this final index generation is something we do in the SSD controller course. And we have reduced the data movement by performing a major chunk into the NAND flash, only send the accumulated result or the reduced result back out to the SSD controller. So this was all about CipherMatch software and hardware. That's how we accelerated. Let's go into a bit quickly on how evaluation results look like. We implement first a real system, our algorithm, using we evaluate our software-based CipherMatch implementation by modifying the Microsoft Seal library on this specific system. And the baselines are that we implement an arithmetic approach, state-of-the-art arithmetic approach, which is the fastest, using Seal. And we implement a Boolean approach, which is one of the other comparison point, using state-of-the-art Boolean approach, which is they use TFHE scheme, basically, TFHE Rust library. And the workloads that we swept across is various query sizes for encrypted database and various encrypted database sizes for a query for 1,000 queries. And this involves like circularly shifted queries for you. Like you will have all possible sort of combinations that you can match in if the query queue exists, you will circularly rotate to for all possible queries. So you can find all possible match cases basically. Now we set the Boolean approach to be the baseline as y equal to 1 for this speed up analysis. So this is speed up for different query sizes. The database encrypted database size is 128 GB. We kept it 128 GB so that we can analyze the data transfer from your storage system to DRAM, because it needs to frequently update, basically fetch the data. So arithmetic approaches, which are prior approaches, they already show a speed up, which is by order of a magnitude as compared to Boolean technique. And we can refer back again from the background that why, because these have lesser memory footprint and they are much faster. Our approach, CipherMatch software, provides further 42.9 times speed up, because we eliminate homomorphic multiplication also in prior approaches and only use addition. We also see that CipherMatch software speed up increases with query sizes. And that's also because we eliminate the homomorphic multiplication, and it's becoming now scalable because homomorphic additions are much easier to perform. Now, this was one of the results. There is an energy results also, which are there in the paper. You can check that out. Next evaluation methodology is now we have CipherMatch software, which is now state of the art. That is better as compared to prior works on CPU. How can we even further improve it? And for that, we implement an IFP-based CipherMatch implementation by modeling the characteristics of NAND flash memory. So we model each of the components of these bitwise operations, and we designed a model in which we will perform homomorphic addition operations, basically. And the baselines that we compared it with CipherMatch, conventional compute-centric system with same configurations, a memory-centric system where we use a SIMD-RAM unit, and a storage-centric system where we still need to move the data from your storage system, NAND flash, but till your internal SSD DRAM. And this is another comparison that how exactly storage-centric system, if we utilize not the IFP, but ISP operation, how it will go. And again, for the same set of workloads. Yes. Sorry. So is it noisy? It was not going. Oh, sorry. Is it fine now? Okay, thank you so much. Okay. Okay, so now I will present the speed up for different query sizes again, but now this will be for our simulation-based methodology. We observe that all these three approaches, the memory-centric, storage-centric, and our approach, they outperform the software approach because, and fundamentally, they reduce the data movement. The next, CipherMatch IFP, which is our proposal, it outperforms CipherMatch software by 136.9 times. So CipherMatch software CPU implementation, And it also outperforms other near data processing approaches, which is memory-centric and storage-centric. One of the fundamental fact is you have reduced the data movement. The second fact is because you have massive bit level array level parallelism that you are utilizing in your NAND flash. The third thing is, which is interesting to observe, is that cipher match IFP speedup actually decreases with the query sizes. Now, there is a reason why this happens. There is a decrement because the flash read operations are very costly that you want to perform. Now, if you have, for example, different query sizes, now if you take all circularly shifted queries, if you have 16 queries, you have 16 variants of those queries. You need to fetch always from NAND flash the same data, basically again and again for the same queries. If you have 256, then it will be 256 times. Whereas in other cases, cipher match like processing using memory, you just load the data once from NAND flash to your DRAM. The DRAM's reads are much faster than NAND flash read. So that's why we see a decline in this speedup. But this is much faster, still faster than as compared to other approaches. But of course, for some cases like 256, where we see cipher match PUM actually outperform cipher match IFP because the number of reads, redundant reads basically increases. There is an energy consumption for this same set of baselines. All three near data processing system provide large energy savings over cipher match software, and cipher match IFP provides 256.4 times energy savings over cipher match software, and by largely reducing the data movement. In this case, we will see that the energy consumption is less as compared to any of the approaches because we reduce the data movement, which is one of the dominating portion which consumes your energy consumption basically. So there are more details in the paper, like more detailed observations from our evaluations, some more results, we comparison with Boolean approaches, end-to-end system design, how can we enable cipher match in commodity SSDs like host changes and the controller changes, SSD controller changes, overhead analysis of the cipher match hardware. Basically, if we assume that we have some sort of modification in the NAND flash by adding those two transistors, and storage overhead, basically we need to perform our operations as we are just discussing in enhanced SLC programming mode, because that's how it will work efficiently or reliably basically. And finally, like how we perform bitwise operations in much more detail. And for that, we invite you to check out a full paper. So to summarize, we propose cipher match, a new algorithm hardware code design that significantly improves the performance of secure exact string matching algorithm with two key ideas. First is by packing multiple bits of database and also eliminating the homomorphic multiplication. It reduces the memory footprint and provides scalable approach. Second, using in-flash processing to accelerate secure exact string matching. It reduces data movement and leverage the bit level parallelism or array level parallelism. And we outperform the prior state of the art in both software and hardware approaches. So that's all about the paper. And thank you. Are there any questions?
I actually have one more question. Like, if you're doing only one homomorphic addition, like, why are we using BFP-like schemes? Because they're like more lightweight, that does not use any polynomial or symmetric schemes.
That's true. Yeah. So that's one of the things in the starting that I said, that if we use symmetric schemes, one of the problems with those symmetric schemes is you will actually leak the search pattern, because the query is actually going to be, so if you send the exact same query with a deterministic encryption, you will have the exact same encryption. So now the server can actually keep a track and get to know that same query has sent, I have to send back the same result. So to remove this part, that's why we use HE type schemes where BFV is actually good for us because we have to perform exact integer, not approximate. And it also provides us with the two encryption parameters. One is secret key and one is the noise, which will provide some more randomness for every queries. Okay.
There's a question on YouTube. So
yes,
the person who asked before, Anshika, she elaborated on her question. So it goes like this: does the presence of these bitwise latching circuits in NAND flash memory enable new opportunities to design specialized security latches or mechanisms that enhance data protection, authentication, or tamper resistance directly within the hardware? you can integrate these security features at the circuit level within the SSD architectures.
Okay, that's a interesting, let's say, comment. So first thing is that for those latches, one of the things is that we need to make them reliable. If we can make them reliable, these can be used to perform some sort of arithmetic operations. With those arithmetic operations, if we can make our data to be secure, this is good. But if we cannot make, like, it needs to study from an algorithm perspective if the data can be made secure, or let's say more private, with using these arithmetic approaches. For example, one of the way I can think is that you have raw data and you want to send it out, let's say do something, and you want to accelerate encryption operation. Can you accelerate encryption operation using this data latches? Maybe that's possible. I'm not saying no, but I'm not saying yes also confidently. It needs to be studied properly. Yes, okay. I think you need this. Oops.
Yeah. So maybe I missed something. So my question is it possible to increase the number of clients to the server? Because for now, the database in server has been encrypted, and if the client try to have some string matching with the server, it also need to encrypt its data. But if we have more than one client, all of them are requested to use the same encryption, right? Is that very dangerous? Thank you.
Thank you. So for example, this whole analysis, whole paper is about single client system and a single server system. And one of the things it works is because your secret key is actually generated by your one client. If you have a organization type of system where you have an organization having their encrypted database and employees wants to perform string matching, let's say string matching, they can use string matching concepts fundamentally like homomorphic addition, but they need to go with some other sort of encryption which uses some other set of parameters, or homomorphic encryption which uses some other sort of parameters, and the encryption part will change. But fundamentally, the homomorphic addition part will still remain the same. Yes. But yeah, it requires some more analysis in depth. If any other client can have something from the other client, can get something, some other information, and there is a separate domain for it, which is using homomorphic encryption and multi-party computations, which is a separate part that uses. Sorry? We have multi-key homomorphic encryption and separate things. Maybe that's a good thing if we want to elaborate it further with those sort of designs, or with those sort of protocols. Yes, Giray.
Yeah, so it's a very relevant question, actually. I see why cipher match is secure intuitively, but I was going to ask if you can prove that it's secure in a formal verification method, for example.
So this is one of the things that we are actually looking at right now. There is something that we are actually deeply analyzing it. There are ways to formally verify it. The fact is, if I just give very brief what we have done till now, it is like what we have done, that if we analyze the cipher match and the protocol itself, and we got to know that the threat model actually assumes that we are actually assuming that the server can actually get to know if there is a match or not. So this is open. So you'll get to know yes or a no. But another thing that we need to solve, or let's say verify, is that if the ciphertext which are visible to the outside person, will they leak anything back to will they provide any details about the query or the database? Now for this part, what we figured out is that we analyzed that once we solve the equations that comes out, which I'm not going into detail, we come at the equations that there will be n equations and n+1 variables. Now what does that mean is that you will have infinite number of solutions that are possible to this state, because it needs to be the other way around, n variables and n+1 equation, then you can get an exact solution. So this is something that we have figured out, but it's still not out there in the public version of the paper. But we will soon add this whole analysis with the formally verifying, which is called indistinguishable chosen plain text attack, IND-CPA, and we do that and formally verify this part yet. Okay, thank you. Okay, you're unmuted.
Yeah.
Okay.
I have one last question. It's a small one. So, all of this is when your database fits inside a single SSD.
Yes.
Now, if there are multiple SSDs, like Nika mentioned, 100 TBs of data, at that time you'll require multiple SSDs. Now, I consider that all the data, all the ciphertext that are going to be present in each SSD will be disjoint, so you can perform parallel
Yes.
query on all of them. But did you perform any such
No, we don't have such
scalability
analysis.
Okay.
This analysis, if I just give a very like what is coming from my this current mind is that you need to basically make your system also, because there are some changes in your controller also, and those all SSDs needs to be controlled from a higher level, let's say kind of a RAID system or a hypervisor which is connecting to this. So you need some modifications also from that at the host side.
Okay.
So this part is also still we have not done.
Okay.
Yes. Okay. Then thank you everyone.
Thanks a lot, Mayank.
Thank you. Unmute.
Hi, Gagan.
Okay.
All needs to be controlled from a higher level.
Hello, can you hear me?
My voice.
So Gagan, you're audible on the Zoom, but we need to adjust speakers in the room.
Yeah.
Awesome. Yeah, sure. I'll share my screen meanwhile.
Maybe you can connect this one now.
Sure. Yes.
You can plug this.
Gagan, meanwhile, can you share your screen?
Just a second. I was trying to do that. Can you see the screen now?
Yes.
Yeah, awesome. Just let me know whenever I can get started. I cannot really hear anyone, so can I get started? Or yeah, hey Mohammad.
So I'm going to Hey Mayank. Hey Gagan. Sorry. Okay, let me. I had your introduction page open, but just closed. Okay, great. So for the next talk, we have invited Gagan. So thanks a lot, Gagan, for accepting to be in this workshop and presenting your work. I'm going to introduce you briefly, but feel free to also talk about yourself more when you when you are start. So Gagan is a senior researcher in AMD's Research and Advanced Development Group in Switzerland, working on application acceleration, design and space exploration, performance modeling, and is also leading research on healthcare and life sciences. Prior to joining AMD, he was a postdoc researcher at ETH Zurich in the Safari Research Group, and he's passionate about computer architecture, AI, and bioinformatics. So thanks a lot, Gagan, and feel free to start when you're ready.
Thanks, Mohammad, for the introduction, and I'm happy to be here. Today I'll present my work, which is from my PhD, actually, which was published in ISCA 2022. And this work is still state-of-the-art. It's called SaLWo, which is an adaptive and extensible data placement in hybrid storage system. This work was done in collaboration with the great researchers from Safari Group, from ETH Zurich, and also from TU Eindhoven. So I'll jump right in. First, I'm going to start with an executive summary. Hybrid storage systems use multiple storage devices to provide high and scalable storage capacity at high performance. And we observe two key shortcomings in prior data placement techniques. First is the lack of adaptivity to workload changes and changes in device types and configurations. And second, they also lack extensibility to more devices. And our goal in this work is to design a data placement technique that provides both adaptivity by continuously learning and adapting to the application and underlying characteristics, and also easy extensibility to incorporate a wide range of hybrid storage configurations. To this end, we propose SaLWo. SaLWo is an online reinforcement learning-based data placement in hybrid storage systems that provides both adaptivity and extensibility, and on top of that also provides the ease of design and implementation that requires only a small computation overhead. And in our results, we extensively evaluate SaLWo on real system using a wide range of workloads. We show that SaLWo outperforms prior state-of-the-art data placement policies by 21% in a dual hybrid storage system, and also up to 48% in a tri-hybrid system. And SaLWo was able to achieve 80% of the performance of an Oracle policy that has a complete knowledge of future access patterns while incurring a very modest storage overhead of only 124.4 kilobytes. And the code is open source on our GitHub repository, so I would recommend you to have a look. This is the outline of the talk, and first I'm going to start by discussing some of the key shortcomings, and then we'll go into more details. So let's look at some of the basics of a hybrid storage system. Over here, we have a typical hybrid storage system, which is consisting of a fast yet small storage device and a slow yet large storage device. And if you look at the address space to a user, it is divided into a number of logical pages, example 4 kilobytes, which are assigned to an application. And so for a user, it comes across the storage are at the same level. There's a storage management layer in the OS, which orchestrates the host input-output requests across heterogeneous devices. And the storage management layer also manages the data migration between the storage devices in a hybrid storage system. So if you would like to evict something, which is usually move infrequently excess data from the fast storage to the slow storage, or when the fast storage is full, then we would do some sort of eviction. When data currently stored in the slow storage is moved to the fast storage device, is called promotion. And promotion is usually performed when a page in the slow storage is accessed really frequently, a lot of number of times. If you want a desired policy to be effective, to effectively utilize the low latency, that's what we ideally want, that this policy should effectively utilize the low latency characteristic of fast device while making effective use of the small capacity, and should also provide extensibility when we go for like more devices. And therefore, the performance of a hybrid storage system highly depends on the ability of the storage management layer to effectively manage these diverse devices and workloads and their characteristics. And so what we did, we looked into the prior state-of-the-art policies at that time, and we observed that there are two key shortcomings in the prior data placement techniques that significantly limit their performance improvement. First was the lack of adaptivity to both workload changes, but also the changes in the device types and configurations, because that has their own unique characteristics. And second, there was also a lack of extensibility to more devices, because when we go for large systems, we would have not just one or two storage devices, we'll have more. So we wanted to take a closer look at each of these shortcomings. So first, we had a look at the lack of adaptivity for workload changes. So if you look at these prior policies, they only considered a limited number of workload characteristics. So designers statically tune the parameters values for all the considered workload at design time based on some empirical analysis and designer experience, and expect that those statically fixed values to be equally effective for a wide range of dynamic workload demands and also for newer workloads. And we know the workloads are changing really rapidly right now, especially in the era of AI. So over here we have we show the average request latency on the y-axis for different policies. So here we have CDE policy, which was state-of-the-art heuristic-based policy. Then we have a policy called RNN HSS policy, which was a supervised learning policy. And then we compare it with an impractical oracle, which is a dream, which we would like to achieve, but it's not possible in terms of the hardware cost and to implement it actually in the system. But this oracle has the full knowledge of the future input-output access pattern. So this one is the golden standard for us. And we observe and here the lower the request latency, the better. And we observe that all the baselines provide reasonable performance under specific workloads. For example, CDE performs really good for RNN HSS performs really well for this HM workload. While for user 0, we see CDA performs better. And then, so none of the policies are good for all, but they're good in certain cases. And we observe, like on average, a performance loss of these policies by up to 41% compared to an oracle. So we conclude that considering a limited number of workload characteristics at design time could lead to a significant performance gap. So we have a lot of performance which is left on the table. And then if you look at the other aspect of lack of adaptivity, which is changes in device types and configurations, that's also one of the problems, because a lot of these policies, they don't really consider the underlying device characteristics. For example, changes in the level of asymmetry in the read-write, garbage collections. So these aspects often are kind of not fully considered in these policies. So we have in this figure, again, we show 3 policies. And in addition, we have another policy, which is an extreme case when everything is placed in the slow storage only, because we have a lot of capacity, so we'll place everything there. And here we observe that the performance of some of the workloads is even worse than slow-only policy. Then that places everything in the slow storage compared to other policies which are out there. So it means we don't even need any sort of policy. We just simply go with the easiest or the naive way of just placing everything in the slow-only storage. While if we go for a different hybrid storage system configuration, we see it might be that the slow one is not the best, and slow one is producing really bad results. So in this case, it makes sense that we have some sort of policy which is managing this data placement. So therefore, we conclude that the high diversity in device characteristics makes it very difficult for a system architect to design a generic data placement technique that is suitable for all hybrid storage system configurations. And now if we look at the lack of extensibility, which is one of the second key shortcomings of most of the prior techniques, that these techniques are really rigid, that require significant effort to accommodate more than 2 devices. So if you look at the state-of-the-art policies, many of them are just designed for 2 storage devices or at most 3. But the moment we go for more, it requires really, there's nothing which is there. We have to manually somehow come up with something on the fly. And if we extend these policies, like for example here, we show like a tri-hybrid storage system, then we would have to design a completely new data policy to exploit the new device characteristics to handle the eviction, the promotion of the new storage, and we would have to update the heuristics, or we have to retrain the machine learning model somehow to take into account this new extra storage we added. Therefore, system architects need to put in significant effort into extending the prior data placement techniques to accommodate more than 2 devices. And of course, this wastes precious design time and human resources. So therefore, in this work, our goal was to come up with design a new completely data placement mechanism that can provide adaptivity by continuously learning and adapting to the application and also the underlying device characteristics. And also it should be easily extensible to incorporate a wide range of hybrid storage configurations so that it's more future-proof as well. And therefore, to this end, we came across, we proposed SaLWo, which formulates data placement in a hybrid storage system as a reinforcement learning problem. And if we would, like first we would have to go into the formulation and understand what exactly we mean by reinforcement learning and how we can formulate data placement as a reinforcement learning problem. So let's look at it like, what is reinforcement learning in the first place? So in an RL system, there are 2 key components, the agent and the environment. The agent observes the state of the environment in every step. It could be any sort of features which you provide of the important features of the environment to the agent. And based on that feature, the state, the environment, the agent will take an action, and then it receives some sort of reward for that action so that the agent knows how good or bad it is performing. So in case if the agent is doing bad, you can give it like a negative reward so that agent knows where to guide its search for the next state and action. So the agent's goal is to find a policy where agent's action in a given state leads to maximum reward. So that's what agent is trying to do here. And so if we would like to formulate data placement as a RL problem, so how would we do that? So in this case, SaLWo is the data placement agent in our case, which is handling different actions, while the hybrid storage system acts as the environment. So SaLWo observes different characteristics from the hybrid storage system. For example, the workload features, system features for every storage request, and it will use it as a state information to take a data placement action. And for every data placement action, SaLWo receives a numerical reward that evaluates the effectiveness of the data placement decision. So that's how we formulate in a nutshell how the data placement as an RL problem. So now we will concretely define the state, action, and the reward for SaLWo. So let's talk about the state first. For the state, we don't want to use too many features because we would like to have this data placement policy still to be possible to run at runtime, not really a compile time or design time. So we use limited number of features after performing proper feature selection to reduce the implementation overhead. And we observed that the RL performance is more sensitive to the reward than to the state information. And there are some even extreme cases where we have seen the reward is all you need. So that even if you provide a good reward, your agent will perform really good. So in our case, we provide a 6-dimensional vector of state features. And some of the examples are like size of the incoming request, the type of request, the capacity, the frequency of the current page, which have been how many times it has been accessed. We provide more details in the paper about that. And we also quantize the state representation into bins so that we reduce the storage overhead. So rather than using a higher precision, we go for a lower precision representation for the state vector. And then if we talk about the reward, so reward is defining the objective of SaLWo. So what SaLWo should try to perform. So based on your metric which you are interested in. There could be different features or different objectives you would like to achieve. Could be performance in terms of throughput, latency, or it could be energy consumption or power, whatever you're interested in. In our case, we formulated the reward as a function of request latency because that was our goal in this work. And this is really an interesting way to do that because it encapsulates three different aspects. So it's able to take into account the internal state of the device. By latency, you can tell whether what are the read-write latencies, if there's some sort of garbage collection that is happening, so the latency will be higher, the queuing delay. So it encapsulates all these things into one function. Then you can also use latency for throughput as well. So the lower the latency, you can achieve like higher throughput. And also evictions. Evictions are like we were discussing before, that evictions happen in the background when you would like to move page from one like faster storage device to the slower one. So that part also is kind of encapsulated. So it's kind of like the internal state that's encapsulated in the request latency. We provide more details in the paper of like how we formulate reward and how it's important for reinforcement learning. So let's go in the action. So for action, we define as a selection of a storage device to place the current pages. So it could be if you have two devices, so we say either fast or slow. If you have three devices, you can have another action. So it could be fast, medium, and slow. So this action is easily extensible to any number of storage devices. You just simply mention how many devices are there, and that becomes your action. So it makes really easy to come up with a new policy whenever you have an extra storage device added to your system. And so SaLWo is able to learn proactively to evict or promote a page based on the action. So whenever you add a new device, so it will handle automatically everything. So you, as a designer, you don't really have to think about again to come up with a different heuristic for eviction, promotion, etc. Okay, let's go into the overview and a bit of design of SaLWo, how we do that, so make things more concrete in terms of all the different parts we just discussed. So first, we discuss the execution model for SaLWo. So we implement SaLWo in the host OS, where for every storage request, SaLWo uses an RL decision thread to make a data placement decision. So there is a thread running which will decide where the data should be placed. While SaLWo uses another thread, which we call as the RL training thread, which is running in the background, and it keeps collecting information about SaLWo's state, action, and reward, which it uses to train a data placement policy. So the training thread is running separately than the decision thread. And periodically, we update the weight of from the training thread to the decision thread. So we don't really keep on doing it like every now and then, but it happens periodically. And like I was mentioning, these two threads are implemented and running asynchronously. That really avoids that the training in RL training thread interrupts any sort of delays while the data placement thread is trying to make a decision for the incoming request. So, and that's kind of like a how to say, a parameter which we choose based on our evaluation when the weight should be updated. So now if we go into the implementation of each of these threads, that's how the complete overview looks like. So first, let's focus on the RL decision thread, where SaLWo decides the data placement of the current storage request while collecting the information about its decisions. So how it works. So for every new storage request to the hybrid storage system, SaLWo will use the state information to make a data placement action. So the information like I was mentioning before in terms of the size of request, type of request, etc. So it will observe those features, which will go into the inference network that predicts the expected benefit of each action for a given state. So it will try to predict what was the best action for this specific state we should take. And SaLWo policy will select the action with the highest expected benefit, or you can say the expected reward. Or it could even be a random action if we would like to do some sort of exploration of the hybrid storage system. So in case that's also a hyperparameter which we use in reinforcement learning that we would like to do some sort of exploration in the beginning or every now and then to understand the environment. So it could be a random action just to see, just to test water in a way that like what sort of reward we'll get if we take a completely separate action just for learning purposes. And while making these data placement decisions, Sybil collects information about the state, action, and reward, and it puts it into an experience buffer, which is used for the other thread, which is the RL training thread. So once we go into the RL training thread, how it executes, whatever the data we were collecting in the experience buffer, it will fetch that data to update another network, which we call as the training network, which is, like I was mentioning, it will be running asynchronously. And this this model will be trained asynchronously, picking up all the experiences which are in the buffer, and it will make sure that you're having the updated weights, so that in this case, Sybil is continuously learning from the past experiences and their impact on the overall system. So once the training thread has updated the weights, then we have a parameter in terms of transferring the weights from RL training thread to the RL decision thread. This enables us to have a parallel execution of two threads. We simply duplicate the neural network. So both the networks are the same in training network and also in the inference network, so that we can easily just copy the weights. And they don't really interfere anyway with the training and the inference steps. And we like I was mentioning, we periodically update those weights. So if we focus a bit on the network itself, it's a neural network, but we don't really go deep as it could be really prohibitive due to long time, and it requires for training and for conversions. And we observe that we don't really need a really deep network. In this case, we can even go for a two-layered network. That's what we do. Here we have we found that only a simple feed-forward network with only two hidden layers provide good performance for Sybil's data placement task. So we don't really have to go deeper in any way. So if you look, the network takes the observation vector, which is coming from this experience buffer. And this observation vector is again in the way of how we have these states encapsulated. So it's size of the request, type of request, these kind of features which we use as an input, and also the reward what you get. And then the network takes these observation vector as the input and produces a probability distribution of Q values as the output. And based on that, it kind of updates its decision making on what sort of state action should the network do whenever we are going through the data placement decisions. So yeah, that's how the implementation looks like. We have more details in the paper. Let's talk a bit about the evaluation of Sybil and the key results. So we perform real system evaluation for both of two different cases. So we have dual hybrid and also tri-hybrid systems. Over here, we show the evaluation system that consists of multiple different devices. We implemented everything on the actual system, and we were using an AMD to run everything on the OS side. We didn't really offload anything on the GPU side, which could be another optimization for the future work that could be performed. But in our case, the model was not that big. And also, since the decisions were happening on the storage side, we observed we don't really need such a offloading mechanism to the GPU side as well. So if we talk about the different configuration which we tested, so we had mainly two different configurations. The first was the configuration we call cost-oriented hybrid storage system configuration, where we had a high-end SSD from Intel. It was an Optane, and then a low-end hard disk drive. So this low-end was really slower compared to the high-end, but the amount of storage was a lot, so you could easily fit a lot of data there. Then the other configuration we had was the performance-oriented hybrid storage system, where the difference between the latency of the high end and the middle end, we call it middle end, not that much. So both of them have really similar latencies in this case. So primarily we focus on these two configuration, but when we also have a hybrid system, we combine all the three storage devices. So we had a system called high end, middle end, and low end. So we perform extensibility analysis on that. And in terms of the workloads, we had 18 different workloads, which were coming from MSR Cambridge and FileBench suites. And at that time, we evaluated 4 state-of-the-art data placement baselines and compared the results with the SaLWo. So we have these two CDE and HPS, which were heuristic-based policies. Then we have archivist and RNN HSS, which were learning-based, ML-based approaches. So here we have show the performance results for the cost-oriented hybrid storage configuration in terms of average request latencies. And these are for MSR Cambridge workloads for all the different workloads and policies. So the lower, the better. So at the end, we also have Oracle policy, which is the best policy, which is hard to achieve in reality, but that one Oracle has the complete knowledge of future access patterns. And if we compare SaLWo to the other policies, we observe that SaLWo consistently outperforms all the baselines for all the workloads in this case, which was pretty impressive. And once we go for the performance-oriented hybrid storage configuration, where the difference between the two devices is latency is not that huge, here we observe SaLWo provides 21.6% performance improvement by dynamically adapting its data placement policy and not just sticking to one policy for every workload. But in this case, we observe that SaLWo provides like slightly lower performance than two baselines for only two workloads. We observed that such workloads were really write intensive, so there were many random requests and also had a lot of random requests in terms of both excess patterns and also the request size were different. Therefore, we have a discussion about this in the paper that in such workload probably we require more frequent retraining. So we update the weights frequently so we can have a better data placement policy in SaLWo, but overall, we saw really good results. And then we saw on average, if we do a comparison, we achieve 80% performance of an Oracle policy that has complete knowledge of the future excess pattern, which is amazing, I would say, because in other cases, it's really hard to achieve that. We also evaluated mixing 2 or more workloads at the same time. So in the previous case, we were just running one workload at a time, but it could be that you have a storage system where you have multiple tenants and each of them is trying to run different workloads. So on the storage side, you will have different requests that are coming from different workloads. So it will kind of lead to a scenario which is unpredictable execution. And then they're unpredictable. It's also like kind of like distributed workloads. And of course, it tests the ability of SaLWo further to dynamically adapt its decision-making policy. So here again, we show average request latency for mixed workloads. We mentioned the mix, so we are mixing the previous workloads from MSR Cambridge with the file benchmark suite. And then you see we have SaLWo, 2 different settings we use. There is a SaLWo with default hyperparameters, which is in pink. And then we have another one, which is called SaLWo Opt, where we optimize the hyperparameters as well for these mixed workloads. And we observe that with using the default settings, we still provide 27.9% higher performance than baseline policies. But if we optimize the hyperparameters a bit more, then SaLWo Opt is able to perform even better. So it can provide 7.2% higher average performance than SaLWo default settings. So we concluded that SaLWo can effectively adapt its data placement policy to highly dynamic workloads. And also hyperparameter tuning is pretty important. We provide a lot of insights into that as well in our paper, and we have more extensible discussion on that. Then we also extended SaLWo for more devices. So in this case, like I was mentioning, extensibility is really important as well going forward to make sure that your policy is future-proof. So to do that, what we had to change in SaLWo. So compared to we had only 2 devices. To go to tri-device system, we had to add a new action, and then we added the remaining capacity of the new device as a state feature so that the agent is aware of how the environment looks like. So these 2 actions were enough for us to just extend SaLWo rather than coming up with the new heuristics for eviction or for promotion. So we just had to do that. And we left it to SaLWo to automatically figure out a new policy, the best policy it can. And so here we show the performance results for a state-of-the-art heuristic-based policy, and we only found one. Actually, there were not many, and we understand why, because it's not easy to make these policies. You always have to handle all the different cases, and there could be even corner cases which you need to handle. And this policy is an extension of the CDE policy, which we mentioned before, which actually required a lot of significant implementation overhead to handle all the data placement cases. And also this policy kind of sets a threshold of when the data should be moved around. So that was also another parameter which you play around with, which makes it a bit like static design time decision. And it's not the great way to do things. And if we compare that to SaLWo for a tri-hybrid system, we observe that SaLWo outperforms the state-of-the-art data placement policy by 48.2% in a real tri-hybrid system. And SaLWo reduces the system's architect burden by providing ease of extensibility. So it's really easy to easily extend this further to even 4 or 5 different devices. And of course, we just didn't apply the RL and try to come up with the best policy. We also tried to provide a bit of explainability analysis. So here I wanted to give a bit of flavor of what sort of explainability we did. So here we wanted to understand further and explain why SaLWo was doing the decision it was doing. And I believe explainability is one of the important aspects whenever you're working anything with the AI models or anything with the reinforcement learning. So what we did, we extracted the SaLWo's action for different workloads under high-end and middle-end storage, and then for high and low-end storage. So these 2 configurations. And we analyzed the page placements for each workload. So figure here shows that SaLWo's preference for fast storage on the y-axis over the slow storage. So it is the ratio of fast placements divided by fast plus slow placements. And on the y-axis, we have different workloads. So if if a bar is higher, it means it has more preference to place data in the faster storage than the slow storage. So we made many different observations. The first observation we made for high-end and low-end configuration, where everything is in dark blue, we see that the SaLWo had a lot of preference to place everything in the high-end storage, so the faster storage, because it was pretty interesting to see that, because SaLWo learns that despite the eviction penalty that we will have because there's not enough space in the fast storage, the benefit of serving more requests from the fast storage is still better, and while taking into account the eviction penalty. On the other hand, when we go for high-end and middle-end, which is the light blue configuration, here the latency difference between the 2 devices is a bit smaller compared to the other configuration. And here we see like SaLWo is placing more only performance critical pages in the faster storage. So we see in some cases the preference to place in the faster storage is almost negligible, because it understands that you still get a lot of benefits by placing it in the mid-end device rather than trying to handle the eviction penalty. So yeah, that was one of the observations we did. We also provided more observation, for example, in the light blue configuration of high-end and middle-end. SaLWo really shows really less preference for putting pages from one in or Proj 2, because these we dig down, we try to understand what sort of characteristics are there for these workloads, and we observe that these workloads are really cold and sequential. Thus, they're less suitable for fast devices because they will cause a lot of evictions. And therefore, SaLWo was able to learn that, and SaLWo shows that there's more preference to place those pages in fast storage device rather than putting into the middle storage device. So it was really interesting insight, which we see. And we provide even more insights, and therefore we observed that the explainability aspect was really there as well, and the SaLWo was making really some decision which an expert designer who's defining a data placement policy would do that. And to understand more explainability and analysis, I would really recommend to read the paper. So we also discuss a bit about the SaLWo overhead. So all of the performance benefits we discussed, they come at a modest cost of 124.4 kilobytes of the total storage cost, which is in terms of the experience buffer, the inference, and the training network. And also we have a 40-bit metadata overhead per page for the state features, which we were discussing in terms of the size of the request, the capacity of the storage device. So these kind of features we provide for the state representation to SaLWo to make an action. So that's also an overhead. If you look at the inference latency, it was 10 nanoseconds for SaLWo to make a decision, which is not really high compared to any high-end storage device we have. While the training latency for the network is 2 microseconds, so this network is running in the background to train. It's training the weights and trying to observe and making sure that we are following the best, the most accurate description of the environment, so SaLWo can make good decisions on the fly. So if we observe all these overheads, and we see that the overhead is not that huge, so it's a small area overhead. The inference latency is not really high as well, and also it satisfies the prediction latency for making a data placement decision, because we have been away from the processor, so we have the storage side, so we can still we can handle these 10 nanoseconds. We have many more exciting results in the paper, including a throughput comparison, where we provide comparison of throughput and compare it to all the baseline policies, and how we like I was mentioning before, the reward we have indirectly captures the throughput. Then we also talk about evaluation of completely new ones in workloads where we don't even do the training, and how SaLWo can effectively adapt their policy on highly dynamic workloads. We also evaluate different features. We talk about the importance of doing feature selection for the state representation, and SaLWo autonomously decides which features are important to maximize the performance. So in the end, after doing proper feature selection, we keep only those features. We don't really have to keep all the features to reduce the overhead. Then we have many more results in terms of hyperparameter values as well. Hyperparameter tuning is pretty important in reinforcement learning to kind of stabilize different aspects of training and learning as well. We also provide the sensitivity to fast storage capacity. So we show like how if a storage capacity changes, how we can dynamically adapt SaLWo's policies to available storage size as well. So we have many more results in the paper. I would really recommend to have a look. We have the code, which has been open source. And yeah, if any questions, please feel free to reach me. So now I will conclude my talk and open the stage for some questions. So in this work, we introduce SaLWo, which is the first reinforcement learning-based data placement policy for hybrid storage systems that provides adaptability, easily extensibility, and also ease of design and implementation. We evaluated SaLWo thoroughly on real systems using many different workloads. We showed SaLWo improved performance by 21.6% compared to the best prior data placement policies in a dual hybrid storage system configuration. When we go for a tri-hybrid storage configuration, SiBL outperforms state-of-the-art data placement policy by 48.2% and shows extensibility as well. And all these benefits of SiBL are coming at a really modest overhead of 124.4 kilobytes. And we observe that it's able to achieve 80% of the performance of an Oracle policy. And again, I would recommend to have a look at the code. Everything is open source. And yeah, I'll be happy to take any questions now. Thank you.
I have a question. Can I go ahead?
Go ahead.
Thanks a lot, Gagan. So we have some people, they have some questions, so they will ask, and then thank you. Go ahead, Priya.
Hi, Gagan. So,
no, not this. It will capture you.
Okay. Hi, Gagan. So in the one of the slides you mentioned that there are two threads, decision and inference and training threads, and the model weights are being copied after some 1,000 I think experiences. So as soon as the model is trained. So when this data when the weight copying is being done, is the inference thread on pause and the requests are stalled or queued up?
Yeah, exactly. So when the weights are being copied, right? Like it cannot really make any decisions at that time. So it's kind of like the request must be queued.
So then, did you see any tangible performance impact due to this stalling on like you could have made there is some Oracle threshold which is a little bit higher or quite a bit higher, but because of the stalling you are experiencing performance drop?
Yeah, so that was kind of like a hyperparameter as well. I would say for us, a parameter in a way that we were trying different configurations. We were trying to do like, okay, when we copy the weights, we can copy after 1,000 experiences or 2,000 or 500. So they were like different things we tried out. And based on the analysis on all the extensive workloads we had, we went with this 1,000 as the parameter we chose. But of course, it could be that there could be more effective way to do that. Maybe we can even have a third network because the overhead is not that high, which is while we are copying, it can still be running in the background. So there are many different ways. So yeah, there's a room to improve that.
So would it have been possible to just switch the two threads and have copying being done at the backhand, like switching the inference thread to training and switching the training thread to inference, and just then transferring or copying the weights from the previous training model to the current training model? So just switching the two threads.
But are you saying like the training thread will do the inference then?
Yeah, so it will be constantly switching between the two as soon as it is ready. So this way there is less stalling and there is copying goes into becomes a backend task instead of putting it on the front end.
Yeah, could be. I haven't looked into like what maybe there's overhead of freezing the network and trying to do the inference, and no, could be. It could be possible. Yeah.
Okay.
Yeah,
Okay.
it's an interesting way to look at.
Yeah. Thank you.
Hey, Gagan, thank you for your talk. Just wanted to ask you about the applicability of this technique to other systems now with more newer technologies coming up like CXL and other interconnection fabrics, which can pull up a lot of memory and storage. So what is your thought on that?
Right. I think it's a really good question. So I think for these newer kind of system, it would be really exciting to try out this kind of approach. And I think this one is the right way to go as well. Because I don't think like for every new system, we want to build something from scratch. I think it's an interesting direction to try out if it can easily adapt or what sort of changes we need to perform to take into account the features for kind of like if we have shared memory aspect of things, or if there are like some unique characteristics which we can exploit and we can add that feature into Sybil, so maybe it can provide even better performance. It's an interesting future direction to try out for sure.
Thanks.
Thanks, Rakesh.
Any other questions? I guess no. Then thanks a lot, Gagan, for being with us and your great talk.
Happy to be here. I at least got the Safari mug with me.
Oh, okay. Yes, you have your. Thank you. So I guess now we have again a 30-minute coffee break. Let's be back at 3:25. Perfect.
Mira,
Can you hear me on microphone? Hello? Test? Test, test.
No, the last one.
Oh. I'm on, not on mute.
That's okay. I'm just mimicking a guy. So that the reviewers will pay attention and you're going to see. But now it's not double. Sharing something else. Which is actually a good idea.
Shall we start? Is the mic on? Yep. Okay, so we just saw Gagan presenting data placement and how we optimize data placement using reinforcement learning in hybrid storage systems. This work, again, we have been looking at this direction for a while, and we have tried to address other tasks that are critical in hybrid storage systems, like data migration also, and how we can't basically optimize them in isolation, and we need to coordinate these two tasks, and how we can use multi-agent reinforcement learning for this. So this work is called Harmonia, enhancing data placement and migration in hybrid storage systems using multi-agent reinforcement learning. So I'll start with an executive summary. As you all saw from the previous talk, hybrid storage systems use multiple heterogeneous storage devices to provide scalable storage capacity at high performance. The performance of this system depends highly depends on the effectiveness of the data placement policy and the migration policy. Now, we identify two key shortcomings of prior HSS data management techniques. So prior techniques focus on improving only the data placement policy or the migration policy, but they do not optimize both. And if we try to naively combine them, then it doesn't actually provide good performance. In fact, it provides subpar performance due to lack of coordination between the two policies. So our goal is to design a holistic data management technique that optimizes both data placement and migration policies and achieves coordination when they make decisions. So we propose Harmonia, which performs combined optimization of both the policies, achieves coordination, provides adaptivity to workload changes and device characteristics, and also can be easily extended to multiple configurations and storage devices. Now, in terms of key results, we evaluate Harmonia also on a real system using 17 data-intensive workloads. We see that it provides 32% and 33% in performance improvement compared to the prior best performing prior approach on two configurations that on a real system. When we extend these configurations to have more devices, we see the performance actually improves, and we see up to 42% average improvement in performance. And again, all these performance benefits come at a very low inference latency and training latency, and also the storage overheads are very negligible. Now I'll provide some background. I think this we have already seen from the prior work. So there is a kernel layer or a management layer in the operating system, which exposes a unified virtual address space to the applications to read or write data, and it orchestrates where the data goes if there are multiple devices, storage devices with heterogeneous characteristics. So there is a high-end device which is quite small but has very high performance. There's a mid-end device and a low-end device which are basically having large capacities. Now the data migration component is also very critical because it has to, you can place the data once in these devices, but over the period of time you need to add more, you need to place more data, and you need to evict the data that you have placed before. And you also need to bring data from prefetch data from a slow device that was placed long back, which is being accessed more and more. So these the data migration policy is also very critical for the performance of HSS. So the effectiveness of these two policies is very critical for the performance of the HSS management layer. So two key shortcomings in prior techniques, or basically three key shortcomings that significantly limit the performance are prior techniques don't optimize both policies together, the placement and migration policies. And if we naively try to combine these policies, then it provides suboptimal performance because these two policies can make conflicting decisions, and we need to, and this results in a lower performance. And some of these policies use heuristic techniques, which are basically fixed policies with thresholds that don't really scale to multiple devices or configurations. So we also see the lack of extensibility in prior works. So some empirical data. So in terms of lack of holistic data management, where prior approaches are not optimizing both the policies together, and they use heuristic approaches for one of the policies. So for example, we just saw Sybil, which is a RL-based data placement policy, but it basically uses a heuristic approach for data eviction, which actually significantly adds a significant latency overhead to the I/O latency. We also show, so we show the average request latency of multiple policies here: CD, KSVM, RNN, HSS. These are some policies that KSVM and RNN, HSS use supervised learning approaches. Sybil uses RL. CD is a heuristic data placement approach. Now, we show the performance on two different configurations across a wide range of workloads, and we see that we still see 50% performance gap between the Oracle approach, which has knowledge of future access patterns, and the best performing prior approach, which is Sybil. In the cost optimized HSS, it is even more exacerbated by with the performance gap being 59% on average. Now, this is because one of the policies that that these techniques propose is a heuristic approach, and it doesn't really adapt to the workload or the changes in HSS configurations. Now, we tried to address this problem by naively or combining the best of both worlds and try to see whether it actually makes improves the performance. But again, we need to what we do with combining these things is basically a naive combination. And so what we observe with combining these best of the both worlds is when we say combine Sybil plus KSVM, CD plus or Sybil plus RNN HSS, and we also look at CD, which is a heuristic technique, and propose an RL based migration policy, and we also show Sybil. So when we see the performance of these baselines or the naive combinations, we see that it actually performs worse than the standalone approach, which is Sybil. So this means that it basically these two policies are making decisions which are conflicting with each other, and they don't coordinate and make decisions which are which improve the performance. So the lack of coordination is basically the reason for why these naive combinations are not working. Then there is extensibility, as we also saw before. Whenever you have heuristic approaches, if you add one more device or change the configuration altogether, the policies have to be redesigned because they are threshold-based policies which don't really work well when you add more, change the configuration. Now, our goal was to co-optimize both data placement and data migration policies and achieve coordination between the two policies, because we don't want, we can combine and then deploy the technique, but it has to work well. So coordination is important, and easy extensibility of to incorporate wide range of configurations. So our proposal is Harmonia, which does all of these things using multi-agent reinforcement learning. So again, I'll go a bit fast on the background on and how we formulate this problem. So in a typical RL environment, you have an agent and an environment. The agent observes the environment via the state features. It performs an action which changes the environment, and then it gets a reward from the environment for the action that it performed, and the reward basically prods the agent in the right direction, hopefully. Now, in our case, we have the data placement agent and the data migration agent, and the environment, which is the hybrid storage system. In both cases, we observe the state from the HSS. The two agents observe the state features. They perform actions in an asynchronous manner, and then they get two rewards now. So we have an immediate reward for the placement agent because the impact of the placement agent is seen immediately, where you place a page in one of the devices. You can observe the latency of that placement right away, and then you can give a reward. But in case of migration agent, the problem is that if you move data across devices, unless the placement agent or the future requests are placed in after the migration, you can't really see the impact of the migrations right away. So that's why we give a delayed reward for the migration agent. Now, again, in terms of state features, we want to have a limited number of state features, primarily to reduce the implementation overhead, and also, as the previous speaker mentioned, RL agents are more sensitive to reward. We have a 7-dimensional vector of state features. Some of them belong to the application characteristics, some from the HSS environment, and we also have some migration related features which are critical to make or basically avoid conflicting decisions. Again, we also do this state quantization of the state representation because we want to reduce the storage overhead. Now, in terms of reward, the objective of the agents are defined by its reward. So we again look at performance as an objective. So our reward is basically a function of the latency. So in case of placement agent, we look at the latency of the current request, which was placed at that time step. as the reward for the placement agent. Now for the migration agent, what we look at is we can perform migrations of, let's say, X pages. You can define the count of, or you can define your own value for the X. But then after performing these migrations, you need to see the impact of these migrations for future placement or future IO request handling. So what we look at is, like, we look at the placements of several future requests, and then use those latencies as a reward for the migration agent. We also, so the function, the migration agent reward is a function of the future placement latencies after the migrations are performed. And we also provide a penalty for the migration agent to avoid ping pong migrations, which means that if you place a page in one device and immediately migrate it, then we want to avoid that. So in terms of the why we choose latency, again, it captures the what is going on inside these storage devices in terms of asymmetry between the read-write latencies, garbage collection, queuing, and so on. So in terms of action, the data placement agent is basically performing, deciding which storage device to place the data. The migration agent is looking at all the pages that are present in the hybrid storage system across all these devices, and selecting which pages have to be migrated and what is the target destination of these pages. Now, these actions are easily extensible to more number of devices because you just need a single node in the neural network that we use for Harmonia. So I'll give a brief overview of the design. So we have the IO request coming from the application. There is a data placement agent, which again has multiple threads, primarily to reduce the overhead of training and training on the action of the data placement. So or the placement of the IO request data. So we have a training thread and an inference thread, and the data placement agent decides where the IO request data has to go into, whether it's the fast device or the slow device. Now, over a period of time, you have pages stored in multiple of these devices. So what we do is we have a data migration agent which is completely running in the background, which looks at all the data that is previously placed. We have some optimizations here to avoid ping pong migrations and so on, which I'll not go into, but I'll refer you to the paper for that. So what the data migration agent looks at is basically deciding which pages have to be migrated. These are called candidate pages, and where they have to be migrated to. Now, this data migration agent puts all these candidate pages into a migration queue, and there is a migration thread running in the background, which basically looks at the bandwidth utilization of these IO storage devices. And whenever the bandwidth is quite low, it basically performs these migrations. Now, there are several cases that I'm not going into where you may not have the bandwidth right away and it can delay the migrations. So we have some other ways to handle these scenarios. But the key idea is that it looks at the bandwidth, the system idle times and the bandwidth utilization, and performs these migrations. The reason why we do look for these parameters is because, again, we don't want to add more overheads into the IO request. Now, we also achieve coordination between the agents. The way we do that is through the reward structure that I just mentioned, where the migration agent looks at the placement latencies of the data placement agent, and then provides a reward to the migration agent. Now, the RL agent design is kind of similar to what we saw in Sybil, but our RL agent is the neural networks that we use here are much smaller compared to what we saw in Sybil. So we have a single hidden layer and an input layer and an output layer. So again, we kind of make the execution asynchronous. So the training happens in the background and we update the weights periodically. Now that's about the design of Harmonia. I'll go into a bit of evaluation, but if you have any questions, I can take it right now. Yes.
So if the migration happens, so you said that there was a like delayed in the design, there was a delayed feedback.
Yep.
And in the real system, you don't know when will the actual migration happen because you don't know the information about bandwidth and the queue, right?
So that's so we continuously look for the bandwidth utilization of these devices. But if in a very high intensity workload, we don't actually get the time to migrate these devices, we have some optimizations, like we look at all the reads that are happening and see if any of these reads are in the migration queue, and then queue them up as low priority writes to the devices. So I mean, this is something that we cannot really avoid, because if the IO intensity is very high and the placements are happening at a fast rate, we have to delay the migrations.
I see. I get it. Yeah.
Yeah.
So there's no like
There is no like a golden rule that can fix everything in this kind of an environment.
Okay, sure.
Yeah. So we again look at two different, or actually in this case, we look at four different configurations, three different configurations, sorry. We look at a dual hybrid, tri-hybrid, and quad hybrid storage system. We have two configurations for our evaluation, mostly like the performance optimized configuration and the cost optimized configuration. We have 8 baselines now, to data placement, to migration, and extended techniques. We also interestingly look at a single agent for both placement and migration to see why do we need 2 agents? Can't we do it with a single agent? But again, there we see that learning one objective or learning one task doesn't necessarily reflect on the other task, because the learnings cannot be transferred if the tasks are different. Now, we also look at 17 data intensive workloads from some of the newer workloads compared to what we saw in Sybil, like even ML perf storage, where we look at image classification, ResNet 50, and then cosmology, parameter prediction, and Cosmoflow, and so on. So these are all standard benchmarks that are available from available open source. Now, in terms of performance evaluation, we see that compared to Sybil, we achieve 32% performance improvement on average. And it also bridges the gap between Sybil and Oracle by 64%. Now, on a cost optimized HSS configuration, we see that the performance also is quite similar, purely because we have the migration also optimized, and there is coordination. So in terms of extensibility analysis, we have like a 3-device configuration where you have a high-end SSD, middle-end SSD, and low-end HDD, and 4-device configuration. So we also add one more. So in these 2 configurations, we see more benefits coming, because prior approaches are still not able to scale because they have some heuristic policy somewhere in them, and they can't really scale up to these kind of configurations. Again, in terms of extensibility, it's quite simple. We add a new action to the agent, which means that you need to add a new node in the output layer of the neural network. We add the remaining capacity of the new device as the state feature for each agent. Now, yeah, we'll see more benefits if we have more devices in the HSS. There is also the factor of device lifetimes, which we have to consider, because now we are letting the RL do the migration of the data or even the placement. So how does it impact the lifetimes? So we see that So if you compare Harmonia, which is in green here, and we show the write amplification on the y-axis, which means that if the write amplification is more than 1, then it means that whatever the number of writes that the application performed, we are writing more than that in the SSD. So if you see the green bar, then it actually is higher than some of the other policies, like this was RNNHSS, and in both the cases. So the write amplification is slightly higher. But the key takeaways from this is that in read-intensive workloads, where there are no updates from the application. So if the application sends an update, then the data placement agent can place the data wherever it wants. But if in a read-intensive workload, you don't actually get the updates. So the data has to be prefetched or evicted from these devices by the agent. So we observe that in read-intensive workloads, the write amplification is higher because the RL is learning that you need to prefetch more from the slower device, the pages, and then put it in the faster device. So when there are reads going into the faster device, the latency will be much lower. In the write-intensive workloads, we see that the write amplification is much lower. And this is because it knows that the application is going to send some updates and you don't have to prefetch the data or evict the data. We also see benefits in terms of multi-programmed workloads. Again, these are workloads where these are cases where we have 8 threads running in parallel, and we are pushing requests into the agent. And we also see some benefits in terms of tail latencies. So this is a very complicated figure to parse, but if you look at the fast only policy, where you have all the requests going to the fast device, and you see Harmonia, which is in green, then you see that it's more closer to the tail latency is much lower than other policies, which are basically performing migrations in the critical path, which means that they are moving data when there is an IO request going on. So in terms of tail latency, we see benefits because we perform migrations when there are idle times. We monitor the bandwidth of these devices and perform these migrations. So we get benefits there. In terms of overhead analysis, we have our total storage cost increases slightly compared to Sybil because we have 2 agents, but our agents are much more lightweight compared to what we saw in Sybil. We have some metadata overhead to track the application characteristics. That's around 32 bits per page. Inference latency is quite low. We evaluated this on a real system, around 240 nanoseconds. Training latency is also quite low, but running in the background. So we have a lot more analysis in the paper. We show the throughput evaluation on unseen workloads, where you train the hyperparameters on a different set of workloads, but evaluate on another set of workloads. We also show the impact of uncoordinated agents, performance sensitivity to migration queue size, and the number of requests considered in the migration agent's reward, convergence of the policies, how fast these policies are able to converge. And we also prepare a synthetic workload to see how Harmonia can adapt to workload changes, and we see really good performance there. We evaluate Harmonia and baselines on a persistent memory-based HSS also, which is where the latencies are quite are very critical. So we also see benefits there, and we provide a detailed overhead analysis. This is the link to the paper. So in conclusion, this is the first work to use multi-agent reinforcement learning to optimize data management in hybrid storage systems. We see performance benefits over best performing prior approach. We also, when it's also an extensible technique, which means that when you add more devices, we see better performance and low inference latency and storage overheads. And this is the end of my presentation for Harmonia. Any questions on this?
Thanks a lot, Rakesh. I have one question. So basically, I want to repeat the question you asked for Gagan. So yeah, how would Harmonia extend it, basically, you know, for considering the nowadays general technologies?
So, so we have in the paper, we have also discussed this at length, where we look at tiered memory systems or tiered storage systems. We look at CXL systems where if you have a memory pool, you still need to perform data placement and migration. And we can actually deploy these kind of lightweight neural networks there in those kind of systems, in the CXL controller, for example. In case of tiered system, what we propose is like the placement can be very simple because you only need to place at the highest tier, but migration becomes more critical. So RL can benefit from, can be useful in those kind of scenarios. But again, it depends on the substrates or the devices that we are using there. If we have very low latency requirements, I guess these kind of techniques don't really, they have a higher overhead and we cannot really afford them, but we can actually use other RL techniques to still make it adaptable and useful.
Yeah, that sounds good to me. Also, I think partly the fact that we can do complex operations for understanding where to migrate and where to place is the fact that basically the DC axis, I mean, I axis is long enough. You know, you have enough slack that you can hide. If we want to implement this similar idea for faster memory devices, first my question is that, is it possible? And if yes, how can we basically adopt it?
So in our evaluation, we also show that on a persistent memory based HSS, as I said, the technique can change because if you have more faster devices like DRAM or an NVM, then the latencies that we are looking at is in the order of nanoseconds. And these the inference latency for this technique is in, let's say, 200 or 300 nanoseconds, which is much higher. So we need to look at, let's say, a table-based RL approach or other kind of techniques that are more lightweight, and we can still benefit from the adaptability of reinforcement learning. But the technique has to change, but the fundamental idea will still be the same. Yes, Nick. Yeah, sure. Yeah, go ahead. Okay, so the question was whether Harmonia can be implemented for compute-enabled systems, storage systems. Yeah, it can actually. Since we are looking at data sets which go beyond the capacity of a single disk, and we have more devices, we need more devices to store the data. I think the challenge would be to kind of manage the policies like data migration and data placement, because for compute we need the data to be in certain locations, and spatial locality and temporal locality matters there. So we need to add more objectives or more features and kind of look at the reward structures more carefully for those kind of systems where we need where we don't want the data to be placed everywhere, and that kind of causes problems for the compute system. So it can be beneficial, but again, we need to look at how we can manage this or configure the RL better.
Any other questions? Anything on YouTube? I haven't checked actually. Okay. Then I think we can move on to the next talk.
Okay. Okay. So this is the last talk of this today's workshop. So this work is called Venice, improving solid state drive parallelism at low cost via conflict-free accesses. And this work was published at ISCA 2023. And this is a work where we look at how we can change the SSD architecture and how we can solve the problem of accessing shared resources. So Mohammad is also here, who is the primary lead of this work. So I'll quickly give some motivation for this work. So this, you have already seen the design of an SSD. You have a SSD controller, which are embedded cores on the device, which perform many functionalities like interacting with the host, performing flash translation responsibilities, address mapping, doing garbage collection, ware leveling. There are a bunch of tiny cores called flash controllers, which basically are responsible for sending the commands to the flash chips and reading the data and so on. There's also a DRAM that you all know by now that which actually stores the recently accessed data, part of the mapping table, and so on. And these flash chips that are storing the data are connected to the flash controller using shared channels. Now, the problem that we look at in this work is called path conflict. So multiple flash memory chips are connected to the SSD controller using shared channels. IO requests that attempt to simultaneously access the flash chips use a single path, which causes path conflict. Path conflicts cause IO requests to be transferred serially on the shared channel, and this limits SSD parallelism and reduces performance. Now, we look at a case where this path conflict is seen. So if you have a single channel where 4 chips are connected, and if 2 requests arrive at the same time, then they both basically cannot be accessed or processed in parallel. These are read requests, by the way. So this, we call it as path conflict. So the way we do this is we take one of the requests, prioritize that, and serialize these operations. So every read request has 3 steps. So there is a command transfer step which happens serially for the 2 requests. There is a read operation which can be done in parallel, but again, this depends on the command transfer, and the data transfer has to be done completely in serially. Now, all these 2 parts of the read operation are served serially. Now, if we have 2 different channels and the read requests are arriving at 2 different for 2 different channels, then these can be served in parallel. And in that case, you see that the command transfer, the read operation, and the data transfer are done completely in parallel. And this also saves a lot of cycles. Now, we can't always expect the read request to always arrive in parallel into different flash chips across channels. This again is an attribute of the workload. So, so if we have path conflicts, we see that it increases the average IO latency by 57% in in our experiments on a performance optimized SSD, and it can actually go up to 1.6 times for high IO intensity workloads. Now, we looked at how prior approaches can solve this problem, are solving this problem basically. So this is the baseline SSD configuration, which again has a shared channel and multiple flash chips connected to it. We have something called the packetized SSD, which increases the bandwidth of every channel. This can only help so far as reducing the latency of the data transfer and the command transfer, but it still doesn't actually solve the path conflict problem completely. There is still a serial processing happening in this configuration. So they don't provide path diversity to flash chips, these kind of shared channel configurations. Now, there is something called the packetized network SSD, which actually introduces more paths to each flash chip. So you can see there is a horizontal channel and a vertical channel. So every flash chip is connected by 2 paths. And there is also a network on SSD, which introduces a network of flash chips, which are connected through links. But the problem with these techniques is that they don't effectively utilize the path diversity, and they incur large area and cost overheads. So our goal in this work was to fundamentally address the path conflict problem in SSDs by increasing the number of paths to each flash chip at a very low cost. And we wanted to effectively utilize the path diversity that we enable for communication between the controller and the flash chips. So we introduced Venice, which has a low-cost interconnection network of flash chips in the SSD, conflict-free path reservation for each IO request, and a non-minimal fully adaptive routing algorithm for path identification. So we'll go over each one of these contributions. So let's start with the low-cost interconnection network. So in Venice, we introduce an interconnection network of flash chips. So where we call each of these as flash nodes, the green boxes, and these flash nodes are connected through bidirectional links to their neighboring flash nodes. And each flash node is having a flash chip, which is the commodity flash chip, and a router chip placed next to it. And they interact with each other using the regular IO bus that is present. So the router chip is what actually connects the different flash nodes in the network. And these are called links. So Venice provides this increased path diversity at a very low cost, because we are not modifying the flash chip, unlike prior works, which actually introduces a lot of overhead in terms of adding buffers and inside the flash chip, and also connecting these links. So we don't modify the flash chips in Venice. Now we look at the conflict-free path reservation for each. Yeah.
So for me to picture it in my mind in a more clear way, the green boxes here, is it like a package? Like, do we have like, or so how should I picture it in my mind? Like there's a board over there, and you have what, like chips, and is blue thing a chip, or is green thing, well, it's a chip. Okay.
So you can visualize it like this. This is this box is basically the flash chips that are present in an SSD. These are the boxes that you can see here, and a small router chip that is placed next to it. So you will, instead of every flash chip that you see in a commodity SSD, you have like a small router chip and a flash chip that are placed next to each other.
Okay.
So,
but they are not in the same package like a green box necessarily.
No, they are not in the same package.
So the communication between the router and the flash chip is also off-chip communication.
Yes.
Okay.
Yes.
I want to add something.
Yeah.
Basically, flash node is a kind of logical abstraction of what we are talking about. There is no, I guess, physical.
No physical entity called flash node.
Okay, so when we access data, we access the flash chip through the router chip.
Yes.
So it should increase latency, I guess, right?
Yeah, I mean, the thing is so sorry, I'm wrong when I say yes. The flash chip has its own IO pins, right? So what we are, so that path is also connected to the flash controller. So the flash controller still has okay. Let me recollect what we did in Venice. So this IO bus is still, I guess we need to go through the router chip. So there will be some overhead. If I'm not wrong, Mohammad.
No, you're right. But I want to add that basically, so the transfer is actually pipeline. So, for example, we want to send a write request, and that write request is like, for example, 8 kilobyte or 16 kilobyte, but our basically channel bits is actually 8 bit. So we are pipelining the transfer. So in the end, that extra step would affect only for the first 8 bits. In the end, it's not going to affect the total transfer latency.
And I guess by adding routers, you already have a better bandwidth anyway, right?
I mean, that part we're gonna get to that, right?
Yeah.
Okay. Thank you.
So yeah, that is the part where we kind of leverage the part diversity, and we have a better bandwidth compared to the shared channels. You had a question.
Yes, I mean, fundamentally, if you see only the architecture, how is it different from the previous one?
So yeah, so the previous work that we saw basically had the router chip also present inside the flash chip, and they used a very simple routing policy, which basically looked at XY routing, where it can only go horizontally and vertically.
Oh, got it. Yeah.
So that's a very simple routing policy compared to what we propose in Venice. But the main limitation is that all of these things are, all the router chip and a lot of buffers are being added to the flash chip. Okay, so I'll move on to the next part. So now we'll look at how we reserve a path for conflict-free IO transfer. So we use a small scout packet to reserve a conflict-free path for each IO request. So whenever an IO request comes to the flash controller, let's say the target node for this IO request is F8. So what this flash controller does is it sends a small scout packet that goes through the network. Whenever it reaches the router of each node, it basically registers, the router creates an entry for this packet where it basically registers the packet ID, the entry port where it came from, exit port, and the valid bit. Now it continues to traverse through the network, finds a path to the destination node, and the router in this destination node, it registers or it reserves the path through the entry and the exit ports of all these nodes, and then sends back the scout packet back to the flash controller to indicate that the path is reserved. So this is for a single IO request. Now, the scout packet that we use is a very small data packet that has a header flit and a tail flit. And we basically, we have some fields for destination flash chip ID, the source controller flash controller ID, and some unused bits. So here in the first bit of this flit, we basically indicate whether it's header or tail. And the second bit, we indicate whether we are canceling the path reservation or we are reserving the path. And this cancellation is basically used when we are in scenarios like live lock and deadlock, where the scout packet can traverse through the network without finding a good path into the destination node. I'll not go into the details of this, but you can find more details in the paper for how we handle that. So we look at, again, if there is a path reserved for F8 and then we need to access F9, which is an IO request, which is the destination node for another IO request, then what we do is we find the nearest neighboring flash controller to send a scout packet for that IO request. So it goes like this, comes back and reserves a path. So now once the path is reserved, the data transfer can happen without any conflicts. So path reservation eliminates path conflicts by enabling conflict-free IO transfer. The overhead of the path reservation is negligible because of the small size of the scout packet. So as you saw, the scout packet is quite small. Now the third contribution, yes, please.
So when we reserve a path, for how long do we reserve it?
Till the IO transfer is completed.
And what is the typical payload of that IO thread?
16 kilobytes or 4 kilobytes, depending on the page size that the application requests.
Okay. So it's pretty much instantly, I guess, like you reserve, you get the data, and then you move on. Okay. Okay, thanks.
So the third contribution is we look at a non-minimal routing algorithm for path identification. So this is a case where we don't actually have a minimal path to access the flash chips. So here is a scenario where you have these ongoing IO requests which have path reservations. Here you have 3 requests which have reserved these paths in orange, red, and green. These are the reserved minimal paths. Now you have a target node which is F2, and we need to find the best way to kind of reach this destination node because all these 3 flash controllers are busy now, and the only one available is F3. So what we do is we find a non-minimal path to reach this compared to, let's say, waiting for in the queue for one of these flash controllers to free up and then get the minimal path. So we take this longer route and reserve this path. So this is a non-minimal path. As you can see, it kind of goes through the idle links that are available in the network and reserves a path. So we are trying to effectively utilize the idle links in the interconnection network instead of, as I said, waiting for one of the controllers to become free and then use those nearest paths to the flash node. So there are more scenarios that we look at in the paper. We handle the deadlock and live lock scenarios. We provide the overhead for exercising this non-minimal path. We also show how these prior architectures try to mitigate this path conflict problem, and more details on the non-minimal adaptive routing policy. Before I jump to evaluation, yeah.
Can you go back to the diagram? Over here, so F8 is receiving the data, but it is also forwarding the other data forward. Okay, yeah. So over here, F8 is receiving the data. The F8 node is receiving the data from its source, and it is also acting as the interconnect between the link between for the blue path. So when it is receiving the data, will the data directly go to the internal flash chip, or will the routing chip will receive it and then it will send it to the flash chip internally?
Path reservation, we are only looking at the router chip.
Yeah, okay, over there only routing chip will be active, but for the red one, it will directly go to the flash chip?
Yes, it is transferring the data to the flash chip. But since the router chip has other links that it can also leverage, it basically allows the path to go through this flash node. So it is only using one of the 4 links that are available for this flash node to use for data transfer, but the other links can be used for the scout packet and the data transfer for this F2 group.
And how big is so does the routing chip also have its own SRAM or something?
So we
Set of
have a very small buffer in the routing chip, unlike the prior work, which actually uses 16 kilobyte buffers or multiple such buffers. So we don't actually have a large buffer in the flash.
Okay. Yeah, thank you.
So normal flash device F0 and F4 will have the same latency, but for this, I guess the left parts have a faster latency compared to the right ones, right?
You mean F0 will have a faster latency compared to F8?
F4, I guess.
Yeah, okay. Yeah, it should have a much faster latency. Yeah.
So if then does it like is it more sensitive to data placement, or like can we like try to optimize data placement for this particular?
Yeah, this yeah.
You can answer again with pipeline.
Yeah. Yeah, that's also a good point that I mean the path length is not actually the key bottleneck, that you can basically pipeline these transfers because the IO pins are still limited in the flash chips. You have only 8 bits. But to answer it in another way, I think we need to look at the data placement policies for these kind of interconnection networks, which we haven't really explored much in this paper, because the FTL policy has to be looked into.
So I'm not confused. Like, are you saying that because this pipeline it won't matter much, that it's unexplored?
So the overhead is not so high, as Mohammad said, that the first set of transfers will basically have a higher latency, but over a period of time it gets amortized. But if let's say we can also look at scenarios like where you have more data in these nodes. I mean, that actually can be helpful, but then it also means that your flash controllers are also yeah, I mean that I don't want to go into those details, but anyway, if you place more into these things, you only have a limited capacity to kind of place the data, right? So you ultimately have to move to other flash chips anyway.
Oh, yeah.
Yeah, but I don't know if you want to add something.
Yeah, I'm gonna add a bit. So I agree with Rakesh. In terms of performance, I don't really think that's really important, because as I said, like when you're transferring, let's say 8 kilobyte of data, you have 8,000, chunks of like packets, or we call it fleets actually. So we have 8,000 fleets, and only for the first fleet, you need to spend a bit more time, and rest per cycle, you're going to receive it, So overall, you're not going to see actually much change. But maybe in terms of power consumption, we might consider, we want to, place them more closely, because when you go over all these links, you're consuming more power essentially, right? So that might be something that we can think about it.
Yeah.
I have one more thing. Every flash chip inside each flash node is directly connected to the flash controller, right?
Yes.
So then when you are transferring the data horizontally, that is for blue path, let's say, from FC3 to F18, will you be going through routing chip of each node, or will it be directly through the connection?
No, it will go through the router chip of each node.
So can it be that you can leverage that connection when you're going horizontally, and only when you want to go up and down, you can use the routing chip?
So
wouldn't it make it faster?
So the direct connections with the flash controller are only like some select signals that we are using for the flash chip, but the IO bus is still connected through the router chip, right?
Okay. Okay. All right. Yeah.
I also have a follow-up.
Yes, please.
So, just like hypothetically, would it make sense to put more flash controllers in this design like this is like a mesh network of flash nodes, right? So let's say at every edge of this, like on the top, on the right side, on the bottom, we have flash controllers everywhere, so that we can access to the flash node we want at most at like 2 hops or something like that. Would that make sense? How expensive is putting an extra flash controller?
It makes sense. It can actually make it much better. This is similar to like adding more flash channels and increasing the parallelism in the SSD, but the cost, as you mentioned, will be much higher. You need to have this. These flash controllers are again tiny cores, right? So you need to have more cores in the SSD that can increase the power consumption, goes beyond the power budget. You need to have dedicated signals, the transmission wires connected to the flash nodes. So it basically means that you need to have your area and power budgets are much higher. Power consumption is much higher.
But what if I have like a big chip with like multiple flash controllers in it? Does it make any difference? No.
No, I don't think so.
Okay.
It will still be the same.
Yeah, that's true. Yeah. It was down to
I think Nika had a question.
Actually, I think I can ask one question at the end. It's not very related to these details. So
If you come out here.
I just want to like discuss in the same way. Like instead of that, can we just thinking, is it possible to add some intelligence to the flash chip itself so that they can communicate with each other better?
But isn't that what the router does?
Like flash controller is controlling
Mm-hmm.
the flash chips, like where the data, how the data should get out and from where. But if the chips can communicate with themselves, among themselves, they can maybe have some better decision, better routing to get out the data.
Mm.
So this is actually going towards like a wireless network where you have different nodes connected in the out there, and they have to communicate with the neighboring nodes and so on, right? Yeah, I guess it's possible. The only thing is, in this kind of a system where you have constraints, whether those scenarios are realistic, or maybe can we deploy those kind of techniques here? I'm not very sure, because you need to have more intelligence in each flash chip. And again, if you are not constrained by any of these constraints like power and area, then for sure it can kind of sync up with its neighboring nodes, transfer data by itself. But again, there has to be some arbitration, because there is this big box sitting on the left which has to know what is going on, right? Yeah. So it has to keep like broadcasting signals to the flash nodes, get to know the status. Yeah.
Just like maybe we can even think of how swarm robotics work, where they have a controller and then small units where they don't have very minimal intelligence and then can communicate also. Maybe something can work here also, probably.
And this is something that we were exploring with in our other work, where we wanted to, or actually in this work, we were trying to see whether for garbage collection, can we move the data without always going to the flash controller. Like you have to transfer data from, let's say, F3 to F2 or F3 to F4. Can we really do that without sending commands from the flash controller? But I mean, these are entirely possible, but again, it depends on the constraints. Yeah. I guess, yeah. Any more questions? Okay. I'll move on to the evaluation. We use MQSIM to evaluate this our work and also the prior works. We have two configurations: the performance optimized configuration and cost optimized configuration, which are based on modeled on real SSDs from Samsung. 19 data-intensive workloads from different benchmark suites, and all the prior approaches that we discussed in the motivation with a path conflict-free SSD. That it's an ideal scenario where there are no path conflicts. Now, in terms of performance analysis, we see on a performance optimized SSD where the access latency is very small. You see that compared to it's normalized to the baseline SSD here. So the speed up is, let's say, around 2.7 times the baseline SSD and 1.9 times the best performing prior approach. And it also its performance is within 45% of the path conflict free SSD. In cost optimized SSD, you see that the performance slightly reduces because the access latencies are much slower. And here you see that it's around 1.5 times the best performing prior approach. And compared to a path conflict free SSD, its performance is within 25%. So it provides significant performance improvements. This is the more critical result that we want to see, which is how many path conflicts do we observe across all these baselines and Venice. So here we see as high as 35% of the requests observe path conflicts in many of these workloads for the prior approaches, but in case of Venice, we see 99.98% of the IO requests don't experience path conflicts. So with path reservation and effective utilization of the path diversity, we mitigate the path conflict. Now, even here, I think this number should not be, we should not see the 0.02% of the path conflicts, because what we have added in this number is basically the flash controllers being busy. All the flash controllers available in the SSD being busy. So it's not a realistic, let's say, value which is indicating whether there are any path conflicts. Yes, please.
So these are very impressive results, and tells me something like maybe we have more hardware than we actually need in that design. So if that 0.2%, like the fact that all the flash controllers are busy is only giving me like 0.2% of 0.02% of overhead here. Maybe I can reduce the number of flash controllers, right?
Yeah, I mean, you could say so. I mean, it depends on the intensity of the workloads also. Like
yeah,
some of these,
but these are plausible workloads, benchmark suites, right?
Yes, you could say that. I mean, if you have a network where there are, let's say, fewer flash controllers but more flash chips, our policy can perform better in those scenarios.
But I wonder, like the ultimate bandwidth of the device should be like determined by the number of flash controllers. Yes. So
Yes.
if you reduce the number of controllers, you'll be reducing the bandwidth.
But do we utilize the full bandwidth?
Not all the time. I mean, we try to utilize as much as possible, but in case of random workloads, you always have some of the resources available. But I mean, we are not targeting those scenarios, but when there are very high intensity workloads, you end up using everything.
But that's actually one of the reasons why this work, makes sense. Because so the available internal bandwidth we have inside the SSD could work when your application has good regular access pattern, But once you have more random accesses, you're going to have more conflicts, and then you cannot benefit from the channel bandwidth essentially. So with this kind of interconnection network, the utilization of that internal bandwidth can be higher.
Yes.
But we are not exceeding the total bandwidth. The total bandwidth is still the same, but
Of
we are
course,
utilizing that better.
Yeah, that makes sense. Does this also show anything about this, like how many of these links between flash nodes are, like what fraction of them are utilized at a given time, for example, when you reserve the paths? I guess maybe I can just like keep going and then tell you like what I think. So in the router, it's more like I wouldn't say complicated, but it's like a fully functional router with like for the 2D mesh network over there, right? So would we get some similar performance improvements with a simpler router? Like maybe some of the links are not enabled at all, and it's still okay because maybe there are some other paths that we can still reserve.
So one thing that I can answer it in one way, that in terms of power consumption, these links are not consuming the same power as the regular channel, which has to be active. So the static power is not so high. So in case you want to turn it off and basically look at what paths are being accessed more frequently and kind of turn on or off some of these links, I think that's something which we can explore. I tried to do some experiments to figure out how many links are available in the flash network, in the network. I don't have the results, but I need to go back and look at it.
My main concern was not the power consumption, but the cost of the silicon itself, basically.
Yeah, I got it.
Yeah, at this point, I think we have kind of not. Yeah.
I think basically what Giray is saying is that, so now we consider that we have 4 links per each router, but he's thinking of, okay, maybe we can have a pool of, in total, we can have the pool for 3 links, and then we can reconfigure to which link we want to have, based on the utilization. Is that what you're thinking of?
So that can be one case, or maybe like nobody goes up, but some of them go down or something like that. I don't know. Like
I mean, that's exactly
like some different topology, basically.
Yeah, so we can, if we want to do that, we should try to look into some more reconfigurable topologies, actually. I mean, this work has a lot of deadlock and live lock issue, but we fixed it, so it's possible.
Because if you can configure online or some way,
Mm-hmm.
you might run into deadlocks, right?
No, but you don't. Yeah, I mean, of course, you should have a granularity or when you want to reconfigure. You cannot reconfigure at on the fly that fine grain. Of course, yeah, you're right. Yeah.
So let me give an example. Let's not consider it like reconfigurable, but maybe like I have like small sets of nodes with ring topology, and then these small sets of nodes are connected to each other with a mesh topology, for example. So I don't implement all the links in the hardware to begin with. Like it's like just to make the chip much smaller, maybe put it inside the flash chip back.
Well, like so here, like we have a very simple routing algorithm that works, but in that case, wouldn't the routing would be difficult?
Could be, yeah.
No, actually,
yeah, but
I'm just asking, what
I would say that the routing approach that we have taken here should work in those topologies also, where we are basically looking at idle links whenever we traverse a node and trying to find the best path to reach the destination node. So if we have fewer links that are connected to the node, then we should still, as long as nothing is available for that particular node, we should still be able to find a path. Mohammad, I don't know.
No, that's actually very exact response. And also, I like what you're suggesting. Actually, we can look into it, because one of the main overhead here is actually the number of router links. Because the router die area that we synthesize using tools, Synopsys, is actually very, very small. But then when we want to put that in a chip, you need to consider the IO pad distance, between all these IOs. I remember Nika and we worked together a lot to, to find the area of that chip. So, and actually our router chip is not that small. Even though the router die is very small, the router chip is not that small. So if we can reduce the number of links, that can actually significantly reduce the cost, area cost. But of course, we should see if it comes with at the price of performance or not. But yeah, that's something we can check.
Yeah, sure.
Thanks a lot. Yeah.
Thanks.
Yeah. So we also get some energy benefits from this design because we don't always wait for the path to become free or the flash controller to become free. We immediately find a different path and then process the request. So the waiting time of these IO requests are reduced, and we see benefits in terms of energy consumption. So it's around 46% better than the prior approach. Tail latency has, we see benefits there also. You can see Venice here compared to path conflict-free SSD. Yeah, we see around 32% reduction on one of the workloads and 22%. Again, this is primarily because if you have longer waiting times in the queues, then you have higher tail latencies, and that we reduce by our the path reservation and non-minimal routing policy. So we also show performance on mixed workloads where we combine multiple workloads and then generate mixes. This is primarily to indicate that if we are having more intense workloads, how does Venice behave? And we see benefits there also. So the performance slightly reduces compared to, let's say, standalone workloads, but we see still higher benefits. Yeah. So we also show the sensitivity to different network configurations. Here, there are some interesting results here, which I found it interesting when we were working on this back then. So in case of 4x16, we don't see much benefits, or the gap between the best performing prior approach and Venice is not so high compared to 8x8. And this is because we are limited by the flash controllers in this case, because on most occasions the flash controller is quite busy.
So does that notation mean that you have 4 flash controllers and 16
4
nodes?
flash controllers and each 16 chips connected to each flash controller.
Okay.
16 nodes connected to each flash controller. 8x8, sorry, I had to explain that. 8x8 is when 8 flash controllers and 8 nodes connected to each one. 16x4 is 16 controllers and 4 connected to each. So you see in case of 8x8, this is kind of a sweet spot in this experiment. In case of 16x4, we still see the gap is not so great because the baselines are also behaving better in this case because we have more flash channels and that parallelism is already available. So our baselines are becoming better in case of 16x4. So yeah, that's about the sensitivity to different configurations. As we mentioned, in terms of power consumption, we have 0.24 milliwatt per 4 KB transfer for each router, and we have 1 per flash node, and the area of the router chip is around 8% of the flash chip area. In terms of link, we have for every link that we through which we transfer the 4 KB page, the average power is around 1.08 milliwatt, which is much less compared to the shared bus power consumption. And the area is around 0.04 times the flash channel area. So yeah, we provide more details on this in the paper. This is the link to the archive version. So any questions, or I'll move to the conclusion. Okay, so Venice is a technique which mitigates path conflicts by efficiently utilizing the path diversity of an SSD interconnection network, improves performance over the best performing prior approach, reduces energy consumption, and it's a very low cost technique and requires no changes to the commodity flash chips. So that's pretty much what is a very high level overview of Venice. Any questions? Yes, Nick.
Could you come close? Oh, okay.
So my question relates a little bit to my previous question for Harmonia. So if we were to design a network for in SSD computation or like in flash computation, how would we need to rethink Venice's design? So I'm thinking also a little bit in the lines of, let's say, the network we had in the case of Tesseract, right? So that's one of the possibilities. But I'm wondering, have you put thoughts into how the network should look like for computation-enabled flash chips?
So to answer that, we haven't given much thought into like how we can change the network topology for in-flash processing. But if we look at the topology that has been proposed in this work, I think that can still benefit for in-flash processing techniques, because if we have to move a lot of data across the flash nodes for computation, then this technique can give a lot of benefit compared to, let's say, moving the data to the flash controller. For example, one of the recent works called Aries Flash performs multiplication by moving the data to the flash controller. Now we can alleviate those kind of transfers by moving the data within the 2D network and then copy the data to some other flash chip where the computation is happening. And that is a very simple example to show the benefit. Again, in terms of, there can be scenarios where you have garbage collection and other scenarios coming along with computation that can also be benefited with this kind of topology. But that's also this is also something that we are targeting for another submission soon. So we need to look at, so we haven't looked at the topologies, different topologies, but this can be certainly benefit in flash processing. Yeah. Any other questions?
I have a small question. Could you go back to, I don't remember which post. Could you go back a little bit? Yes, this one. So it just stuck in my mind, this question. So these results are normalized to the baseline SSD, right?
Yes.
For all configurations within themselves, I guess. So if you look at the absolute values, should I expect those blue bars to be equal to each other? Because it's like path conflict free?
Not really.
Because the total number of flash chips are the same.
But the number of controllers are different. So
yeah, the total number of flash chips are the same. But again, the
Depends how we implement them.
yeah, maybe we should. I'll check this, because that's actually a good point. That should we have expected the same value for all of them? Yeah, what we had done is to dedicate one channel for each flash chip. So for the ideal case, but yeah, we should.
That's what I also now remember.
Yeah.
Yeah, so all of them, they have 64 flash chips. And
yes.
For path conflict-free SSD, we consider that each flash chip is connected to has one specific channel.
So 64 controllers in a sense. I see. Okay.
I think that should be equal, but I'll check this.
Hmm.
Yeah.
Okay. Yeah. And one more small question. It's not really important actually, but I'm just curious. So all these like conflicts should depend on how the data is laid out across chips, right?
Yes.
So did you put some extra effort to randomizing this data, like locating your data across these chips?
Yes. So what we did was we explored different page allocation policies. So there are different allocation policies in terms of how you place the data across different channels, planes, chips, dice. So there are many techniques that are already supported in MQSIM. And we looked at all these policies and took the one where prior approaches are performing the better actually.
Okay.
So we took the best case of all the prior approaches and then evaluated on that.
Yeah. Sounds good. Thanks.
Yeah, you had a question. Sorry, what is it?
I think it's good.
Okay.
Do you have a question, Joe?
Yeah, you said that like if it's one component per channel, shouldn't that be like compared to the baseline SSD, shouldn't it be like 16 times, 8 times, 4 times higher?
What do you mean?
No, because you don't have that much conflict, right? You don't have 64 requests on the fly.
Yeah.
But in order to make sure that we don't have any path conflict, we should have considered that. I mean, that's why we consider 64 channels, but for sure not all of them are utilized.
Yeah.
Okay, sure. Then I think like this is where like 4x16, that's the point where the links are underutilized, right?
Yeah, there are links under it. Yeah, of course.
That's
I
true.
think that if you go to the left part, there are more links that are underutilized, so we have more chance to optimize or improve the links. Possibly.
In case of 4x16?
Yeah, compared to 16.
I'm not sure because you're saying the links near the flash controller are underutilized. Is that what you're telling in 4x16?
I mean, so you have a mesh, and you're talking about you can just prune some like topology or cross points, but maybe if the SSD, I don't know what a real SSD configuration is, but the less the number of controllers and the more chips you have per controllers, probably they would have a better chance to prune out the links.
So in that sensitivity section in the paper,
Yeah, in the sensitivity section of the paper, we discuss about upside because so when we have less number of controllers, in one sense this can help you to get better performance, and in some other way it actually affects your opportunity.
Yeah.
So that's why the sweet spot is coming 8x8. But now I'm trying to remember what was that.
So the point was like if your flash controllers are busy all the time, then you don't see much benefit because even Venice has to wait for the sending the scout packet. But if the flash controllers are available and let's say 3 of these paths are already occupied, you can still take the remaining path and then find a good path, conflict-free path for the IO request. So as Mohammad said, the benefit is you can also get some benefit, but depends on whether the flash controllers are available or not. Yeah. Okay, then that closes. Or do you want to give a parting comment? Yeah.
Okay, so yeah, let's first thank the speaker. Thanks a lot, Rakesh, and thanks a lot everyone that today they gave talk. I think we had several excellent talks. We have learned a lot of good things. Some of these works were familiar to us, but today also we had quite fruitful discussion on all these works. So thanks a lot also to Giray that he basically organized SaLWo. And I don't know when is going to be the next edition, but stay tuned and we will inform you. Do you want to add anything? Yeah.
So maybe I can ask a little bit.
Okay. I just unmuted myself. So yeah, thanks a lot for attending and making this a lively event. I really enjoyed organizing it, and probably in the next edition I will not be organizing because I'm leaving soon, and I'm starting my own group in CISPA and hiring students. So in case you know good students, please refer them to me. Yeah, that's all.
Okay, thank you.